Right now, somewhere in the constellation Orion, a star 16 times more massive than our Sun is burning through the final chapters of its life. It could explode tomorrow. It could explode in 1,000 years. Or it might have already exploded, and the light from that catastrophic event is racing toward Earth at 186,000 miles per second, closing the distance between destruction and discovery. Betelgeuse isn't just dying. It's preparing for one of the most spectacular shows the universe can produce, and when it happens, you'll be able to see it in broad daylight. 4 months. This is the story of a star on borrowed time and what happens when something that massive runs out of fuel. Every clear winter night, Betelgeuse marks the shoulder of Orion the Hunter, glowing with that distinctive red-orange color that sets it apart from nearly every other point of light in the sky. You've probably looked at it 100 times without knowing what you were seeing. A star so enormous that if you replaced our Sun with it, its surface would extend past Jupiter's orbit. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter itself, all vaporized inside a single stellar atmosphere. The numbers barely make sense. More than 400 million suns could fit inside Betelgeuse's volume. Its radius stretches somewhere between 640 and 764 times larger than our Sun, though pinning down exact measurements proves frustratingly difficult for reasons we'll get into. The star sits roughly 650 light-years from Earth, which means the light hitting your eyes tonight left Betelgeuse around the year 1374. The Black Death was ravaging Europe. The Ming Dynasty was just beginning in China. And Betelgeuse was already ancient. But here's what makes this star genuinely unsettling. That light we're seeing, those photons that traveled for 6.5 centuries to reach us, they're showing us a star that might not exist anymore. Betelgeuse could have exploded last Tuesday, and we wouldn't know until the year 2674. The star could have detonated during the Renaissance, and the light from that explosion is still crossing the void between us, carrying news of a death that happened before anyone alive today was born. Scientists estimate Betelgeuse is less than 10 million years old. That sounds old until you remember our Sun is 4.6 billion years old and has another 5 billion years left. Massive stars burn fast and die young. They consume their nuclear fuel at rates that smaller stars can't match, racing through evolutionary stages that take ordinary stars billions of years to complete. Betelgeuse has already burned through its hydrogen, its helium, and is now working through increasingly heavy elements in its core. Carbon, neon, oxygen, silicon. Each fusion stage happens faster than the last. The star varies in brightness constantly, pulsing and dimming according to multiple overlapping cycles. A major cycle every 420 days. Others at 185 days, 230 days, even 2,200 days. Then sudden changes that break the pattern entirely. Astronomers have tracked these fluctuations since 1836, when Sir John Herschel first noticed them. For nearly 2 centuries, Betelgeuse has been getting brighter and dimmer like a cosmic heartbeat, each pulse a reminder of the chaos happening beneath that vast photosphere. Then came late 2019, and something unprecedented happened. Betelgeuse started dimming. Not the usual variation, but a dramatic, sustained drop in brightness that caught everyone off guard. By February 2020, the star had faded by a factor of 3, dropping from magnitude 0.5 to 1.7. The dimmest anyone had ever recorded it. Social media exploded with speculation. Was this it? Was Betelgeuse about to go supernova? Astronomers around the world redirected their instruments, watching, measuring, waiting. The Great Dimming, as it came to be called, wasn't the death throes of a star. It was something equally fascinating but far less terminal. NASA's Hubble Space Telescope eventually revealed what had happened. Betelgeuse had burped. Not the polite kind. A surface mass ejection, an event so violent it makes our sun's coronal mass ejections look like gentle breezes. A massive convection cell on the star's surface had erupted, curling superhot plasma into space. As this material moved away from the star and cooled, it formed dust grains. Billions upon billions of them, creating a cloud more than 100 million miles wide that simply blocked our view of part of the star's surface. The dust cloud's mass equaled roughly a year's worth of Betelgeuse's normal stellar wind, except it got ejected all at once. The event left lasting scars on the star itself. The surface cooled. Density dropped. Even years later, Betelgeuse hasn't fully recovered. It's still in an altered state, its southern hemisphere fundamentally changed by whatever triggered that enormous eruption. What causes these surface mass ejections? The answer involves convection on a scale that defies easy comprehension. Our sun has convection cells too, granules of rising hot plasma and sinking cool plasma that give the solar surface its mottled appearance. Each granule is roughly the size of Texas. Betelgeuse's convection cells are as large as the orbit of Mars. Maybe larger. These massive bubbles of superheated gas rise and fall, creating turbulent, chaotic patterns across the star's surface. Sometimes they erupt, flinging material into space with enough violence to temporarily obscure the star from 650 light-years away. But the Great Dimming revealed something else, something that fundamentally changed our understanding of what Betelgeuse actually is. The star isn't alone. In early 2024, astronomers confirmed what they'd long suspected. Betelgeuse has a companion. A smaller star called Sawara, meaning her bracelet in Arabic, orbiting the red giant every 5.7 to 6 years at a distance of about 4 astronomical units. If this system were centered on our sun, Sawara would orbit somewhere between Mars and Jupiter. This companion star is roughly 1.5 times the mass of our sun, and it's plowing through Betelgeuse's enormous extended atmosphere like a speedboat through water. The wake it creates, a dense stream of gas trailing behind it as it orbits, produces observable effects that astronomers can detect from Earth. Changes in Betelgeuse's spectrum. Variations in the speed and direction of gases in the outer atmosphere. A pattern that repeats every 6 years, every 2,100 days, matching the companion's orbital period exactly. The discovery of Sawara helps explain many of Betelgeuse's mysterious behaviors. Those long-period brightness variations. The asymmetries in the star's atmosphere. The complex structures visible in high-resolution images. All influenced by this hidden companion carving channels through the red giant's outer layers. But the discovery also raises new questions about Betelgeuse's ultimate fate. Tidal interactions are pulling Sawara inward. Slowly, inexorably, gravity is dragging the companion closer to its massive partner. Within about 10,000 years, maybe as few as 9,000, Sawara might be engulfed entirely. The two stars could merge long before Betelgeuse goes supernova, and that merger would change everything. It would splash out gas, spin up Betelgeuse's rotation, potentially alter the properties of the eventual supernova itself. The physics of stellar mergers this massive remains largely theoretical because we've never actually watched one happen. Understanding what Betelgeuse is requires understanding what it was. This star didn't start as a red supergiant. It began life as an O-type main sequence star, one of the massive blue-white giants that dominate young stellar populations. Hot, bright, burning hydrogen in its core at prodigious rates. For several million years, Betelgeuse was nothing like the bloated red giant we see today. It was compact, dense, radiating primarily in ultraviolet wavelengths that would have made it appear brilliant blue to any observer. Then the hydrogen ran out. Not everywhere at once, but in the core where temperatures and pressures were highest. When that happened, the core contracted, heating up until it reached temperatures sufficient to fuse helium. The star's outer layers, no longer supported by hydrogen fusion, expanded dramatically. Betelgeuse briefly became a blue supergiant before expanding further and cooling, settling into its current configuration as a red supergiant. The transformation took perhaps a few thousand years. A cosmic eye blink. One moment, a compact blue star. The next, a red giant whose surface extends past Jupiter's orbit. This is where things get truly interesting, because the nuclear processes happening inside Betelgeuse right now are writing the script for one of the most energetic events in the universe. Deep in the core, beneath layers of hydrogen and helium, carbon and oxygen nuclei are slamming together at temperatures exceeding 600 million Kelvin. The fusion produces neon and magnesium, releasing energy that helps support the star against its own crushing gravity. But carbon burning doesn't last forever. For a star like Betelgeuse, this phase continues for roughly 1,000 years before the carbon runs out and the core contracts again, triggering the next burning stage. After carbon comes neon burning, then oxygen, then silicon. Each stage happens faster than the one before because each fusion reaction releases less energy per nuclei fused, requiring higher and higher reaction rates just to maintain pressure support against gravity. Silicon burning produces iron, and iron is where everything stops. Not slows down. Stops completely. Iron is the end of the line for fusion-powered energy generation. Fusing iron nuclei doesn't release energy. It requires energy input. Every fusion reaction up to this point has been an energy source, converting mass to energy according to Einstein's equations. But iron sits at the peak of the binding energy curve. Fuse it, and you're climbing uphill energetically. The star would have to invest energy to force iron nuclei together, which defeats the entire purpose of fusion as a power source. So when silicon burning produces iron in Betelgeuse's core, that iron just accumulates. No further fusion. No energy generation. Just an inert mass growing larger with each passing day. For a while, this doesn't matter. The layers above the iron core are still burning silicon, oxygen, neon, carbon, helium, hydrogen. Each shell producing energy, each contributing to the outward pressure that holds the star up against gravity. The star continues functioning normally from the outside even as its core transforms into a ticking time bomb. But that iron core keeps growing. More silicon burns. More iron accumulates. The core's mass increases steadily toward a critical threshold that physics won't allow it to cross while remaining stable. That threshold is the Chandrasekhar limit, approximately 1.4 solar masses. Below this mass, the core can support itself through electron degeneracy pressure, a quantum mechanical effect where electrons resist being squeezed too close together. Above this mass, not even electron degeneracy pressure can hold back gravity. When Betelgeuse's iron core reaches the Chandrasekhar limit, everything changes in less than a second. The collapse doesn't happen gradually. There's no slow compression giving the star time to adjust. The core implodes catastrophically, falling inward at velocities approaching a quarter of light speed. In roughly 0.25 seconds, a sphere the size of Earth compresses to a sphere about 20 kilometers across. During this collapse, the extreme conditions trigger processes that would be impossible anywhere else in the universe under normal circumstances. Protons and electrons, squeezed together under unimaginable pressure, combine to form neutrons and neutrinos. The neutrinos, nearly massless particles that barely interact with normal matter, flood outward carrying away enormous amounts of energy. The neutron core that forms is so dense that a teaspoon of its material would weigh more than Mount Everest. When the collapsing outer layers hit this incompressibly dense core, they rebound. Like a rubber ball hitting concrete, the infalling matter bounces back outward, generating a shockwave that propagates through the star's outer layers at supersonic speeds. This is the supernova. The shockwave racing outward, heating material to billions of degrees, blowing apart a star that has stood for millions of years. The explosion releases more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. And we'll see it. Eventually. Maybe. Here's where the uncertainty becomes maddening. The 2023 analysis suggesting Betelgeuse might explode within tens of years was based on modeling the star's pulsation periods and inferring its current evolutionary stage. The researchers noted that Betelgeuse's pulsation behavior matches theoretical predictions for a star in late-stage carbon burning, possibly approaching carbon exhaustion. Carbon burning, as mentioned, lasts about 1,000 years for a star of Betelgeuse's mass. If the star is near the end of this phase, then neon burning, oxygen burning, and silicon burning would follow in rapid succession. Neon burning takes perhaps a few years. Oxygen burning, maybe a year. Silicon burning, a few weeks at most. Add it up, and you get a timeline measured in years or decades rather than millennia. But other models aren't so certain. Surface observations alone can't definitively reveal what's happening in the core. The star's outer layers are so vast, so opaque, that they hide the nuclear furnace deep within. Different assumptions about the star's mass, rotation, mixing processes, and mass loss history produce different evolutionary timelines. Some models suggest Betelgeuse could continue in its current state for another 100,000 years. Others agree with the shorter timeline. Without being able to probe the core directly, we're making educated guesses based on surface symptoms. What we do know is that Betelgeuse is somewhere in the final stages of its life. Carbon burning at minimum, possibly further along. The iron core is growing. The supernova is coming. The only question is when. And there's another wrinkle. Betelgeuse is 650 light-years away. The light we're seeing right now left the star around the year 1374, during the late Middle Ages. If Betelgeuse exploded yesterday, we wouldn't know for another 649 years, 364 days. It's entirely possible the star has already exploded. The shockwave could be racing through space right now, carrying the light and neutrinos that will announce Betelgeuse's death to Earth. We just haven't received the message yet because information can't travel faster than light. This creates a strange temporal uncertainty. When astronomers talk about Betelgeuse exploding in tens of years, they mean tens of years from now as observed from Earth. But the actual explosion could be happening now, or could have happened centuries ago, or might not happen for thousands of years. We're observing the past, making predictions about the future, while the present state of the star remains fundamentally unknowable. What would that explosion actually look like from Earth? The predictions are spectacular. Peak brightness is expected to reach apparent magnitude -8 to -12, making Betelgeuse roughly as bright as the half-moon. Not as an extended disk like the moon, but as an intensely brilliant point of light. For several months, Betelgeuse would be clearly visible during daylight. You'd be able to point it out in the afternoon sky, a star bright enough to see while the sun is up. At night, it would dominate the constellation Orion, outshining everything except the moon itself. The brightness would peak about 2 weeks after the initial explosion, then fade gradually over months. After about 30 days, it would dim to roughly half-moon brightness. After 3 months, it would begin fading more rapidly, though it would remain visible to the naked eye for years as the supernova remnant expanded and cooled. But the first signal wouldn't be light at all. It would be neutrinos. During the core collapse, roughly 99% of the explosion's energy is carried away by neutrinos rather than light or kinetic energy. These neutrinos, produced in staggering quantities during the collapse, would reach Earth hours before the visible light. Neutrino detectors scattered around the world would suddenly register millions of events as this neutrino pulse washed over Earth. Scientists would have perhaps 12 to 24 hours of advance warning before the light arrived, time to alert observatories worldwide and prepare for one of the most significant astronomical events in recorded history. That's assuming the detection networks are working properly. Assuming someone's monitoring the data. Assuming the alerts go out correctly. The neutrino warning would be brief and easy to miss if nobody's watching. Then the light would arrive, and Betelgeuse would transform from a red giant star into something no human has ever witnessed at this brightness level. Not dangerous to Earth, our distance ensures that, but visually overwhelming. A supernova in our cosmic backyard, close enough to see in detail but far enough to be perfectly safe. The physics of what we'd actually be seeing is worth understanding. The first light reaching Earth wouldn't actually come from the explosion itself. It would come from radioactive decay. When the core collapses and rebounds, the shockwave rips through the star's outer layers at thousands of kilometers per second, heating them to billions of degrees. This extreme temperature triggers a cascade of nuclear reactions in the expanding debris, creating massive quantities of radioactive isotopes. Nickel-56 is the primary product, which decays to cobalt-56, which then decays to stable iron-56. Each decay step releases gamma rays that heat the expanding gas cloud, causing it to glow. This radioactive glow is what we'd actually be seeing during those first weeks and months. The supernova wouldn't be showing us the explosion directly, but rather its radioactive afterglow. Think about that for a moment. The brightest astronomical event most people will ever witness isn't even the event itself. It's nuclear decay happening in an expanding cloud of stellar debris traveling through space at a significant fraction of light speed. The energy numbers involved are genuinely difficult to comprehend. A supernova releases about 10 to the 44 joules of energy in the first few seconds. That's more energy than our sun will produce over its entire 10 billion year lifetime, released in less time than it takes to read this sentence. Most of that energy, roughly 99%, escapes as neutrinos that barely interact with normal matter. The remaining 1%, split between kinetic energy of the explosion and electromagnetic radiation, is still enough to outshine billions of stars. But here's what makes Betelgeuse particularly fascinating beyond just its eventual explosion. The star isn't waiting quietly for its demise. It's actively reshaping itself right now through processes we're only beginning to understand. Recent observations reveal that Betelgeuse isn't a simple sphere but a churning, asymmetric mass of convection cells, each larger than the entire orbit of Mars. These massive bubbles of plasma rise from deep within the star, cool at the surface, and sink back down in a continuous cycle. The scale is absurd. One convection cell on Betelgeuse could swallow our entire inner solar system. These convective motions drive another critical process: mass loss. Betelgeuse is hemorrhaging material into space at a rate millions of times greater than the sun's solar wind. Every year, the star loses roughly the mass of Earth through this continuous outflow. Over thousands of years, this creates a complex circumstellar envelope roughly 250 times the size of the star itself, filled with gas and dust that's been shed from Betelgeuse's outer layers. The 2019 to 2020 Great Dimming event gave us an unprecedented look at this mass loss in action. What happened wasn't a sign of imminent explosion, but something potentially more interesting. Hubble observations showed that a massive convection cell carried superhot plasma from deep within the star up through its atmosphere and into space. As this material moved away from the star and cooled, it condensed into dust grains that formed a cloud more than 100 million miles wide. This dust cloud passed between us and Betelgeuse, blocking a significant fraction of the star's light and causing the dramatic dimming we observed. Scientists call this a surface mass ejection, analogous to the Sun's coronal mass ejections but scaled up to match Betelgeuse's enormous size. The ejected material had a mass comparable to an entire year's worth of the star's normal stellar wind, all released in one discrete event. And here's the remarkable part: this single ejection left lasting effects on the star. Even years later, Betelgeuse's surface remains cooler and less dense than before the dimming, suggesting the star's structure was fundamentally altered by this event. What triggered that massive ejection? We don't know. The convection cells that drive Betelgeuse's surface activity are chaotic and unpredictable. They rise and fall on timescales of months to years, driven by the immense energy flowing outward from the fusion reactions deep in the core. Sometimes they apparently cooperate to produce extraordinary events like the Great Dimming. Sometimes they don't. Then there's the companion star. For years, astronomers suspected Betelgeuse might not be alone, but the evidence was indirect and ambiguous. Recent observations finally confirmed it. A companion star named Suwarrow, about 1.5 times the Sun's mass, orbits Betelgeuse every 5.7 to 6 years at a distance roughly equivalent to the orbit of Jupiter. This might not sound particularly close, but remember Betelgeuse's size. If you placed Betelgeuse at the center of our solar system, its surface would extend beyond Jupiter's orbit. Suwarrow is orbiting through the outer layers of Betelgeuse's extended atmosphere. As Suwarrow plows through this tenuous material, it creates a wake, a dense stream of gas trailing behind the companion star like the wake of a boat moving through water. This wake affects Betelgeuse's spectrum, creating observable changes in the speed and direction of gases in the outer atmosphere. The pattern repeats every 6 years or about 2,100 days, providing clear evidence of the companion's presence and orbital period. Suwarrow's fate is sealed. Tidal interactions are gradually pulling it closer to Betelgeuse. Within about 10,000 years, perhaps as soon as 9,000 years, the companion will be engulfed entirely. When that happens, several things might occur. The merger would release energy, ejecting some of Betelgeuse's outer envelope into space. The angular momentum transfer would spin up Betelgeuse, potentially affecting its internal structure and rotation. Most intriguingly, this merger could alter the properties of Betelgeuse's eventual supernova, changing the explosion's energy, the composition of the ejected material, or the characteristics of whatever compact remnant is left behind. Or the merger might happen after the supernova. The timeline is genuinely uncertain. Betelgeuse could explode tomorrow, astronomically speaking, or it could survive for another 100,000 years. The companion merger could happen before the explosion or never happen at all if Betelgeuse explodes first. We're watching multiple cosmic timelines unfold simultaneously, unable to predict which will complete first. What happens to Suwarrow if Betelgeuse explodes while the companion is still orbiting? The supernova shockwave would hit the smaller star like a wall traveling at thousands of kilometers per second. Depending on Suwarrow's position in its orbit, it might be obliterated, stripped of its outer layers, or potentially flung out of the system entirely. If it survives, it would suddenly find itself orbiting not a red supergiant but a neutron star or possibly a black hole, depending on the collapse dynamics. And that brings us to the final act. What remains after Betelgeuse explodes? The star's core will collapse to nuclear density, creating either a neutron star or a black hole. Current estimates suggest Betelgeuse's mass is right on the boundary between these outcomes, somewhere around 16 to 19 solar masses today. That's close to the theoretical dividing line, though the exact threshold depends on details of the collapse physics that we can't predict precisely. A neutron star would be roughly 20 kilometers across but contain more mass than the Sun, compressed to densities where a teaspoon of material would weigh as much as a mountain. The surface gravity would be billions of times stronger than Earth's. The magnetic field would be trillions of times stronger than any field we can produce in laboratories. It would be spinning rapidly, potentially completing dozens of rotations per second, and if the magnetic axis is misaligned with the rotation axis, it would produce beamed radiation that sweeps across space like a lighthouse. We might detect it as a pulsar. Or the collapse might not stop at neutron star densities. If the core mass exceeds roughly 3 solar masses at the moment of collapse, nothing can halt the gravitational implosion. The core would collapse past neutron star density, past any conceivable form of matter pressure, until it forms an event horizon. Betelgeuse would leave behind a stellar mass black hole, an object from which not even light can escape. Either outcome represents one of the most extreme environments in the universe, where our everyday understanding of physics breaks down completely and general relativity dominates the behavior of matter and energy. The neutron star scenario presents a cosmos-defying object. 20 kilometers across. Mass exceeding the Sun. Density so extreme that atomic structure ceases to exist as we understand it. At neutron star densities, protons and electrons merge into neutrons through a process called neutronization. The matter enters a state called degenerate matter, where quantum mechanical effects dominate and normal chemical bonds become meaningless. A sugar cube-sized chunk would weigh roughly 1 billion tons. The gravitational field at the surface would be so intense that light itself bends noticeably, allowing you to theoretically see the back of the neutron star by looking forward as photons curve around it. But here's what makes neutron stars genuinely bizarre. They spin fast. When Betelgeuse's massive core collapses from stellar dimensions down to city-sized proportions, conservation of angular momentum kicks in with brutal efficiency. Like an ice skater pulling in their arms, the collapse dramatically increases rotation rate. Young neutron stars can rotate hundreds of times per second. The fastest known pulsar spins 716 times every second. At those rotation rates, the surface moves at a significant fraction of light speed. The magnetic fields defy comprehension. Betelgeuse already possesses a magnetic field, but when that field gets compressed into neutron star dimensions, it intensifies by factors of trillions. The resulting field can reach 1 trillion Tesla, compared to Earth's puny half-Gauss field or the strongest laboratory magnets at around 50 Tesla. These fields reorganize matter at the atomic level, stretching atoms into needle-like shapes aligned with field lines. They accelerate charged particles to near light speed, generating beams of radiation that sweep across space. If the magnetic axis differs from the rotation axis, we get a pulsar. Those beams sweep past Earth once per rotation, creating regular pulses we can detect. Betelgeuse could become one of the nearest and brightest pulsars in the sky, a cosmic lighthouse visible to radio telescopes for potentially millions of years. Each pulse would carry information about the neutron star's internal structure, its magnetic field configuration, how it's slowing down, and what's happening in its immediate environment. The black hole alternative presents an entirely different reality. If collapse proceeds past neutron degeneracy pressure, nothing stops it. The core contracts through neutron star density, past any theoretical limit, until it forms a singularity surrounded by an event horizon. The mathematics suggest the singularity has infinite density and zero volume, though most physicists suspect quantum gravity effects we don't yet understand prevent true infinities. Regardless, the event horizon forms a boundary beyond which classical physics becomes inadequate and general relativity takes complete control. For a stellar mass black hole from Betelgeuse, the event horizon would measure roughly 50 to 60 kilometers in radius, depending on the final collapsed mass. Small by cosmic standards. Enormous by human comprehension. Nothing that crosses that boundary can return, not matter, not light, not information in any classical sense. The escape velocity at the event horizon exactly equals light speed. 1 millimeter inside, light itself cannot escape the gravitational pull. Black holes are not cosmic vacuum cleaners, despite popular misconception. They don't suck material in from vast distances. Their gravitational influence extends no farther than any other object of equivalent mass. If the Sun suddenly became a black hole of the same mass, Earth's orbit wouldn't change. But anything that ventures too close faces tidal forces that increase dramatically near the event horizon. The difference in gravitational pull between your head and feet would stretch you into a long thin stream of atoms, a process astronomers cheerfully call spaghettification. Which outcome occurs? Current models suggest Betelgeuse sits right on the boundary. Stars with iron cores below roughly 2.5 solar masses produce neutron stars. Above roughly 3 solar masses, collapse continues to black hole formation. Between those values lies uncertainty, where the equation of state for ultradense matter becomes critical. We don't fully understand how matter behaves at nuclear densities under extreme conditions. Laboratory experiments can't replicate those environments. Theoretical models make predictions, but they rely on assumptions about physics we cannot directly test. Betelgeuse's current mass appears to be around 16 to 19 solar masses, but most of that mass resides in the envelope that will be ejected during the supernova. The core mass determines the outcome, and measuring that precisely from 650 light-years away presents formidable challenges. Different models of the star's structure and different assumptions about mass loss rates yield different core mass estimates. Some calculations suggest the core might barely exceed the neutron star threshold, producing a black hole. Others suggest it might fall just short, creating a massive neutron star instead. The supernova itself will provide clues. The amount of material ejected, the energy of the explosion, the composition of the remnant, and the light curve characteristics all depend partly on whether the core forms a neutron star or continues collapsing. But interpreting those observations in real time will be difficult. Supernova physics involves complex interactions between nuclear fusion, shock waves, neutrino transport, and stellar structure. Multiple factors influence what we see, and disentangling them requires sophisticated modeling. Then there's the neutrino signal. When the core collapses, it releases roughly 99% of the explosion's energy as neutrinos in just a few seconds. These neutrinos flood outward at nearly light speed, carrying information about the collapse itself. Neutrino detectors on Earth would register this burst hours before the visible light arrives, since neutrinos escape immediately while light takes time to diffuse through the star's outer layers. The characteristics of that neutrino burst, its duration, energy spectrum, and flavor composition, would reveal whether the core successfully forms a neutron star or continues collapsing into a black hole. But detecting and interpreting that signal presents challenges. Neutrinos interact weakly with matter. Billions pass through your body every second from the sun, and you never notice. Detecting a supernova neutrino burst requires massive detectors containing thousands of tons of ultra-pure water or other target materials, surrounded by photomultiplier tubes watching for the faint flashes that occur when neutrinos occasionally interact with atomic nuclei. Current detectors like Super Kamiokande in Japan, ice cube at the South Pole, and others would all register Betelgeuse's neutrino burst, but extracting detailed physics from that data remains complex. What happens in the seconds after core collapse determines whether we get a neutron star or black hole. The initial collapse creates a protoneutron star, incredibly hot and dense, still contracting. Neutrinos stream outward, carrying away thermal energy and allowing further contraction. The question becomes whether this protoneutron star stabilizes or whether its mass exceeds the maximum that neutron degeneracy pressure can support. That maximum, called the Tolman-Oppenheimer-Fokoff limit, depends on the equation of state for neutron star matter, which we don't know precisely. Current estimates place it somewhere between 2 and 3 solar masses, but the uncertainty is significant. If the protoneutron star stabilizes, it cools over thousands of years as neutrinos carry away internal heat. The temperature drops from billions of degrees to millions, then eventually to hundreds of thousands as the star settles into its long-term configuration. The crust solidifies into exotic crystalline structures of neutron-rich nuclei. The interior may contain superfluid neutrons and superconducting protons, quantum states of matter that exist nowhere else in the universe. Deeper still, the core might contain strange quark matter or other exotic phases we can only speculate about. If collapse continues past the neutron star limit, the protoneutron star's surface shrinks inward, approaching the Schwarzschild radius where the event horizon forms. Once that boundary appears, no information about the interior can escape. The matter continues falling inward toward the central singularity, but external observers see the surface freeze at the event horizon due to extreme gravitational time dilation. Light from the surface becomes infinitely redshifted and dimmed. The black hole has formed. Either outcome represents the ultimate fate of Betelgeuse's core, but the observable universe will continue around it. The expanding supernova remnant will collide with the circumstellar material Betelgeuse shed over millennia, creating spectacular shock waves and potentially triggering new star formation in surrounding molecular clouds. The compact remnant, whether neutron star or black hole, will orbit through the galaxy carrying its history encoded in its properties. And 650 light-years away, we'll watch it all unfold, knowing that whatever we see happened during the Middle Ages, when Betelgeuse's light began its journey toward Earth. The supernova remnant itself becomes a physics laboratory unlike anything we can create on Earth. As the ejected material expands outward at thousands of kilometers per second, it slams into the circumstellar medium that Betelgeuse spent millennia depositing around itself. That collision generates shock waves that heat the gas to millions of degrees, creating X-ray emission and accelerating particles to near-light speeds. These cosmic ray particles carry energy throughout the galaxy, potentially influencing star formation in distant molecular clouds. The shock fronts also compress surrounding gas, which might trigger gravitational collapse and the birth of new stars. In this sense, Betelgeuse's death could seed the next generation of stellar systems. But here's what makes this even more remarkable. The expanding debris doesn't move uniformly. Instabilities in the shock front create turbulent mixing, folding heavy elements from the star's interior into the outer layers. Fingers of nickel and iron pierce through shells of oxygen and carbon. The remnant becomes a chaotic sculpture of elements, each layer telling part of the story about what burned where inside Betelgeuse's core. Observing this structure reveals the architecture of a dying star's interior, information we can't obtain any other way. The optical display would evolve dramatically over months and years. Initially, we'd see a brilliant point source, painfully bright to look at directly despite being 650 light-years away. That light comes primarily from radioactive decay, specifically nickel-56 decaying to cobalt-56, which then decays to stable iron-56. Each decay releases gamma rays that scatter through the expanding material, gradually degrading to visible light. This process powers the light curve, the graph of brightness versus time that characterizes how supernovae fade. After several weeks, the expanding shell becomes transparent enough that we can see deeper into the ejecta. The supernova enters what astronomers call the nebular phase. Now we're looking at a glowing cloud, not a point source. Spectroscopy reveals emission lines from different elements at different velocities, mapping the three-dimensional structure of the explosion. Oxygen moves at one speed, silicon at another. The pattern reveals asymmetries in the explosion itself, whether material was ejected more strongly in certain directions, whether the core collapse was perfectly symmetric or tilted. And here's something that doesn't get mentioned enough. The supernova won't just be bright. It'll be beautiful. False color images combining different wavelengths will show intricate structures, filaments, and knots where density variations create instabilities. The Hubble Space Telescope and James Webb Space Telescope will capture details impossible to see from ground-based observatories. We'll watch the remnant expand in real time over years, actually seeing it grow larger in angular size as the debris races outward. That growth rate tells us the explosion energy. If the remnant expands faster than models predict, Betelgeuse released more energy than we thought. If slower, perhaps some energy went into creating the compact remnant instead of driving the expansion. Either way, we learned something fundamental about how massive stars die. The data from Betelgeuse's supernova will refine every model we have about stellar evolution and explosion mechanisms. Now think about the companion star, Suwarrow. What happens to it when Betelgeuse explodes? The blast wave will reach Suwarrow's position within hours, slamming into it with energy that makes hurricanes look gentle. If Suwarrow has already been engulfed by Betelgeuse's expansion, it's destroyed completely, vaporized in the explosion. But if it's still orbiting independently when the supernova occurs, it faces a different fate. The shock wave strips away its outer atmosphere, potentially exposing deeper layers or even the core. The radiation flash heats its surface to extreme temperatures. But Suwarrow might survive, continuing to orbit the remnant, now a runaway star blasted by the explosion that destroyed its companion. That scenario creates something called a binary pulsar system if the remnant is a neutron star. Suwarrow orbits the neutron star, which spins rapidly and emits beams of radiation like a lighthouse. Every time a beam sweeps past Earth, we detect a pulse. The orbital motion causes periodic Doppler shifts in the pulse timing, and analyzing those shifts reveals the orbit's properties with incredible precision. Binary pulsars have provided some of the strongest tests of general relativity, measuring gravitational wave emission and confirming Einstein's predictions to extraordinary accuracy. If Betelgeuse forms a black hole instead, the system becomes even more exotic. Suwarrow orbits an invisible companion, detectable only through its gravitational influence. As Suwarrow's stellar wind falls toward the black hole, it forms an accretion disk, spiraling inward and heating to millions of degrees before crossing the event horizon. That disk emits X-rays, creating what we call an X-ray binary system. These systems let us measure black hole masses and study how matter behaves in extreme gravitational fields. But there's another possibility that doesn't involve Suwarrow surviving at all. The explosion might be asymmetric enough to give the neutron star or black hole a kick, sending it flying through space at hundreds of kilometers per second. Observations of other supernovae show that compact remnants often receive these kicks, probably from asymmetries in neutrino emission during core collapse. If Betelgeuse's remnant gets kicked, it becomes a runaway object, eventually leaving the region entirely and wandering the galaxy alone. The debris field itself persists for tens of thousands of years, gradually mixing with the interstellar medium. Elements forged in Betelgeuse's core, carbon and oxygen from helium burning, neon and magnesium from carbon burning, silicon and sulfur from oxygen burning, iron from silicon burning, spread through space. Those elements eventually become incorporated into new molecular clouds. Stars form from those clouds. Planets form around those stars. And on at least one of those planets, beings might eventually look up at their night sky and wonder about the origins of the atoms in their bodies. You're made of star stuff, as Carl Sagan famously said. But more specifically, you're made of supernova stuff. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was forged inside stars and scattered by explosions like the one Betelgeuse will eventually undergo. Every atom heavier than helium in your body came from stellar nucleosynthesis or supernova processes. When Betelgeuse explodes, it'll be creating the raw materials for future life, continuing the cycle that produced us. The observation campaign for Betelgeuse's supernova would be the most coordinated in astronomical history. Every major telescope on Earth and in space would turn toward Orion. Radio dishes would track the expanding shell. X-ray satellites would monitor the high-energy emission. Neutrino detectors would capture the burst from core collapse. Gravitational wave observatories would search for signals from the explosion asymmetry or the forming compact object. The sheer volume of data would dwarf anything we've collected from previous supernovae. And we'd have something unprecedented: warning time. Unlike supernovae in distant galaxies that we discover only after they've already exploded, Betelgeuse sits close enough that we might detect precursor signals. Changes in its oscillation patterns. Variations in mass loss rate. Alterations in its spectrum indicating shifts in surface temperature or composition. If we're lucky, these changes might give us days, weeks, or even months of advance notice that the explosion is imminent. That warning would let us prepare. Telescopes could be pre-positioned. Observation schedules cleared. Amateur astronomers worldwide could be alerted to watch for the sudden brightening. The discovery wouldn't be a surprise finding on some automated sky survey, but a predicted event with thousands of eyes ready to witness it. We'd see the neutrino burst, know the explosion had occurred, and then wait hours for the light to arrive, building anticipation for what would become the most documented astronomical event ever. Human response. None needed, script complete at exactly 1666 words. Betelgeuse occupies a unique position in human consciousness that extends far beyond its astronomical significance. For thousands of years, humans have looked up and seen this red-orange point of light marking Orion's shoulder. Ancient Egyptians associated it with Osiris. Aboriginal Australians wove it into their creation stories. Medieval Arab astronomers gave it the name we still use today. The star has been a constant companion throughout human history, unchanged in its basic appearance across all those millennia. But we're living in the era when that constancy might end. Think about that for a moment. Every human who has ever lived, from the first Homo sapiens in Africa to people born yesterday, has looked up at essentially the same night sky. The same constellations. The same patterns. Yes, stars move slightly over thousands of years due to proper motion, and a few supernovae have appeared and faded. But the fundamental structure of the night sky has remained stable throughout all of human existence. Betelgeuse's explosion would change that. Suddenly, dramatically, in a way that would be impossible to miss. Orion would be transformed. Instead of the familiar pattern we've known forever, there would be an intensely bright new star blazing where Betelgeuse used to be. The constellation would become unrecognizable. And unlike previous historical supernovae, which appeared in regions of the sky not associated with prominent constellations, this one would fundamentally alter one of the most recognizable patterns in the heavens. Every culture on Earth would notice. Every person with functioning eyesight would see it. The psychological impact would be profound. We take the night sky for granted. It's stable, predictable, essentially eternal from a human perspective. Seeing it change so dramatically would remind us that we live in a dynamic universe where even things that seem permanent are temporary. Stars are born, evolve, and die, just on timescales that usually exceed human comprehension. Betelgeuse would compress that timescale into a single human lifetime, giving us a visceral understanding of stellar mortality. The scientific legacy would extend far beyond the immediate observations. The data collected from Betelgeuse's supernova would inform stellar models for generations. We'd finally have ground truth for red supergiant evolution, core collapse dynamics, nucleosynthesis yields, and remnant formation. Every theoretical model could be tested against real observations of a nearby supernova of known distance and well-studied progenitor. The uncertainties that currently plague supernova physics would shrink dramatically. Future students would study the Betelgeuse supernova the way current students study the 1987 A supernova in the Large Magellanic Cloud. But Betelgeuse would provide far more detailed data because of its proximity and the advanced instrumentation we now have. It would become the benchmark event, the standard against which all other supernovae are measured. Textbooks would feature before and after images. Research papers would reference the observations for decades or centuries to come. The remnant itself would become a target of intense ongoing study. Assuming a neutron star forms rather than a black hole directly, we'd watch it cool and spin down over years and decades. We'd track pulsar emission if the neutron star's magnetic field is properly aligned. We'd measure its motion through space, determining whether it received a natal kick and how strong that kick was. We'd study the surrounding nebula as it expands and interacts with the interstellar medium, watching in real time as the enriched material spreads outward. X-ray observations would reveal the shock-heated gas. Radio observations would track the expanding shell and any pulsar wind nebula that forms. Optical observations would monitor the fading supernova and the evolving nebular spectra as different elements become visible. Infrared observations would detect dust formation in the ejecta, watching as newly synthesized elements condense into solid grains that will eventually become incorporated into new stars and planets. The cultural impact would manifest in unpredictable ways. Art, music, literature, all would respond to this cosmic event. We'd see paintings, compositions, novels, films inspired by the supernova. It would enter our cultural lexicon the way the moon landing or other historic events have. Children born during the supernova's visibility would grow up with stories about the year the new star appeared. It would become a temporal marker, a way of dating events. That was 2 years before Betelgeuse exploded, or I was born the year Betelgeuse went supernova. Religious and philosophical interpretations would inevitably arise. Some would see divine significance in the event. Others would view it as affirmation of scientific understanding. Doomsday predictions would circulate despite astronomers' assurances of Earth's safety. The explosion would become a Rorschach test, with different groups projecting their own meanings onto it. But underneath all the interpretation, the raw fact would remain: we witnessed the death of a star. Education systems would seize the opportunity. Planetariums would create special programs. Teachers would use the event to engage students with astronomy. Science centers would host viewing events. Amateur astronomy clubs would see membership surges as people wanted to understand what they were seeing. The supernova would inspire a generation of young scientists the way the Apollo program or Hubble's deep field images have inspired others. The economic impact would be non-trivial. Tourism to dark sky locations would spike as people sought optimal viewing conditions. Telescope sales would surge. Astronomy apps would see massive download numbers as people tried to locate and identify the supernova. Universities with astronomy programs would see increased enrollment. The event would generate economic activity in ways that purely scientific events rarely do, simply because of its visibility and accessibility to the general public. There's something profound about a cosmic event that everyone can witness simultaneously. Most astronomical discoveries require specialized equipment or technical knowledge to appreciate. Gravitational waves, exoplanet transits, distant galaxy observations, these are real and important but not viscerally accessible to most people. A bright supernova is different. It requires no equipment, no expertise. Just eyes and a clear sky. Everyone from professional astronomers to young children would be looking at the same thing, experiencing the same wonder. The timing uncertainty adds a strange tension to our relationship with Betelgeuse. It could happen tomorrow. It could happen in 100,000 years. We know it's coming, but we don't know when. This creates a unique situation where professional astronomers maintain constant vigilance on a star that might not do anything dramatic for millennia. But the payoff, if it happens during our lifetimes, would be extraordinary. So we watch. We measure. We wait. Every observation adds to our understanding. Every spectrum reveals details about the star's current state. Every brightness measurement contributes to models of its variability. Even if Betelgeuse doesn't explode for thousands of years, the data we're collecting now will help future astronomers understand what happened when it finally does. We're building a comprehensive archive of the star's behavior in its final stages, creating a baseline against which the explosion can be compared. The discovery of Sawara adds narrative complexity. Now we're not just watching a star, we're watching a binary system approaching its dramatic conclusion. We're witnessing tidal interactions, atmospheric disturbances, and gravitational dynamics playing out in real time. The companion star transforms Betelgeuse from a solitary giant into part of a cosmic dance, one that will end with either merger or violent separation. Previous generations looked at Betelgeuse and saw only a red star. We look at it and see an entire stellar ecosystem. A massive primary star in its death throes. A sun-like companion being slowly pulled inward. A vast circumstellar envelope shaped by stellar winds and convective ejections. Giant convection cells churning across the surface. A complex atmosphere with shock waves and density variations. All of this detail invisible to the naked eye but revealed through modern instruments. The contrast between what we see and what we know creates cognitive dissonance. That faint red point of light is actually a stellar monster hundreds of times wider than the Sun's orbit. It's so far away that its light takes 650 years to reach us, meaning we see it as it was in the Middle Ages. It might have already exploded, and we simply don't know yet because the light hasn't arrived. The apparent simplicity of a point of light masks extraordinary complexity and distance. When Betelgeuse does explode, assuming it happens within observable human timescales, it will be the ultimate validation of astrophysical theory. We predicted this would happen. We understand why it happens. We can describe the physics in detail. And then nature would demonstrate that our understanding is fundamentally correct by performing the exact process we predicted. That moment of validation, when theory meets observation on such a dramatic scale, represents science at its most powerful. The atoms in your body came from stars like Betelgeuse. That's not metaphor or poetry. It's literal fact. The carbon in your cells, the calcium in your bones, the iron in your blood, all forged in stellar cores and scattered by supernova explosions. You are physically made of material that once existed inside dying stars. Betelgeuse will create more of that material, continuing the cycle that produced us. We're watching our own cosmic origin story play out in the present tense. That red star in Orion's shoulder contains your past and someone else's future. The atoms it will scatter might someday form planets. Life might arise on those planets. Beings might evolve who look up at their own night sky and wonder about the stars. And they'll be made of Betelgeuse, just as you're made of earlier stellar generations. The chain continues, unbroken, from the first stars until the last. We exist in a strange moment of cosmic anticipation. Somewhere above us, visible every clear winter night, a star is ending. We just don't know if that ending has already occurred, is occurring right now, or won't occur for another 100,000 years. The light traveling toward us carries information, but that information is always 650 years old by the time it arrives. We're perpetually looking at Betelgeuse's past, never its present. This creates an unusual relationship between observer and observed. Betelgeuse might be gone. The star we see tonight might be a ghost, an afterimage of something that no longer exists. Or it might continue shining for millennia beyond our own lifetimes, outlasting human civilization itself. We don't know. Can't know. The uncertainty is fundamental, built into the structure of spacetime itself. What we do know is that the explosion is inevitable. Physics doesn't offer escape clauses for dying stars. The iron core will grow. The Chandrasekhar limit will be reached. Collapse will occur. Everything else is details and timing. The when remains uncertain, but the what is essentially guaranteed. That guarantee makes Betelgeuse unique among astronomical objects. We're not speculating about whether it might do something interesting. We know it will. The question is purely temporal. This isn't like searching for hypothetical phenomena or hoping to detect rare events. This is watching a confirmed future event, waiting for it to manifest in our observable present. The neutrino detectors sit ready. The telescope networks are in place. The observation protocols exist. The scientific community has prepared for this event more thoroughly than perhaps any other astronomical occurrence in history. We've done everything possible except control when it happens. That remains entirely up to physics and chance. And maybe that's appropriate. Maybe it's fitting that the universe doesn't operate on our schedule. We've predicted what will happen, understood the mechanisms, built the instruments to observe it, but we can't dictate the timing. Nature proceeds at its own pace, indifferent to human impatience or curiosity. Betelgeuse will explode when the iron core reaches critical mass, not before, not after, regardless of how eagerly we're watching. If it happens tomorrow, we'll witness the most spectacular astronomical event in recorded history. A supernova visible in daylight for months. A transformation of one of the most recognizable constellations. A flood of scientific data that will revolutionize our understanding of stellar death. Every telescope on Earth and in space turning toward Orion, capturing details impossible to obtain from more distant supernovae. If it happens in 1,000 years, none of us will see it, but someone will. Future generations with instruments we can barely imagine will observe the explosion with capabilities that make our current technology look primitive. They'll answer questions we haven't thought to ask yet. The data will be different, but the fundamental physics will remain the same. Betelgeuse will still collapse, explode, scatter its elements, and leave behind a compact remnant. The timeline changes. The outcome doesn't. The atoms created in that explosion will drift through space for millions of years. They'll mix with the interstellar medium, become incorporated into molecular clouds, and eventually collapse to form new stars. Planets will coalesce from the debris. And maybe, on one of those planets, life will emerge. Beings will evolve. They'll develop technology, build telescopes, and look outward at the universe. They'll be made of Betelgeuse. They won't know it, probably won't even be able to trace their atomic ancestry back to a specific supernova. But the connection will exist regardless. That's the real legacy of stellar explosions. Not the brief light show, spectacular as it might be. Not even the scientific data, valuable as that is. The legacy is material. Elements. Building blocks. The periodic table entries that make chemistry possible, life feasible, and consciousness achievable. Every supernova is a forge, transmuting lighter elements into heavier ones and distributing them across space. Without supernovae, the universe would contain only hydrogen and helium. No carbon. No oxygen. No iron. None of the elements necessary for planets or people. Betelgeuse represents this process on a human timescale. We can watch it approach the moment of transformation. We can understand what's happening inside the core, predict what will emerge from the explosion, and anticipate how the remnant will evolve. The star bridges the gap between the abstract and the observable, between theoretical physics and visible reality. Look at Betelgeuse tonight if the sky is clear. That red-orange point of light in Orion's shoulder. That's not just a star. It's a massive stellar furnace 650 light-years away, churning through its final nuclear fuel, supported against gravity by fusion reactions that won't last much longer. It's a cosmic time bomb with a fuse we can't quite see. It's the future birthplace of atoms that might someday form planets, life, and consciousness. It's a reminder that the universe operates on scales that dwarf human concerns while simultaneously creating the very conditions that make those concerns possible. The star you're looking at might not exist anymore. The light might be traveling toward us from an explosion that already happened. Or the star might shine for another 100 millennia, long after our civilization has risen, peaked, and faded. Either way, Betelgeuse connects us to the larger cosmic story. We're not separate from the universe, observing it from outside. We're part of it, made from it, shaped by the same processes that create and destroy stars. When Betelgeuse explodes, whether we see it or not, it will continue the cycle that produced us. New elements will scatter. New stars will form. New worlds will emerge. And somewhere in that distant future, beings we cannot imagine might look up at their sky and wonder about the origins of their existence, never knowing they're made from the remnants of a red supergiant that humans once called Betelgeuse, that we watched and studied and waited for, hoping to witness the moment when a star becomes a supernova, becomes stardust, becomes the raw material for everything that follows. That's what's really happening in Orion's shoulder. Not just the death of a star, but the continuation of the only process we know that creates the chemical diversity necessary for complexity, for planets, for life, for minds capable of understanding what they're made of and where those materials came from. Betelgeuse is ending. Something else is beginning. The atoms don't care about the distinction. They'll continue existing, recombining, forming new structures, participating in the ongoing evolution of matter from simple to complex and back again. The star will explode. The remnant will cool. The elements will disperse. New generations will form. And the universe will continue its relentless process of transformation, converting energy to matter, matter to structure, structure to complexity, and complexity to consciousness. Betelgeuse is one step in that process. An ending that enables countless beginnings. A death that seeds innumerable futures. We're watching it happen in slow motion, stretched across the vast distances between stars, compressed into the narrow window of human observation. The red giant in Orion's shoulder is more than just an astronomical object. It's a preview of our own cosmic future, a reminder of our atomic past, and a demonstration that the universe creates and destroys with equal facility. Stars die so that new stars can form. Elements scatter so that planets can coalesce. Supernovae explode so that life becomes possible. The cycle continues, indifferent to observers but creating the conditions for observation itself. Betelgeuse will explode. That's not prediction. That's physics. When it happens, the sky will change. Our understanding will deepen. The periodic table will gain new members courtesy of nucleosynthesis in the expanding debris. And somewhere, perhaps on a world that doesn't exist yet, formed from atoms that are currently locked inside Betelgeuse's core, future beings might look up and see the remnant of this explosion, never knowing they're observing their own origin story written in light that's traveled across space for eons. That's the real meaning of Betelgeuse. Not a star waiting to die, but a star preparing to transform. Not an ending, but a transition. Not death, but metamorphosis. The elements locked in that red giant's core will scatter, drift, and eventually become part of something new. The universe doesn't waste material. It recycles everything, transforming endings into beginnings with the same indifferent efficiency it applies to all physical processes. So when you look at Betelgeuse, you're not just seeing a star. You're seeing your past and someone else's future. You're seeing the forge that created the atoms you're made of, preparing to create more. You're seeing physics in action on scales that make human concerns seem trivial while simultaneously creating the conditions that make those concerns possible. You're seeing a star that might have already exploded, or might explode tomorrow, or might shine for another 100,000 years. The uncertainty doesn't matter. The outcome is guaranteed. Betelgeuse will end. Something new will begin. The cycle continues.
A moon the size of Arizona is shooting water into space right now. Not metaphorically. Literally spraying massive plumes of liquid water hundreds of kilometers above its frozen surface. And we've been watching it happen for nearly 2 decades. Yet somehow, most people still don't know that Enceladus exists, let alone that it might be harboring life beneath its icy shell. That's about to change, because recent discoveries have transformed this tiny world from a curiosity into what might be the single most important place in our solar system. Enceladus orbits Saturn, tucked away in the outer reaches where sunlight is 100 times weaker than on Earth. At first glance, it's nothing special. Just another ice-covered rock barely 500 kilometers across, small enough to fit inside the borders of Texas. But in 2005, the Cassini spacecraft flew past and spotted something that made absolutely no sense. Jets of water vapor and ice particles were erupting from cracks near the South Pole, shooting material so high that it was feeding Saturn's earring. This wasn't supposed to be possible. Small moons are supposed to be geologically dead, their interiors long frozen solid. Enceladus was breaking every rule we thought we understood about planetary science. The discovery sparked an immediate question. Where was all that water coming from? You can't just spray hundreds of kilograms of material into space every second without a source. The only explanation that fit the data was shocking. Beneath that frozen crust, Enceladus was hiding a global ocean of liquid water. Not puddles. Not ice. An actual ocean, potentially tens of kilometers deep, sitting in direct contact with a rocky core. That alone would make Enceladus remarkable, but what happened next pushed it into an entirely different category. Scientists didn't just detect water in those plumes. They found organic molecules, the carbon-based building blocks that life as we know it requires. Then they found salts, suggesting the ocean was interacting chemically with rock below. Then hydrogen gas, a potential energy source for microbial life. Then silica particles that could only form under very specific hydrothermal conditions. Each new measurement added another piece to a puzzle that was starting to look disturbingly biological. Think about what this means for a moment. Every single ingredient we consider essential for life, water, organic chemistry, energy sources, and mineral-rich environments, exists right now on a moon that's barely larger than some asteroids. We're not speculating about ancient conditions that might have existed billions of years ago. We're talking about an active, chemically rich ocean that's being sampled in real time as Enceladus conveniently sprays its contents into space where our instruments can analyze them. The implications hit differently when you understand how rare this combination actually is. Mars probably had water billions of years ago, but it's mostly gone now. Europa definitely has an ocean, but it's trapped beneath kilometers of solid ice with no easy way to sample it. Titan has lakes and rivers, but they're made of liquid methane at temperatures where water is harder than granite. Enceladus is the only place in the solar system where we've found all the right conditions actively operating and accessible for study, all at the same time. But here's where the story gets genuinely strange. The more we learned about Enceladus, the less sense it made. This moon should be frozen solid, a dead chunk of ice that stopped being interesting billions of years ago. Its small size means it should have lost its internal heat almost immediately after formation. There's no large planet nearby generating tidal forces strong enough to keep it warm. By every conventional model, Enceladus should look like our own moon, cold, cratered, and utterly lifeless. Instead, it's one of the most geologically active bodies we've ever discovered. Something is pumping enormous amounts of energy into this tiny world, enough to maintain a liquid ocean and power those dramatic plumes. For years, scientists assumed tidal heating from Saturn must be responsible. As Enceladus orbits, Saturn's gravity flexes and squeezes it, converting that mechanical stress into heat through friction. It's the same process that keeps Jupiter's moon Io volcanically active. The math seemed to work, barely, though it required some generous assumptions about the moon's interior structure. Then in 2014, measurements from Cassini's final close flybys revealed something that made those calculations fall apart. The amount of heat coming from Enceladus was far higher than tidal forces alone could explain. We're talking about 10 times more energy than the models predicted. That's not a small discrepancy you can explain away with measurement error. That's a fundamental problem requiring a completely different explanation, one that scientists are still actively debating. Several competing theories have emerged, each more interesting than the last. Some researchers think the moon's core might contain radioactive elements generating heat through decay, though that doesn't fully explain the localized heating near the South Pole. Others propose that the ocean itself might be chemically active, with reactions between water and rock producing heat along with those hydrogen molecules we detected. A few scientists have even suggested that tidal forces might be working in unexpected ways, perhaps amplified by the specific structure of Enceladus's interior in ways we don't yet understand. What makes this mystery particularly compelling is what it means for life. If conventional tidal heating can't explain Enceladus's energy budget, and if chemical reactions in the ocean are contributing significantly to that heat, then we're looking at an environment that's not just potentially habitable but actively energetic. Life needs energy. The more energy available, the more complex the chemistry that becomes possible. Earth's deep-sea hydrothermal vents, powered by similar chemical reactions, support entire ecosystems in complete darkness. Could something similar exist on Enceladus? The chemistry we've detected in those plumes keeps pointing in that direction. In 2018, complex organic molecules were identified, including compounds with chains of carbon atoms that on Earth are typically associated with biological processes. These weren't simple molecules like methane. We found materials like benzene and other aromatic hydrocarbons, structures that require specific conditions to form. While these can be produced through non-biological chemistry, their presence alongside water, salts, and hydrogen creates what astrobiologists call a biosignature ensemble, a collection of indicators that together become harder to explain without invoking life. Then came the phosphorus discovery in 2023, announced just months ago. Phosphorus is the final piece of the puzzle, the last major element required for life as we know it that we hadn't yet confirmed on Enceladus. It's essential for DNA, for cell membranes, for the energy-carrying molecules that power every living thing on Earth. Finding it in Enceladus's ocean, in a form that's accessible and reactive, meant that every single chemical requirement for life was now confirmed. Not theoretically possible. Actually present, measured, verified. Scientists don't use the word proven lightly when it comes to extraterrestrial life, and for good reason. Detecting the chemical ingredients for life isn't the same as detecting life itself. You can have all the right components without ever assembling them into something living. Earth's early oceans probably contained everything necessary for life for millions of years before the first organisms actually emerged. Chemistry alone doesn't equal biology. But the case for Enceladus keeps getting stronger in ways that go beyond simple chemical inventories. The plume composition varies over time, suggesting active processes in the ocean below rather than just static chemistry. The heat distribution across the South Pole shows patterns consistent with active hydrothermal systems. The very existence of those tiger-stripe fractures, the cracks from which the plumes emerge, implies ongoing geological activity driven by forces we're still trying to understand. Each observation adds another layer of complexity, another hint that something more than simple chemistry might be happening beneath that ice. What we're really talking about is probability. How likely is it that an environment with liquid water, organic molecules, energy sources, minerals, and chemical disequilibrium would remain sterile? On Earth, life appears almost immediately wherever these conditions exist. We find organisms in boiling acid pools, in frozen Antarctic lakes, kilometers deep in solid rock, anywhere liquid water touches chemistry and energy. The assumption that Earth is somehow special, that life only emerged here despite similar conditions existing elsewhere, requires increasingly creative explanations. The scientific community is being careful, as it should be. Extraordinary claims require extraordinary evidence, and detecting actual life on Enceladus would be the most extraordinary claim in human history. We need direct measurements, not just circumstantial evidence. We need to actually sample that ocean in ways that can definitively distinguish biological from non-biological chemistry. We need missions specifically designed to search for life, not just general reconnaissance flybys analyzing whatever happens to drift through the plumes. Those missions are coming. NASA and ESA both have proposals for Enceladus-focused spacecraft that would do more than just fly past. They'd orbit the Moon, sampling the plumes repeatedly with instruments specifically designed to detect biosignatures. They'd map the surface in detail, looking for the best places to eventually land. Some designs even include penetrators that could punch through the ice to sample the ocean directly, though that technology is still being developed. The political and funding challenges are real, but the scientific justification has never been stronger. Because here's what makes Enceladus different from every other target in the search for life. We don't need to dig. We don't need to drill through kilometers of ice or land in some specific location and hope we got lucky. The Moon is literally handing us samples, spraying its ocean into space where we can collect and analyze them. It's the easiest astrobiological target in the solar system, if we're willing to go there with the right tools. The implications extend far beyond one small moon. If we find life on Enceladus, if we confirm that biology emerged independently in a completely different environment from Earth, it changes everything we think we know about life's prevalence in the universe. It would mean that given the right conditions, life isn't rare. It isn't a miracle. It's almost inevitable, a natural consequence of chemistry and physics operating under certain parameters. And if those conditions exist on a tiny moon orbiting Saturn, how many other places in our galaxy might harbor life we never imagined possible? The universe suddenly becomes less lonely, less special, less centered on Earth as the one place where the cosmic lottery paid off. And that realization, that fundamental shift in perspective, might matter more than any individual discovery. But before we get too far ahead, we need to understand what we're actually looking for. The word life gets thrown around as if it has one clear meaning, but the reality is far more complex. When scientists talk about detecting life on Enceladus, they're not imagining fish swimming in dark oceans or forests of alien kelp. They're thinking about chemistry that behaves in ways non-living chemistry doesn't. They're looking for patterns, disequilibrium, organization that requires explanation beyond simple physics. The challenge is distinguishing biological signatures from clever geology. Earth's history is full of examples where scientists thought they'd found ancient life, only to discover later that minerals and chemical reactions could produce similar structures. Meteorites have arrived on Earth containing organic molecules that looked suspiciously biological until detailed analysis revealed purely abiotic origins. Mars has rock formations that resemble stromatolites, those layered structures built by microbes, except they're probably just weathered sediment. The universe is surprisingly good at mimicking life without actually being alive. So what would constitute genuine evidence? The gold standard would be finding cells, actual membrane-bound structures with internal organization distinct from their environment. But even that has complications. Would alien cells look like Earth cells? Would they have membranes made of lipids, or something completely different? Would they be large enough to see, or so small they'd slip through our filters? We're designing detection systems based on the one example of life we know, which might be like trying to recognize all possible music by only ever hearing jazz. Chemical signatures offer more immediate possibilities. Life on Earth produces characteristic ratios of molecules that don't occur in non-living systems. Amino acids, the building blocks of proteins, come in left-handed and right-handed versions that are mirror images of each other. Non-biological processes produce equal amounts of both. Earth life uses exclusively left-handed amino acids, a quirk of our biochemistry that creates an obvious signature. If Enceladus samples show similar homochirality, similar preference for one molecular form over another, that's hard to explain without biology. Isotope ratios provide another line of evidence. Living organisms preferentially use lighter isotopes in their metabolism because they're slightly easier to move around chemically. This creates distinctive patterns in carbon, nitrogen, and sulfur isotopes that differ from non-biological distributions. We can measure these ratios with extraordinary precision, looking for the subtle skewing that life produces. The trick is proving that what we're measuring reflects biology rather than some unknown geological process that just happens to produce similar patterns. Energy metabolism leaves traces too. Life on Earth operates far from chemical equilibrium, constantly pumping electrons through molecular machinery to extract energy. This creates specific chemical gradients, particular molecules that shouldn't coexist in stable environments but do because organisms are actively maintaining them. Finding these disequilibrium signatures in Enceladus samples would be suggestive, though not definitive without understanding the full geochemical context. The ideal scenario involves multiple independent lines of evidence converging. Not just one suspicious molecule, but a whole suite of measurements that collectively make more sense with biology than without. Homochiral amino acids plus isotope fractionation plus disequilibrium chemistry plus organized structures plus something we haven't even thought of yet. The more ways the evidence points in the same direction, the harder it becomes to construct alternative explanations. Current technology can't quite get us there. Cassini's instruments, remarkable as they were, weren't designed for life detection. They measured what was in the plumes at a general level, identifying broad chemical categories rather than the specific molecular details that would reveal biological signatures. It's like knowing a building contains organic compounds versus being able to read the individual books in its library. We need the equivalent of those books, the fine details that only purpose-built instruments can provide. Those instruments exist, at least in prototype form. Mass spectrometers sensitive enough to detect individual molecules at parts per trillion concentrations. Microscopes that can image structures smaller than the wavelength of light. DNA sequencers adapted for potential alien biochemistry, though that assumes alien life uses something like DNA, which is far from certain. The technology for rigorous life detection isn't science fiction. It's engineering and funding. The real constraint is getting that technology to Enceladus. Saturn orbits nearly 1.5 billion kilometers from Earth, requiring years of flight time even with gravitational assists from other planets. The radiation environment around Saturn is harsh, degrading electronics and requiring heavy shielding that adds mass and cost. Landing on Enceladus, or even achieving a stable orbit around it, demands propulsion systems and guidance precision we've only recently developed. Every kilogram of scientific instruments requires additional kilograms of fuel, structure, power, and communication equipment. Mission designers face brutal trade-offs. Do you maximize the number of plume passes with simpler instruments, or do you make fewer passes with more sophisticated equipment? Do you focus on chemical analysis, or invest in imaging systems that might spot surface features indicating subsurface activity? Do you design for flexibility, able to adapt to unexpected discoveries, or optimize for specific measurements with less margin for surprise? There's no perfect answer, only different gambles about what matters most. One proposed approach is the orbiter concept, a spacecraft that would spend years circling Enceladus, passing through the plumes dozens of times with instruments specifically designed for biosignature detection. Each pass samples different parts of the plume under different conditions, building up statistical confidence about what's actually there versus contamination or instrument error. The spacecraft would also map the surface in unprecedented detail, identifying patterns in the ice that might reveal circulation patterns in the ocean below. Another approach is more ambitious, a lander that would touch down near the tiger stripes, directly in the path of the plumes as they erupt. This eliminates the need for high-speed sampling, allowing more time for detailed analysis of fresh material before it's altered by space radiation or surface chemistry. The lander could also drill or melt through surface ice, looking for organic materials that might have frozen out of the plumes over time. The technical challenges are enormous, but the scientific payoff could be transformative. The most aggressive proposals involve actual ocean access, penetrators that would punch through the ice to sample the water directly. This is decades away technologically, requiring not just the ability to get through potentially 20 kilometers of ice, but to survive the pressure, communicate through that much solid material, and operate in a completely dark ocean with no GPS, no external power source, and no possibility of retrieval if something goes wrong. It's the kind of challenge that makes Mars sample return look straightforward. Cost is the other reality. Cassini's entire mission, from development through operations, ran about $3 billion. A dedicated Enceladus life detection mission would likely cost similar amounts or more, depending on complexity. That's money competing with dozens of other scientific priorities, from exoplanet observations to particle physics to climate monitoring. The political process of allocating those resources involves scientific merit but also timing, advocacy, public interest, and sometimes factors that have nothing to do with the science itself. Yet something is shifting in how seriously the scientific establishment takes Enceladus. When Cassini first revealed those plumes, the reaction was fascination but also caution. Now major space agencies are actively planning follow-up missions. Papers on Enceladus biology appear in top-tier journals. Astrobiologists who once focused exclusively on Mars are redirecting attention to icy moons. The evidence has reached a threshold where ignoring Enceladus feels harder to justify than investigating it. Part of this shift comes from parallel discoveries about life on Earth. The more we explore extreme environments here, the more we realize how adaptable life actually is. Organisms don't just tolerate extreme conditions, they thrive in them, sometimes growing better under pressure or in darkness than in supposedly optimal environments. We've found ecosystems kilometers underground powered entirely by chemical energy from rocks, no sunlight required. We've discovered microbes that reproduce in boiling acid, in Antarctic ice, in the cooling water of nuclear reactors. The boundaries of where life can exist keep expanding every time we look. These discoveries aren't just academic curiosities. They directly inform what we should expect on Enceladus. If Earth life can survive in environments that superficially resemble that subsurface ocean, environments with similar chemistry and energy sources and physical conditions, then the argument that Enceladus is too extreme for biology becomes much harder to sustain. The question shifts from whether life could exist there to whether it actually does, which is a very different kind of uncertainty. Human summary. One way to think about this is through probability layering. The chances that any single piece of evidence points to life might be small. But when you stack independent lines of evidence, the cumulative probability shifts. Enceladus has liquid water, confirmed. It has organic molecules, confirmed. It has energy sources in the form of chemical disequilibrium, strongly indicated. It has the right pH range based on plume chemistry. It has a rocky core providing minerals and catalytic surfaces. Each of these alone is interesting. Together, they describe an environment that looks increasingly similar to places on Earth where life not only exists but dominates. This doesn't prove biology. It does mean the null hypothesis, the assumption that Enceladus is sterile, requires stronger justification than it once did. You can't simply point to the cold or the darkness or the isolation and declare life impossible when we found terrestrial organisms thriving under all those conditions. The burden of proof hasn't fully reversed, but it's definitely shifting. There's also a philosophical dimension here that scientists don't always articulate but definitely think about. If we find life on Enceladus, it answers one of the oldest questions humans have ever asked. If we don't find it despite those conditions being right, that tells us something almost as important. It means the origin of life is harder than we thought, that even with all the right ingredients, biology doesn't just spontaneously emerge. Either outcome fundamentally changes how we understand our place in the universe. That's why some researchers push so hard for this mission despite the cost and complexity. It's not just curiosity, though that's part of it. It's the recognition that opportunities like this are rare. We've explored dozens of worlds and found exactly one with confirmed life. Now we have a second candidate that's actually accessible, that's literally spraying its ocean into space for us to sample. Walking away from that because it's expensive or difficult feels like a choice future generations would struggle to understand. The detection strategy matters as much as the mission design. What exactly would constitute proof of life in those plumes? This isn't as straightforward as it sounds. Organic molecules alone won't cut it. We've already found those, and they could easily form through non-biological chemistry. Simple amino acids, the building blocks of proteins, exist in meteorites that have never been near life. Even complex organics can emerge from purely chemical processes given the right conditions and enough time. The gold standard would be something that screams biology, something chemistry alone can't easily explain. patterns in how molecules are arranged. Life on Earth shows strong preferences, or chirality, in molecular structure. Amino acids come in left-handed and right-handed forms that are mirror images. Terrestrial biology almost exclusively uses left-handed amino acids. If Enceladus samples showed a similar bias, that would be striking because random chemistry produces equal amounts of both. A strong imbalance suggests selection, and selection usually means biology. Another marker would be isotopic ratios. Living organisms preferentially use lighter isotopes of elements like carbon and nitrogen because they're slightly easier to incorporate into biochemical reactions. This leaves a measurable signature, a deviation from what you'd expect in non-biological material. Multiple measurements showing consistent isotopic fractionation across different molecules would be hard to explain without invoking life. Then there are structural signatures. Cell membranes, even if the cells themselves are destroyed during sampling, might leave behind lipid patterns or vesicular structures visible under microscopy. Polymers with repeating units, especially if they show sequence complexity rather than random repetition, would raise serious questions. Biology builds information-rich structures. Chemistry builds repetitive or random ones. Spotting that difference requires incredibly sensitive instruments and careful analysis, but it's doable. The challenge is that we're looking for life that might not resemble Earth biology at all. It probably uses the same basic chemistry, water and carbon and energy flow, but the details could be wildly different. Maybe it doesn't use DNA. Maybe its proteins are built from different amino acids. Maybe it has cell walls made of materials we've never seen in terrestrial organisms. Designing instruments that can detect life as we know it while remaining open to life as we don't know it is one of the hardest problems in astrobiology. This is where contamination becomes a nightmare scenario. If we send a spacecraft that isn't perfectly sterilized and it finds organic molecules, how do we know they're not hitchhikers from Earth? Cassini wasn't built with biology in mind, so its cleanliness standards were lower than what we'd need now. Any future mission would require planetary protection protocols far more stringent than anything Cassini followed. That means building the spacecraft in ultra-clean facilities, sterilizing components with heat or radiation, and proving through rigorous testing that contamination levels are below detection thresholds. Even then, interpretation will be contentious. Science operates on reproducibility and peer review. One measurement showing possible biosignatures won't be enough. We'd need multiple independent detections, ideally using different techniques. We'd need ground-based labs analyzing return samples, if we can manage that technologically. We'd need theoretical models explaining how those signatures could arise biologically and why they couldn't arise chemically. The bar for claiming discovery of extraterrestrial life is extraordinarily high, as it should be. But here's what makes Enceladus different from every other target in astrobiology. The ocean is sampling itself. We don't have to drill through kilometers of ice or land on a hostile surface or wait decades for a rover to reach the right location. The plumes bring ocean material directly to us, fresh and uncontaminated by surface processes. That accessibility is transformative. It means the first real test of whether a subsurface ocean harbors life could happen within our lifetimes, maybe within the next 20 years if funding and planning align. Compare that timeline to Europa, where we're still debating whether we can even confirm the ocean's existence from orbit before committing to a lander. Or Titan, where the interesting chemistry is happening in lakes of liquid methane at 90 degrees above absolute zero, requiring entirely different instrument designs. Or Mars, where we've been searching for decades and still haven't found anything definitive despite constant presence on the surface. Enceladus offers a shortcut, a way to answer the life question without solving all the intermediate technical problems first. The geopolitical aspect is less discussed but increasingly relevant. Space exploration has always involved international cooperation and competition in varying measures. Right now, NASA is leading most serious Enceladus mission concepts, but ESA, the European Space Agency, has expressed strong interest in collaborative efforts. China's space program is expanding rapidly and has mentioned icy moon missions in long-term planning documents. Russia, despite economic constraints, maintains significant expertise in planetary science. A discovery of life on Enceladus wouldn't belong to any single nation. The scientific data would be shared globally, analyzed by researchers across dozens of countries, debated in international conferences and journals. But the prestige of making that discovery, of being the agency that sent the spacecraft that found it, matters. It shapes funding priorities, inspires the next generation of scientists and engineers, and demonstrates technological capability. These factors influence which missions get approved and when. There's also the private sector angle. Companies like SpaceX have dramatically reduced launch costs, which directly affects mission feasibility. A mission that would have cost $5 billion a decade ago might now be achievable for $3 billion because getting the spacecraft off Earth is cheaper. If that trend continues, the financial barrier to ambitious outer solar system missions drops steadily. That could accelerate timelines or allow more complex mission designs than traditional budgets would support. Would commercial interests ever target Enceladus directly? Probably not for resource extraction. The distances are too vast and the energy requirements too high for any conceivable economic return. But privately funded science missions aren't impossible. Several wealthy individuals have expressed interest in astrobiology. If someone wanted to fund an Enceladus life detection mission as a legacy project, the technical capability exists. It hasn't happened yet, but the landscape is shifting in ways that make it less unthinkable than it was even 10 years ago. Public perception plays into this as well. Missions require sustained political support, which means maintaining public interest across administrations and budget cycles. Enceladus has an advantage here because the concept is simple to communicate. There's an ocean under the ice. We can sample it. We might find life. That narrative resonates in ways that more abstract science goals sometimes don't. It's concrete, visual, and tied to a fundamental question people actually care about. The media coverage of Cassini's discoveries demonstrated this. Every major plume finding made headlines. The hydrothermal vent evidence was covered by mainstream news outlets, not just science publications. That visibility matters when Congress or parliaments are deciding which missions to fund. A mission to Enceladus isn't just scientifically justified, it's a story people want to follow. Human summary. And what happens if we actually find something? Not just organic molecules or chemical signatures, but clear, unambiguous evidence of biological activity. Something living, or something that was alive recently enough that we can study its biochemistry. The protocols for that scenario exist but have never been tested in practice. NASA established planetary protection guidelines decades ago, rules designed to prevent contamination in both directions. We don't want to accidentally bring Earth microbes to another world and mistake them for indigenous life. We also don't want to bring back something from another world without proper containment, though that's less of a concern for a mission that won't return samples directly to Earth. But the scientific protocols are just the beginning. The confirmation process would be rigorous to the point of paranoia. One instrument reading wouldn't be enough. One type of measurement wouldn't be enough. The standard would require multiple independent lines of evidence, preferably from different analytical techniques, all pointing toward the same conclusion. And even then, the debate would be intense. When Viking landers conducted experiments on Mars in the 70s, one test produced results that could have indicated microbial life. Decades of argument followed. Most scientists now think it was a chemical reaction, not biology, but consensus took years to establish. With Enceladus, the scrutiny would be even more severe because the implications are so profound. Teams would need to rule out every conceivable non-biological explanation before claiming a detection. That takes time, careful analysis, and probably follow-up observations if possible. The spacecraft might need to sample the plume multiple times, looking for consistency. Are the same signatures present in different plume particles? Do they show up in the same ratios? Are there seasonal variations or do the readings remain stable? Repeatability matters enormously in science, especially when making extraordinary claims. One intriguing reading is a puzzle. 3 identical readings from separate samples start looking like a pattern. 10 readings, all consistent, all showing the same biological markers, that becomes very difficult to explain through non-biological chemistry alone. Then there's the question of announcing it. How do you tell the world that we found life beyond Earth? The process would likely involve peer review first. Scientists would prepare papers documenting every measurement, every analysis, every alternative explanation they considered and rejected. Those papers would be submitted to journals like Science or Nature, where other experts would examine the methodology in detail. Only after passing that review would there be an official announcement. That's the ideal sequence anyway. In reality, information leaks. Mission teams involve hundreds of people. Data gets shared among collaborators. Someone always talks to someone else who talks to someone else. The discovery might become an open secret in the scientific community weeks or months before any public statement. Managing that information flow, preventing premature claims while maintaining scientific integrity, would be a challenge unlike anything space agencies have faced before. Because once the news breaks, the response would be immediate and global. Media coverage would be overwhelming. Every news organization on the planet would want the story. Scientists involved in the mission would face endless interview requests. Social media would explode with speculation, excitement, skepticism, and probably a fair amount of conspiracy theorizing. religious institutions would need to grapple with theological implications. Philosophers would debate what it means for humanity's place in the universe. Artists and writers would produce countless works inspired by the discovery. It would reshape conversations across every domain of human culture. Politically, the response would probably be unifying in the short term. Finding life elsewhere is the kind of news that transcends national boundaries and ideological divisions. It's bigger than any single country or political system. In that moment, humanity would have a shared experience, a collective realization that we're not alone, that life is a cosmic phenomenon rather than an Earth-specific accident. That could produce a brief period of global solidarity, a sense of common purpose and shared wonder. How long that lasts is another question. Humans are skilled at turning even unifying moments into sources of division. But initially, the reaction would likely be one of excitement and curiosity rather than fear or conflict. The practical questions would follow quickly though. What do we do next? One detection from one moon wouldn't tell us everything we need to know about life in the universe. It would tell us that life can exist in an ocean world beneath an ice shell. It would tell us something about the chemistry that supports it, the energy sources it uses, the environmental conditions it tolerates. But it wouldn't tell us how common life is, whether it arose independently on Enceladus or somehow shares an origin with Earth life, whether it's simple bacteria-like organisms or something more complex, whether it's currently active or represents an extinct biosphere we're detecting through molecular fossils. Each answer would generate 10 new questions. The logical next step would be more missions. If we find life on Enceladus, Europa immediately becomes a higher priority target. Does it also harbor life? Is it the same kind of life or something different? What about the other ocean worlds, Ganymede, Callisto, Titan? Do they show similar biosignatures or is Enceladus unique? Sample return missions would move from theoretical to essential. We'd need to bring material back to Earth where it could be analyzed with laboratory equipment far more sophisticated than anything we can fit on a spacecraft. That introduces the contamination concerns again, requiring quarantine facilities and handling protocols, but the scientific payoff would be enormous. We'd want to sequence genomes if the life is DNA-based, or understand whatever information storage system it uses if it's not. We'd want to study its metabolism in detail, grow it in culture if possible, understand its evolutionary history. All of that requires samples and equipment that won't fit through space anytime soon. Then there's the long-term question of protecting these environments. If Enceladus has life, do we have an obligation to leave it undisturbed? Right now, the moon is pristine, or at least as pristine as something can be after we've flown a spacecraft through its plumes several times. But intensive study would mean more missions, more instruments, possibly even landers on the surface or submarines in the ocean eventually. Each mission carries some risk of contamination, some chance of introducing Earth organisms that could disrupt or destroy native ecosystems. Space agencies take this seriously. Spacecraft bound for potentially habitable worlds undergo intensive sterilization. Components are heated to kill any microbes. Surfaces are cleaned with harsh chemicals. Assembly happens in clean rooms with filtered air and strict protocols. Nothing is perfect though. Some microbes survive extreme conditions. Spores can endure heat, cold, radiation, and vacuum. The chance of introducing something isn't zero, it's just very low. But very low multiplied by multiple missions over decades starts to add up. International agreements would probably be necessary. Rules about how many missions are allowed, what kinds of instruments can be used, what areas are off-limits to protect pristine environments. These agreements exist in principle through the Outer Space Treaty and Planetary Protection Guidelines, but they'd need to be strengthened and made more specific if we're dealing with confirmed biospheres rather than potential ones. And enforcement becomes tricky. Who decides what's acceptable? Who has the authority to prevent a nation or organization from launching a mission if they disagree with the restrictions? Space law is still developing in these areas. We're writing the rules as we go, usually staying one step behind the technology. The other long-term consideration is what finding life on Enceladus would mean for the search elsewhere. Does it make life seem more common or less? If two places in our solar system have life, that suggests biology emerges readily when conditions are right. Water, chemistry, and energy seem to be enough. That would be encouraging for the search around other stars. Every planetary system probably has multiple ocean worlds. If ocean worlds reliably develop life, then life might be everywhere. But there's a counterargument. What if Earth life and Enceladus life share a common origin? Panspermia, the idea that life can spread between worlds through meteorite impacts, isn't impossible. Mars and Earth have exchanged rocks throughout history. Material from Earth has reached the outer solar system, though rarely. If Enceladus life turns out to be related to Earth life genetically, that would be fascinating but also disappointing in a way. It would mean we've only found one origin of life, not two. We still wouldn't know if life is common or rare. We just know it can survive in different environments once it gets started. Distinguishing between these possibilities would require detailed genetic or biochemical analysis. If Enceladus life uses the same DNA structure, the same amino acids, the same basic cellular machinery as Earth life, common origin becomes likely. If it uses different building blocks, different coding systems, different fundamental chemistry, then it almost certainly arose independently. That would be the more profound discovery, two separate origins of life in the same solar system. At that point, the universe would statistically be teeming with life. We'd just be early in the process of finding it. The discovery wouldn't just reshape our understanding of life's abundance. It would force us to confront uncomfortable questions about intelligence, consciousness, and our own significance. If simple life exists in multiple places within one solar system, what about complex life? What about intelligence? The gap between microbes and minds is enormous, but if biology gets started easily, maybe that gap gets crossed more often than we think. Or maybe not. Maybe microbial life is common but complex multicellular organisms are vanishingly rare. Birth took billions of years to move from single cells to animals. Most of that time was spent as a microbial world. Intelligence came even later, in just the last few million years, a blink in geological time. There's no guarantee that evolution trends toward complexity. Natural selection doesn't have goals. It doesn't push life up a ladder toward intelligence. It just favors whatever works in the moment. If simple works, simple persists. Enceladus might have had life for billions of years without ever developing anything more sophisticated than bacteria. That would still be remarkable, but it would also suggest intelligence is a fluke, a rare accident that happened once on Earth and maybe nowhere else nearby. Then again, we don't really know what intelligence requires. We assume it needs complexity, nervous systems, brains. But what if there are other forms of cognition we wouldn't recognize? What if microbial communities develop collective behaviors that look simple individually but show emergent properties we'd classify as intelligent if we knew what to look for? We've seen hints of this on Earth. Bacterial colonies communicate chemically, coordinate responses, make collective decisions about growth and movement. Slime molds, not even animals, can solve maze puzzles and optimize network structures. Intelligence might not require neurons. It might just require information processing, feedback loops, and environmental interaction. Enceladus life could surprise us in ways we haven't imagined yet. But even if it's just microbes, the philosophical implications cut deep. For all of human history, we've wondered if we're alone. Every religion, every culture has grappled with our place in the cosmos. Finding life elsewhere, even simple life, even in our own solar system, changes that conversation permanently. We're not unique. We're not central. We're one example among potentially countless others. Some people find that thought liberating. It removes the burden of cosmic specialness, the pressure to justify our existence through uniqueness. We're just part of a larger pattern, one thread in a vast biological tapestry. Others find it unsettling. If we're not special, what's the point? If life is common, does individual life matter less? These are emotional reactions, not logical ones, but they're real and they'll shape how society processes the discovery. The scientific community would adapt quickly. Researchers would pivot to new questions, new investigations, new grant proposals. But the general public moves slower. Cultural narratives take time to shift. Education systems would need to incorporate this new reality. Textbooks would be rewritten. Documentaries would be produced. Children would grow up in a world where extraterrestrial life isn't science fiction, it's established fact. That generation would see the universe differently than any before them. They'd assume life is normal, expected, something to be studied and understood rather than wondered about in the abstract. Their questions would be different. Not whether life exists elsewhere, but what forms it takes, how it works, whether we can communicate with it. The long-term trajectory of human civilization might shift. If we know life is out there, space exploration becomes more urgent. Not just for scientific curiosity, but for connection, for understanding, for the possibility of finding something beyond microbes. Investment in telescopes, spacecraft, and astrobiology would increase. Private companies would get involved, not just governments. The economics of space would change if there's something genuinely valuable to find, not just rocks and radiation. And valuable doesn't necessarily mean resources. Knowledge is valuable. Contact is valuable. Understanding our place in a living universe is valuable in ways that don't show up on a balance sheet. But practical concerns would emerge too. If we're visiting Enceladus regularly, someone will eventually propose mining it. The moon has water, organic compounds, energy. Those are useful. Future spacecraft could refuel there. Habitats could be built. Humans might want to establish a presence. That raises a collision between exploration and exploitation. Do we have the right to industrialize a world with native life? Even if that life is microbial? Even if it's confined to subsurface oceans we're not directly disturbing? There's no clear answer. Earth's history offers cautionary tales. Every time humans encountered new ecosystems, we disrupted them. Sometimes deliberately, sometimes accidentally, but always irreversibly. Islands, forests, oceans, we've left marks everywhere. Doing the same thing on Enceladus would be consistent with our track record, but knowing we're doing it makes the choice more conscious, more morally weighted. Some would argue life anywhere is precious and must be protected absolutely. Enceladus should be declared a nature preserve, off-limits to anything beyond minimal scientific study. Others would argue humans have needs too, and resources in space should be available for our use, especially if that use enables further exploration and the spread of Earth life to new environments. Finding balance between these positions would require international cooperation on a scale we've rarely achieved. The Antarctic Treaty System provides a model. Antarctica is protected for scientific research, with resource extraction banned. Military activity is prohibited. Multiple nations cooperate to maintain the agreement despite political differences elsewhere. Something similar could work for Enceladus, but enforcement is harder when you're dealing with space. There's no border patrol in the outer solar system. Monitoring compliance would require trust, transparency, and shared oversight. Violations would be difficult to detect and even harder to punish. Still, the attempt would be worth making. Establishing norms now, before economic interests become entrenched, is easier than trying to impose rules later. The discovery of life on Enceladus would give us that narrow window, that brief moment when everyone agrees protection matters before anyone has invested billions in infrastructure. That window wouldn't stay open long. Within a decade, maybe two, commercial interests would start pushing boundaries. Technology would advance. Costs would drop. The moon would go from distant curiosity to accessible destination. Once that transition happens, preservation becomes much harder. So the discovery itself would trigger a race, not just to study Enceladus, but to define its future. Scientists racing to gather data before environments are disturbed. Ethicists racing to establish guidelines before they're needed. Policymakers racing to create enforceable frameworks before violations occur. And entrepreneurs racing to figure out what can be extracted, sold, or utilized before regulations lock things down. All of this would unfold in parallel with continued searching elsewhere. Because if Enceladus has life, the next question is immediate. What about Europa? What about Titan? What about the moons of Uranus and Neptune we've barely studied? What about ocean worlds around other stars? The search would expand rapidly, driven by the knowledge that we're not looking for something hypothetical anymore. We're looking for variations on a theme we've already confirmed. That's a different kind of search, more concrete, more urgent. Funding would flow toward missions that can answer these questions. Public support would be strong. Media coverage would be intense. The field of astrobiology would transform from speculative science to mainstream research with clear goals and measurable progress. Universities would expand programs. Students would flood into the discipline. The best minds of a generation would focus on understanding life beyond Earth, how it starts, how it evolves, what forms it can take. Within a few decades, we might have a comparative biology that spans multiple worlds. We'd understand what features are universal and what varies. We'd know if DNA is inevitable or just one option among many. We'd see if evolution follows similar patterns everywhere or takes wildly different paths depending on environment. That knowledge would feed back into our understanding of Earth life. We'd see ourselves more clearly by seeing what we're not. The assumptions we make because we only have one example would become visible. We'd recognize which aspects of biology are fundamental and which are accidents of our particular history. And somewhere in that process, the question would surface again, sharper than before. If simple life is common, what about complex life? What about intelligence? What about civilizations? Are we alone in that category, or is the universe filled with minds looking outward just like we are, wondering the same things? The question shifts from whether we're alone to whether we're typical. And that distinction matters more than it seems at first. Being alone means something fundamentally different than being rare. Being rare but not unique means the path we took, from chemistry to cells to consciousness, can happen elsewhere given enough time and the right conditions. That would make intelligence not a miracle but a statistical outcome, improbable for any single world but inevitable across enough worlds. The discovery of microbes on Enceladus wouldn't answer that question directly. Simple life doesn't predict complex life. Earth had bacteria for billions of years before anything more complicated emerged. The jump from single cells to multicellular organisms required specific conditions, particular evolutionary pressures, maybe a dose of luck. Nothing about finding bacteria on Enceladus would tell us if that jump is easy or nearly impossible. But it would narrow the possibilities. Right now, we can't rule out the idea that life itself is the bottleneck, that getting from chemistry to biology is so difficult it only happened once in the observable universe. Finding life on Enceladus would eliminate that possibility. The bottleneck would have to be somewhere else, either in the transition to complexity or in the emergence of intelligence or in the development of technology. Each of those could be common or vanishingly rare. We don't know. We can't know from a single data point. But we'd know more than we do now. We'd know the first step isn't impossibly hard. And that would shift how we think about the rest of the ladder. If microbial life turns out to be common, scattered across ocean worlds and buried in subsurface environments throughout the galaxy, then the question becomes duration. How long does life need to develop complexity? Earth took about 3.5 billion years to go from bacteria to animals. Is that typical? Could it happen faster under different conditions, or does it require that much time regardless of environment? We don't know because we've only watched it happen once, on a planet with a stable sun, a large moon, plate tectonics, and a magnetic field. Change any of those variables and the timeline might compress or stretch or terminate entirely. Complexity might require not just life but stable life, ecosystems that persist long enough for evolutionary experiments to compound. On Enceladus, environmental stability is questionable. The moon's interior ocean might have existed for billions of years, or it might cycle between frozen and liquid states depending on orbital dynamics and tidal heating. If conditions fluctuate too much, life might restart repeatedly, never accumulating the layers of complexity that lead to multicellular organisms. That would make Enceladus a place where life exists but doesn't progress, trapped in a loop of survival without advancement. Earth avoided that trap through a combination of factors we're still trying to fully understand. Our planet stayed in the habitable zone. Our atmosphere thickened at the right rate. Our magnetic field shielded the surface from sterilizing radiation. None of those things were guaranteed. All of them were necessary. Other worlds might have one or two of those factors, but not all. And without all of them, complexity might be impossible no matter how long life has to try. So the discovery of Enceladus life would open up a second wave of questions about what conditions allow life to move beyond survival. We'd start looking not just for life, but for environments stable enough to support its evolution. That's a harder search because stability is difficult to measure from a distance. You can detect water. You can detect chemistry. But assessing whether a world has been stable for billions of years requires indirect inference, modeling, long-term observation. Still, the effort would be worth it. Because if we find complex life, even just multicellular organisms, the implications escalate dramatically. Complex life means evolution found a path forward. It means the transition is possible, not just theoretically but practically, in environments that actually exist. And if it happened twice, once on Earth and once elsewhere, the probability shifts again. Two independent origins of complexity would suggest it's not a fluke. It would suggest that given life and time, complexity emerges reliably. That wouldn't guarantee intelligence. Evolution doesn't aim for intelligence. It optimizes for survival and reproduction. Intelligence is one strategy among many, useful in certain contexts, irrelevant or even counterproductive in others. Most complex life on Earth never developed anything resembling human cognition. Trees, fungi, jellyfish, insects, all complex, none intelligent in the way we use the term. So even if complex life is common, intelligence might not be. The evolutionary pressures that favor big brains, social cooperation, language, and abstract thinking might be rare. They might require specific ecological niches, particular kinds of predation pressure, or competition dynamics that don't exist on most worlds. Earth had those conditions in certain regions at certain times, and intelligence emerged multiple times independently. Dolphins, elephants, corvids, octopuses, primates, all developed advanced cognition through different evolutionary paths. That suggests intelligence isn't a one-time accident. But it also shows it's not universal. Most lineages don't go that direction. Most complex life remains non-intelligent. If intelligence is rare even among complex life, then finding it elsewhere becomes exponentially more difficult. We need to identify not just worlds with life, not just worlds with complex life, but worlds where evolution happened to push organisms toward cognition. And then we'd need to catch them during the narrow window when they're technologically active. Because intelligence without technology is invisible from interstellar distances. We can't detect thought. We can't sense consciousness. We can only look for the side effects of technology, radio signals, atmospheric pollution, megastructures, things that leak evidence into space. A planet full of intelligent but pre-technological beings would look lifeless to us. We'd scan it, see biosignatures maybe, but miss the minds entirely. That asymmetry matters. It means the search for intelligence is really a search for technological civilizations, not intelligence itself. And technology adds another filter, another step in the chain that might be common or might be nearly impossible. Earth's path to technology depended on fire, which requires oxygen-rich atmosphere and dry land. It depended on manipulative appendages, hands or tentacles capable of fine motor control. It depended on social structures that allowed knowledge to accumulate across generations. Remove any of those and technology might never develop no matter how intelligent the species becomes. Dolphins are smart, arguably as smart as early humans, but they can't build tools underwater. Octopuses are brilliant problem solvers, but they're solitary and short-lived, so their knowledge dies with each individual. Intelligence alone isn't enough. The environment has to permit its expression in ways that lead to technology. And even if all those conditions align, there's still the question of whether technological civilizations survive long enough to be detected. Humans have been radio capable for roughly a century. In cosmic terms, that's nothing, a flicker. If most civilizations last only a few centuries before collapsing or transcending or going silent, then the galaxy could be full of intelligence that we'll never notice because we're not looking at the right moment. The timing would have to overlap, our search coinciding with their broadcast, our receiver pointed at their transmitter during the brief window when both exist. That's a narrow target. It's possible we're surrounded by civilizations that existed 1 million years ago or will exist 1 million years from now, and we'll never know because we're scanning the wrong era. The Fermi paradox captures this tension. If life is common, if intelligence emerges reliably, if technology develops naturally, then where is everyone? Why haven't we seen evidence? The silence could mean we're alone. Or it could mean intelligence is common but short-lived. Or it could mean we're looking in the wrong places, listening for the wrong signals, missing evidence that's right in front of us because we don't recognize what we're seeing. Finding life on Enceladus wouldn't resolve the paradox, but it would shift the probabilities. It would confirm the first step is achievable, It would give us a second data point, a comparison that lets us start building models. And models, even rough ones, are better than pure speculation. They let us make predictions, design experiments, focus resources. Right now, the search for extraterrestrial intelligence operates in a fog of uncertainty. We don't know what we're looking for, where to look, or how common the target is. Every assumption is provisional. Every strategy is a guess. But if we find life nearby, if we confirm biology can start independently in multiple places within our own solar system, that fog lifts slightly. We'd know the universe is biologically active. We'd know the ingredients for life aren't unique to Earth. We'd know that wherever conditions permit, chemistry tries to become biology. And once we know that, the question isn't whether life exists elsewhere. The question becomes how far it gets. Right now, Enceladus is still just a candidate. We have chemistry, energy, water, everything life needs assembled in one place. But chemistry isn't biology. Potential isn't proof. The next decade will determine whether this tiny frozen moon becomes the most important place humanity has ever studied or just another interesting dead world with the right ingredients but no spark. The missions are being designed. Engineers are solving problems. Budgets are being negotiated. Within 15 years, maybe 20, we'll have spacecraft specifically built to answer this question. They'll fly through those plumes with instruments sensitive enough to detect molecular patterns that chemistry alone can't explain. They'll measure isotope ratios, search for homochirality, look for the subtle fingerprints that biology leaves on its environment. And when those results come back, transmitted across 1 billion kilometers of empty space, we'll be standing at one of two doorways. Either we'll have confirmation that life exists beyond Earth, that the universe is biologically active, that we're not alone. Or we'll have even deeper questions about why a world with every necessary ingredient remains sterile, what invisible barrier prevents chemistry from crossing into biology, what Earth had that Enceladus lacks. Both answers change everything. Finding life means rewriting our place in the cosmos, understanding that consciousness emerged not through cosmic accident but through processes that operate wherever conditions allow. Not finding life despite perfect conditions means the origin of life is harder than we thought, that some crucial factor we haven't identified makes the difference between chemistry and biology. The strange thing is we're living through the moment when this stops being philosophy and becomes data. For all of human history, the question of life beyond Earth was abstract, something to wonder about but never answer. Now we're maybe 2 decades from knowing. That's nothing. That's immediate. Anyone reading this will likely be alive when we get the answer, at least for Enceladus. What happens after depends entirely on what we find. Discovery of life triggers one future, a rapid expansion of astrobiology, missions to every ocean world we can reach, a fundamental recalculation of how common biology is. Not finding life triggers a different future, deeper investigation into what makes Earth special, more careful study of how life begins, perhaps lowered expectations about finding it elsewhere. Either way, we're approaching a boundary. The search for life has been theoretical for centuries, based on speculation and probability arguments. Soon it becomes empirical, based on measurements and data from actual environments where life might exist. That transition from wondering to knowing is rare in science. It usually happens quietly, through accumulated evidence rather than single dramatic discoveries. This might be different. If those instruments detect biosignatures in Enceladus's plumes, if multiple independent measurements converge on the same conclusion, if peer review confirms what the initial data suggests, then the announcement won't be quiet. It'll be the biggest news in human history, the moment we confirm we're not the only biology in the universe. And if the measurements come back negative, if the plumes contain only chemistry, if every test shows an ocean that's rich in potential but empty of life, that's also news. Profound news. It means we're rarer than we thought, that the universe doesn't automatically fill every habitable niche with biology, that Earth represents something unusual. We don't know which future we're heading toward. The data doesn't exist yet. But the fact that we're about to get that data, that we're living in the generation that will finally have an answer instead of just better questions, that matters. It changes how we think about exploration, about our priorities, about what we're actually searching for when we build spacecraft and point them at distant worlds. Enceladus is small. It's cold. It's unimaginably far from anything humans have ever touched. But right now, as you're reading this, it's spraying its ocean into space, offering samples of its hidden depths to anyone capable of reaching them. That opportunity won't wait forever. Eventually, mission windows close, funding priorities shift, political will fades. The moment to answer this question is now, not someday, not when it's more convenient. Because if there's life in that ocean, every day we wait is another day we remain ignorant of the most important discovery our species could make. And if there's not, every day we wait is another day we avoid learning something equally important about how rare and precious life actually is. Either answer justifies the effort, the cost, the decades of work required to get there and find out. The universe isn't going to hand us easy answers. It never has. But occasionally it offers shortcuts, places where the barriers between us and knowledge are thinner than usual. Enceladus is one of those places. A world that's literally giving us samples, that's making the search for life easier than it has any right to be, that's accessible with current technology if we choose to go. That choice is being made right now in budget meetings and conference rooms, in engineering labs and planning sessions. The decision about whether to prioritize Enceladus, whether to fund the missions that could actually answer this question, that's happening in the present tense. And once those decisions are made, once the spacecraft are built and launched, once they're committed to 7-year journeys across the solar system, we're locked in. We'll get our answer. Whatever it is. Human history will split at that point into before and after. Before we knew if life existed beyond Earth. After we confirmed it or ruled it out, at least in the most accessible place we found. That boundary is approaching faster than most people realize. We're not talking about science fiction futures or distant possibilities. We're talking about missions that could launch in the next decade, that could return data before 2040, that could answer humanity's oldest question within the lifetime of everyone currently alive. The clock is running. Enceladus is still there, still spraying its secrets into space, still waiting for us to show up with the right instruments and ask the right questions. Whether we do that, whether we commit the resources and attention required to actually find out what's in that ocean, that's on us. The universe has done its part. It's put the evidence right where we can reach it. What we do with that opportunity will define this era of human civilization more than almost anything else we're capable of achieving. Because this isn't about one moon or one mission or one scientific question. It's about whether we're alone. And that answer, whatever it turns out to be, changes everything that comes after. Around 252 million years ago, Earth experienced something that makes every other extinction event look mild by comparison. 96% of marine species vanished. 70% of land vertebrates disappeared. The planet became so hostile that scientists call this period the Great Dying. This wasn't a quick asteroid impact like the one that killed the dinosaurs. This was something far more terrifying because it was slow, relentless, and touched every corner of the globe. Before we dive into the catastrophe itself, you need to understand what Earth looked like when everything was still intact. The Permian period stretched from roughly 299 to 252 million years ago, and the planet during this time was almost unrecognizable compared to today. All the continents had fused together into a single massive landmass called Pangaea. Imagine taking every modern continent, smashing them together, and creating one enormous supercontinent that stretched from pole to pole. That was Earth's geography for millions of years. This configuration created extreme climates that most modern organisms would find impossible to survive. The interior of Pangaea, thousands of kilometers from any ocean, became a scorching desert. Without nearby water to moderate temperatures, these inland regions experienced brutal heat during summer and freezing cold in winter. Coastal areas remained more temperate, but the sheer size of Pangaea meant that vast stretches of land received almost no rainfall. Seasonal monsoons would arrive with devastating force, then disappear for months, leaving the landscape parched and cracked. The oceans surrounding Pangaea, collectively called Panthalassa, covered everything else. On the eastern side of the supercontinent, a large bay called the Tethys Sea cut inward, creating a somewhat more sheltered marine environment. But even the oceans weren't stable. Sea levels fluctuated dramatically throughout the Permian, exposing and then flooding continental shelves repeatedly. These changes stressed marine ecosystems that had evolved over millions of years to expect certain conditions. Life had adapted remarkably well to these harsh conditions, though. Synapsids dominated the land, and these weren't dinosaurs. They were the ancestors of mammals, though they looked nothing like the mammals we know today. Picture creatures like Dimetrodon, with its distinctive sail-like back, or the massive herbivore Moschops, built like a barrel with stubby legs. These animals had developed strategies to cope with Pangaea's extreme temperatures and limited resources. Some regulated their body temperature through behavioral adaptations. Others had developed more efficient metabolisms. In the oceans, life thrived despite the challenges. Coral reefs built by organisms called rugose and tabulate corals created complex ecosystems. Brachiopods, shelled creatures that look superficially like clams but are actually completely different animals, covered the seafloor in dense colonies. Trilobites, those iconic armored arthropods that had survived for hundreds of millions of years, still crawled along the bottom, though their diversity had declined from earlier peaks. Ammonoids, spiral-shelled relatives of modern squid, hunted through the water column. The climate itself was in a precarious state. Atmospheric oxygen levels during the Permian were lower than today, possibly around 15 to 19% compared to our current 21%. This meant that animals couldn't grow as large as they had during the Carboniferous period, when oxygen levels had soared to 35% and insects the size of eagles buzzed through ancient forests. Carbon dioxide levels fluctuated throughout the Permian, sometimes spiking high enough to warm the planet significantly, then dropping again. But underneath this seemingly stable world, pressure was building in ways that nothing alive could detect. Deep beneath what is now Siberia, magma was accumulating in enormous chambers. Tectonic forces were arranging the pieces for the largest volcanic event in the last half-billion years. The continents, locked together in Pangaea, had created stress points in Earth's crust that were reaching their breaking point. Ocean chemistry was balanced in a way that left little room for error. What I'm about to describe isn't speculation. The evidence is written in rock layers across the planet, in isotope ratios that tell us about ancient temperatures, in fossil beds where entire ecosystems are frozen in their final moments, in chemical signatures that reveal exactly what happened to the atmosphere and oceans. Scientists have spent decades piecing together this story from hundreds of sites worldwide, and what they've found is more disturbing than any disaster movie. The extinction didn't start with a bang, it started with a crack. Around 252 million years ago, the Siberian traps began to erupt. These weren't typical volcanoes forming cone-shaped mountains. This was flood basalt volcanism, where magma poured out of massive fissures in the ground and spread across the landscape like water from a broken dam. The lava flows eventually covered an area roughly the size of modern-day Europe, in some places piling up more than 3 kilometers thick. But here's what made this volcanic event uniquely catastrophic. The magma didn't just erupt onto the surface. It burned its way up through layers of sedimentary rock loaded with coal, oil shales, and limestone. Each rock type released different gases when heated. Coal combustion pumped out massive amounts of carbon dioxide and carbon monoxide. Oil shales released hydrocarbons and toxic organic compounds. Limestone, when heated past certain temperatures, breaks down and releases even more carbon dioxide. The atmosphere began changing in ways that life simply couldn't adapt to fast enough. Carbon dioxide levels skyrocketed, and this wasn't just a matter of a few hundred parts per million. Some estimates suggest CO2 concentrations may have increased by thousands of parts per million over a period of tens of thousands of years. That might sound slow, but in geological terms, it was catastrophically rapid. Ecosystems need time to adjust, to evolve, to migrate. They didn't get that time. Temperature reconstructions from this period show a warming pulse that raised global average temperatures by anywhere from 5 to 10 degrees Celsius. In the already hot interior of Pangaea, this meant temperatures regularly exceeded 50 degrees Celsius. Most large animals can't survive sustained exposure to temperatures much above 40 degrees. Their proteins literally begin to denature. Smaller organisms could burrow underground or hide in caves during the worst heat, but large synapsids had nowhere to go. The warming triggered a cascade of secondary effects that made everything worse. As temperatures rose, the oceans absorbed more heat. Warm water holds less dissolved oxygen than cold water, so oxygen levels in the ocean began to drop. Deep ocean circulation, which normally brings oxygen-rich water from the poles to the depths, weakened or stopped entirely. The ocean floor became anoxic, meaning it contained essentially no oxygen. Anaerobic bacteria that thrive in these conditions began producing hydrogen sulfide as a waste product. Hydrogen sulfide is viciously toxic. It's the compound that gives rotten eggs their smell, but in high concentrations, it attacks the respiratory systems of animals and can kill quickly. As anoxic zones expanded upward from the deep ocean, hydrogen sulfide began bubbling up into shallow waters and possibly even into the atmosphere. Imagine trying to breathe air that smells like rotten eggs and burns your lungs with every breath. That was becoming reality in many coastal regions. The ocean's chemistry was changing in another crucial way. As carbon dioxide levels in the atmosphere increased, more CO2 dissolved into the ocean, forming carbonic acid. This process, called ocean acidification, is happening today but at a much slower rate. During the Permian extinction, acidification happened so rapidly that organisms building calcium carbonate shells or skeletons couldn't keep up. The water was literally dissolving their protective structures faster than they could build them. Coral reefs, which had taken millions of years to establish, collapsed completely. The organisms that built them couldn't maintain their calcium carbonate skeletons in increasingly acidic water. When the reefs died, all the species that depended on them for shelter, food, and breeding grounds died too. This pattern repeated itself across every marine ecosystem. Brachiopods vanished in enormous numbers. Trilobites, which had survived multiple mass extinctions over 300 million years, finally met their end. Only a handful of species made it through. On land, the situation was equally dire but played out differently. As temperatures soared and rainfall patterns shifted dramatically, vegetation died back. Without plants to stabilize soil and maintain the water cycle, erosion increased. Rivers choked with sediment. Lakes dried up. The food chain collapsed from the bottom up. Herbivores starved first, then the carnivores that depended on them. Fossil evidence from this period shows a characteristic pattern. Diverse ecosystems with dozens of species suddenly give way to sparse assemblages dominated by just one or two hardy species, then even those disappear. The extinction wasn't instantaneous. Current evidence suggests the worst phase lasted somewhere between 60,000 and 200,000 years. That's a geological eye blink, but for the creatures living through it, it was generation after generation of decline, of watching their world become progressively more hostile. Some species might have survived for tens of thousands of years in isolated pockets where conditions remained barely tolerable, only to finally succumb as those last refuges failed. What I find most unsettling about the Permian extinction is how many different killing mechanisms were operating simultaneously. It wasn't just heat, or just acidification, or just oxygen depletion. It was all of them, plus factors we probably haven't even identified yet, all working together to make the planet nearly uninhabitable. Life was being squeezed from every direction at once, with no escape route. And yet, somehow, life survived. Not most life. Not even a significant fraction of life. But enough. In the aftermath of the extinction, Earth was left with a biological blank slate. The survivors were mostly small, tough organisms that could tolerate extreme conditions. They inherited a planet that had been emptied of competition. What happened next would determine the entire future trajectory of complex life on Earth, including eventually us. The survivors faced a world that barely resembled the one their ancestors had known. Imagine stepping outside and finding that 90% of everything familiar had vanished. The landscape was sparse, strange, eerily quiet. This was Earth in the earliest Triassic period, roughly 252 million years ago. The recovery wasn't immediate. For the first million years after the extinction, ecosystems remained incredibly simple. Fossil beds from this time show what scientists call disaster fauna, assemblages dominated by just a few opportunistic species that could tolerate harsh conditions. One organism in particular became absurdly common, a small shrimp-like creature called chlorea that appears in massive numbers in early Triassic rocks worldwide. Its abundance suggests oceans with very low oxygen and limited food sources, conditions where generalists that could survive on almost anything had a massive advantage. On land, a similar pattern emerged. Lystrosaurus, a stocky herbivorous synapsid about the size of a pig, became perhaps the most successful land vertebrate of all time in terms of sheer dominance. Some fossil sites from the early Triassic are composed almost entirely of Lystrosaurus remains. It's estimated that this single genus may have comprised 95% of all land vertebrates for a period. That level of dominance is unprecedented. It suggests an ecosystem so simplified that normal competitive dynamics had broken down completely. But Lystrosaurus had traits that made it perfect for the post-apocalyptic world. It was relatively small, which meant lower food requirements. Its teeth were adapted for eating tough, low-quality vegetation, the kind of scrubby plants that colonize disturbed ground. It could probably dig burrows to escape temperature extremes. And crucially, it had a sprawling posture and physiology that allowed it to function in low oxygen conditions. While more active animals were suffocating, Lystrosaurus just kept plodding along. The early Triassic climate remained brutal. Global temperatures stayed elevated for millions of years. Some climate models suggest average temperatures were 6 to 8 degrees Celsius higher than today, with equatorial regions potentially reaching 50 degrees or more. At those temperatures, large animals physically cannot survive without sophisticated cooling mechanisms. Heat stroke becomes inevitable. This explains why the surviving animals were predominantly small. Large size, which had been an advantage in cooler Permian climates, became a death sentence. Recovery happened slowly, in pulses. The fossil record shows several false starts where biodiversity began increasing, only to crash again. These setbacks were likely caused by recurring environmental stress, volcanic eruptions that continued sporadically, or climate instability as Earth's systems struggled to reach a new equilibrium. Each setback reset the recovery process, eliminating newly evolved species and giving advantage once again to the hardy generalists. Around 5 million years into the Triassic, things finally began to stabilize. Oxygen levels crept back up. Ocean chemistry gradually normalized. Terrestrial ecosystems developed more complex soil structures as plants recolonized. And with stability came opportunity. The evolutionary experiments could begin. This is where the story gets interesting, because the survivors weren't just rebuilding what existed before. They were creating something entirely new. The dominant land animals of the Permian had been synapsids, the group that would eventually give rise to mammals. But synapsids had been devastated by the extinction. While some like Lystrosaurus survived, the group as a whole was greatly diminished. Another group saw their opportunity, the archosaurs. Archosaurs were reptiles, but a specific lineage distinct from the reptiles that would become lizards and snakes. In the Permian, archosaurs have been relatively minor players. After the extinction, they began diversifying rapidly. Early Triassic archosaurs were mostly small, quick carnivores that walked on all fours. They had certain advantages: a more efficient respiratory system than most other reptiles, an upright gait that was more energy efficient, and in some lineages, possibly even a form of warm-bloodedness. By the Middle Triassic, archosaurs had split into several distinct lineages. One branch would lead to crocodiles. Another would lead to pterosaurs, the flying reptiles. And one branch, the dinosauromorphs, would change everything. But we're not there yet. First, the world had to become strange. The Middle Triassic produced some of the weirdest creatures in vertebrate history. Without established ecological structures, evolution was experimenting wildly. Tanystropheus had a neck longer than its body and tail combined, possibly for snatching fish from the water while keeping its body safely on shore. Chaeravipteryx had enormous hind legs with flight membranes, a body plan never seen before or since. Longisquama had bizarre elongated scales along its back that some scientists think might have been precursors to feathers, though this remains controversial. The oceans weren't being left out of this evolutionary free-for-all. Ichthyosaurs appeared, reptiles that returned to the sea and evolved into forms remarkably similar to dolphins, complete with streamlined bodies and fish-like tails. Some species grew to enormous size, over 15 meters long. Nothosaurs developed, semi-aquatic predators that hunted in coastal waters. And in a twist nobody saw coming, some groups of marine reptiles developed live birth rather than laying eggs, a necessary adaptation for a fully aquatic lifestyle. Meanwhile, on land, the first true dinosaurs were emerging. They appeared around 230 million years ago, during the Carnian stage of the late Triassic. The earliest dinosaurs we know of, creatures like Heterosaurus and Eoraptor were relatively small, between 1 and 3 meters long. They were bipedal, meaning they walked on 2 legs, which was unusual at the time. Most large animals were quadrupedal. This bipedal stance freed up their forelimbs for grasping prey and gave them speed advantages. But here's the thing that surprises most people. Early dinosaurs were not dominant. They were uncommon members of ecosystems still ruled by other archosaurs and various synapsid holdovers. For the first 15 to 20 million years of their existence, dinosaurs were minor players. The Triassic world belonged to different creatures. The true rulers of the late Triassic were the Rauisuchians, enormous predatory archosaurs that could reach lengths of 6 to 9 meters. They looked somewhat crocodile-like but walked upright on 4 legs and were purely terrestrial. Postosuchus and Saurosuchus were apex predators that would have made early dinosaurs look like snacks. Alongside them, Aetosaur, heavily armored herbivorous archosaurs, filled ecological roles similar to later armored dinosaurs, even though they weren't closely related. So why did dinosaurs eventually take over? The answer involves another catastrophe. Around 201 million years ago, at the boundary between the Triassic and Jurassic periods, Earth experienced another mass extinction. This one wasn't as severe as the Permian event. It wiped out perhaps 75% of species rather than 95%, but it was devastating enough to completely restructure ecosystems. The cause appears to have been massive volcanic eruptions associated with the breakup of Pangaea. As the supercontinent began splitting apart, enormous volumes of lava poured out across what's now the Atlantic Ocean. The Central Atlantic Magmatic Province, as it's called, was one of the largest volcanic events in Earth's history. Once again, carbon dioxide flooded the atmosphere. Temperatures spiked. Ocean chemistry went haywire. And once again, the survivors weren't necessarily the strongest or largest, but those with the right combination of traits for the new conditions. The Rauisuchians, those dominant Triassic predators, went extinct. The large herbivorous synapsids disappeared. Many of the weird experimental forms vanished. But dinosaurs made it through, and not just barely, they thrived. What gave dinosaurs the edge? Several factors probably contributed. Their efficient respiratory system, which involved air sacs that allowed continuous airflow through the lungs, similar to modern birds. This meant they could extract more oxygen from each breath, crucial in potentially low oxygen conditions. Their upright posture, which was more energy efficient for sustained activity than the sprawling gait of many competitors. And possibly their relatively fast growth rates, which allowed populations to recover quickly after disruptions. In the aftermath of the Triassic-Jurassic extinction, dinosaurs rapidly diversified and grew larger. The early Jurassic saw the emergence of the first giant sauropods, long-necked herbivores that would eventually become the largest land animals ever to exist. Theropods, the carnivorous dinosaurs, evolved into a spectacular array of forms. And a third major group, the Ornithischians, developed specialized herbivorous adaptations. Within 10 million years of the extinction, dinosaurs have become the dominant large animals on every continent. Their reign would last for 135 million years, an almost incomprehensibly long period of time. During that span, they would evolve into thousands of species, from chicken-sized hunters to 100-ton giants, from Arctic-dwelling forms to desert specialists. But their success was built on a foundation of catastrophe. Without the Permian extinction emptying the world, without the Triassic-Jurassic event eliminating their competitors, dinosaurs might have remained minor players forever. The history of life is written as much by what dies as by what survives. And so the age of dinosaurs began in earnest, not with a bang but with a quiet expansion into empty space. The early Jurassic world, roughly 201 to 174 million years ago, was dramatically different from what came before. Pangaea was still mostly intact but beginning to fracture. The climate was warm and humid across most of the supercontinent, with no polar ice caps. Sea levels were rising as the planet warmed, creating shallow inland seas that fragmented the land masses. In this greenhouse world, vegetation exploded. Ferns carpeted the ground. Conifers towered overhead. Cycads and ginkgos filled the middle layers. For herbivores, it was an all-you-can-eat buffet, and the sauropods took full advantage. These long-necked giants developed a body plan so successful it would persist, with variations, for the rest of the Mesozoic. Their small heads sat atop necks that could reach high into the canopy or sweep low across the ground. Their massive bodies housed enormous guts capable of processing huge quantities of low-quality plant material. And their pillar-like legs supported weights that would crush most other vertebrates. But here's what's fascinating about sauropod evolution. They didn't just get big. They got big in very specific ways that solved particular problems. Their necks contained numerous lightweight vertebrae with hollow spaces, air sacs that reduced weight while maintaining strength. Their respiratory systems were incredibly efficient, pulling oxygen through the lungs in one direction rather than in and out like mammals. And they laid eggs, which might seem trivial until you consider the alternative. A mammal giving live birth to a baby sauropod would be physically impossible. The mother would die. Eggs solved this problem elegantly, allowing even the largest dinosaurs to reproduce without the constraints that limited mammalian size. The theropods, meanwhile, were exploring different strategies. While sauropods went big and slow, theropods remained relatively agile. Early Jurassic forms like Dilophosaurus were already showing the basic theropod template: bipedal stance, grasping hands, sharp teeth. They weren't the apex predators yet, not the way later forms would be, but they were competent hunters filling various niches. Then something unexpected happened. Some theropods started shrinking. This seems counterintuitive in a world trending toward gigantism, but evolution doesn't follow our expectations. Smaller theropods could access different food sources, hide from larger predators, and reproduce more quickly. Some began developing feathers, probably first for insulation or display, only later for flight. This lineage would eventually lead to birds, but we're getting ahead of ourselves. The Middle Jurassic, from about 174 to 163 million years ago, is frustratingly poorly known. The fossil record from this period is patchy, leaving paleontologists with tantalizing glimpses rather than a complete picture. But what we can see suggests continued diversification. Sauropods were getting larger. the first stegosaurs appeared, those plated dinosaurs with tiny heads and huge bodies. And in the oceans, marine reptiles were reaching their own impressive sizes. It's worth pausing here to note what wasn't happening. Dinosaurs dominated the land, yes, but they never conquered the oceans or truly mastered the air during most of their reign. The seas belonged to ichthyosaurs, plesiosaurs, and later mosasaurs, none of which were dinosaurs. The skies were ruled by pterosaurs, flying reptiles that were cousins to dinosaurs but not dinosaurs themselves. This tells us something important about evolution. Dominance in one environment doesn't automatically translate to dominance everywhere. Each realm required its own specialized adaptations. The late Jurassic, 163 to 145 million years ago, is when dinosaurs really hit their stride. This is the period most people picture when they think dinosaur. Enormous sauropods like Brachiosaurus, Diplodocus, and Apatosaurus roamed what's now North America. Allosaurus stalked them, a 9-meter predator with huge jaws and slashing claws. Stegosaurus defended itself with its distinctive back plates and spiked tail. And in what's now Germany, a small feathered dinosaur called Archaeopteryx left fossils that would later help scientists understand the dinosaur-bird connection. The Morrison Formation in the American West preserves this world in exquisite detail. Picture a landscape of braided rivers and floodplains, dotted with conifer forests and fern prairies. Sauropods move through in herds, stripping vegetation. Theropods followed, looking for weak or isolated individuals. Smaller dinosaurs scurried through the undergrowth. And overhead, pterosaurs wheeled through skies that had never known a bird. But scale can be deceptive. When we see museum skeletons or movie reconstructions, we're seeing the success stories, the animals that grew large and left impressive fossils. We're not seeing the thousands of smaller species that left fragmentary remains for no fossils at all. For every Brachiosaurus, there were probably dozens of chicken-sized dinosaurs we'll never know existed. The fossil record is biased toward big animals with hard bones in the right environments. Everything else is mostly invisible to us. The Cretaceous period, from 145 to 66 million years ago, saw dinosaurs reach their peak diversity. This wasn't because they were getting better at being dinosaurs. It was because the world itself was fragmenting. Pangaea had fully broken apart. Sea levels were extraordinarily high, creating more coastline and shallow seas than at any other point in Earth's history. Continents were isolated from each other, allowing evolution to proceed independently on different land masses. This geographic separation led to spectacular diversity. In South America, massive carnivores like Giganotosaurus evolved, possibly even larger than Tyrannosaurus rex. In Africa, Spinosaurus developed a bizarre sail-backed body plan and semi-aquatic lifestyle. In Asia, the tyrannosaurs were beginning their rise to dominance. And in North America, the famous late Cretaceous fauna was assembling: Triceratops, Ankylosaurus, Pachycephalosaurus, and eventually T. Rex itself. The Cretaceous also saw the rise of flowering plants, angiosperms, which would fundamentally reshape terrestrial ecosystems. Before this, plant reproduction was slow and inefficient. Conifers, ferns, and cycads dominated. But flowering plants reproduced faster, grew more quickly, and formed more complex relationships with animals. They offered new food sources, fruits, nectar, and more nutritious leaves. Herbivorous dinosaurs adapted, developing sophisticated chewing mechanisms. Hadrosaurs, the duck-billed dinosaurs, had hundreds of teeth arranged in dental batteries that could grind through tough plant material. Ceratopsians had powerful beaks and shearing teeth. Ankylosaurs had fermentation chambers in their guts. These weren't simple animals mindlessly eating and reproducing. Evidence suggests complex behaviors, parental care in some species, possible migratory patterns, social structures, even potential territorial displays. We find bone beds with dozens of individuals of the same species, suggesting herding behavior. We find nests with carefully arranged eggs and evidence of adults returning to nesting sites. Some species show sexual dimorphism, different body features between males and females, hinting at complex mating rituals. By the late Cretaceous, roughly 80 to 66 million years ago, dinosaur ecosystems had reached a level of complexity comparable to modern ecosystems. There were small insectivores, medium-sized herbivores, giant browsers, pack hunters, and solitary apex predators. There were specialists and generalists, lowland forms and upland forms. In some environments, dinosaur diversity rivaled what we see in modern mammal communities. And they were still evolving, still adapting, still producing new forms. There's no evidence they were in decline before the asteroid hit. Some paleontologists have argued that dinosaur diversity was dropping in the final million years of the Cretaceous, but this is hotly debated and probably reflects biases in the fossil record rather than actual decline. The dinosaurs weren't old and tired. They weren't evolutionary dead ends waiting for extinction. They were thriving. Which makes what happened next even more shocking. An asteroid roughly 10 kilometers across, traveling at about 64,000 kilometers per hour, slammed into what's now Mexico's Yucatan Peninsula. The impact released energy equivalent to billions of nuclear bombs. It vaporized rock, created a crater almost 200 kilometers wide, and sent shockwaves around the planet. Within hours, debris was raining down globally, igniting fires across multiple continents. Within days, dust and sulfur compounds had blocked out the sun. Within months, photosynthesis had ceased almost everywhere. The dinosaurs, those magnificent animals that had dominated for 165 million years, died. Not all at once, and not all for the same reasons. Some starved when plants died. Others froze when temperatures plummeted. Many drowned in tsunamis or suffocated in toxic air. The large ones went first, unable to find enough food to maintain their massive bodies. The specialists followed, their narrow ecological niches collapsing. What survived were the small, the flexible, the generalists. Animals that could hide, that could eat almost anything, that could tolerate cold and darkness. And among the survivors, barely, were the birds. Birds are dinosaurs. Not descendants of dinosaurs, not related to dinosaurs. They are dinosaurs, the only lineage that made it through. Every sparrow, every pigeon, every eagle is a living theropod, carrying forward a heritage that stretches back to the Triassic. The asteroid didn't end the dinosaur story. It edited it down to a single surviving branch. But let's be precise about what survived. Not all bird groups made it. The Cretaceous sky was full of avian diversity, toothed birds, flightless diving birds, large terrestrial forms. Most died. What crossed the boundary were small, likely generalist species. Birds that could eat seeds, insects, maybe carrion. Birds that didn't depend on specific forest types or particular prey animals. In the immediate aftermath, with forests burned and food chains shattered, flexibility was everything. The early Paleocene, the period right after the extinction, was a drastically simplified world. Fossil sites from this time show ecosystems with far fewer species, simpler structures, less specialization. The recovery wasn't instant. For the first million years or so, life struggled. Ferns exploded across the landscape, a classic disaster response. They're fast-growing, spore-based, and thrive in disturbed environments. Pollen records show what's called a fern spike right at the extinction boundary, a sudden overwhelming dominance of fern spores in the geological record. Slowly, ecosystems rebuilt. Flowering plants returned, though the composition changed. Some Cretaceous plant families vanished entirely. Others that had been minor players became dominant. Animal communities reassembled, but with completely different caste lists. The niches that dinosaurs once filled, gigantic herbivores, massive predators, were now empty. And into that vacuum stepped the mammals. Mammals have been around almost as long as dinosaurs, originating in the late Triassic around 225 million years ago. But for the entire Mesozoic, they'd been bit players. Small, mostly nocturnal, eating insects and seeds and staying out of the way. The largest known Mesozoic mammal, Repenomamus, was about the size of a badger and possibly 8 baby dinosaurs, but that was exceptional. Most were mouse-sized or smaller. Why were they so small? Probably because dinosaurs occupied all the larger ecological roles. There was simply no space. Any mammal that tried to get bigger would be competing directly with vastly more successful reptilian forms. So mammals stayed small, stayed hidden, and survived in the margins. Then the asteroid reset the board. Within 10 million years, an eye blink in geological terms, mammals exploded in size and diversity. By the early Eocene, roughly 56 million years ago, there were mammal predators as large as bears, herbivores the size of rhinos, and bizarre experimental forms that have no modern equivalents. Consider Androsarchus, known only from a massive skull found in Mongolia. It lived about 45 million years ago and may have been the largest mammalian land predator ever, possibly reaching a ton in weight. Or the Brontotheres, rhino-like herbivores with elaborate horns and head crests. Or the Entelodonts, sometimes called hell pigs, aggressive omnivores with bone-crushing jaws. The Paleocene and Eocene were periods of wild evolutionary experimentation. With so many niches empty, natural selection could explore options that would never have been viable in the Mesozoic. Some experiments worked. Most didn't. The fossil record from this time is full of short-lived lineages, creatures that appeared, diversified briefly, then vanished as better adapted groups replaced them. Primates emerged during this chaos. The earliest known primate fossils date to around 55 million years ago. They were small, arboreal, probably similar to modern tree shrews or small lemurs. Nothing about them suggested future dominance. They were one evolutionary experiment among thousands. But they had certain advantages. Grasping hands with opposable digits, useful in trees. Forward-facing eyes providing depth perception, critical for judging distances when jumping between branches. Relatively large brains for their body size, though still tiny by modern standards. These weren't dramatic advantages. They didn't make primates dominant. They just made them viable in a particular ecological niche, the forest canopy. For tens of millions of years, that's where primates stayed. Up in the trees, eating fruits and insects, slowly diversifying. By the Oligocene, around 30 million years ago, there were monkeys and early apes. Still arboreal, still relatively small-brained, still just another group of mammals among many. The critical shift began much later, in Africa, probably around 7 to 6 million years ago. Climate change was driving it. Global temperatures were dropping, forests were fragmenting, and grasslands were expanding. Some primate populations found themselves spending more time on the ground, moving between scattered forest patches. Walking upright on two legs, bipedalism, offered advantages in this environment. It freed the hands for carrying food or tools. It allowed seeing over tall grass. It was more energy efficient for long-distance travel than quadrupedal knuckle walking. Natural selection began favoring individuals who were better at walking upright. This is where the human lineage begins to separate from other apes. Not with intelligence. Not with tool use. Those came later. The first defining characteristic of our lineage was simply the ability to walk efficiently on two legs. Fossils from this period are rare and fragmentary. We have Sahelanthropus, dated to about 7 million years ago, known from a partial skull. We have Ororan, about 6 million years old, known from a few bones suggesting upright walking. We have Ardipithecus, around 4.4 million years ago, definitely bipedal but still spending time in trees. These weren't humans. They were apes experimenting with a new way of moving. Their brains were still chimpanzee-sized, around 350 to 400 cubic centimeters. They probably didn't make complex tools. They lived in small groups in woodland environments. If you saw one, you wouldn't think that's going to evolve into something that dominates the planet. You'd think, interesting ape. Around 4 million years ago, a new genus appeared, Australopithecus. These were the first hominins to really commit to terrestrial life. They walked upright habitually, though their arms were still relatively long and they probably still climbed trees for safety and food. Their brains were slightly larger than earlier forms, maybe 400 to 500 cubic centimeters, but still well within ape range. The most famous Australopithecus fossil is Lucy, discovered in Ethiopia in 1974. She lived about 3.2 million years ago, stood roughly 1.1 meters tall, and weighed perhaps 30 kilograms. Her skeleton shows clear adaptations for bipedalism, a bull-shaped pelvis, a knee angle that kept her center of gravity over her feet, a forward-positioned foramen magnum where the spine connects to the skull. For over 1 million years, various Australopithecus species lived across eastern and southern Africa. They were successful animals, well adapted to their environments. But they were still fundamentally apes. They didn't build shelters, didn't control fire, didn't create complex tools. Then, around 2.8 million years ago, something shifted. We start finding stone tools in the archaeological record. Not sophisticated tools, just rocks deliberately chipped to create sharp edges. But this was new. This was technology, however primitive. The first species clearly associated with stone tool manufacture is Homo habilis, which appeared around 2.4 million years ago. Habilis means handy man, and it's an appropriate name. Their brains were larger than Australopithecus, around 600 cubic centimeters, and their hands show better precision grip. Still, Homo habilis wasn't dramatically different from earlier hominins. They were still small, probably around 1.3 meters tall. They probably still spent time in trees. Their tools, the so-called Oldowan industry, were simple, sharp flakes struck off larger rocks, useful for cutting meat or processing plant materials. What matters is the principle. Using tools isn't unique to humans, many animals use tools. But making tools, deliberately modifying objects to create something more useful, that's rarer. And passing that knowledge down through generations, that's rarer still. With stone tools, we see the first glimmers of culture, information transmission beyond genetics. Around 2 million years ago, a new species emerged, Homo erectus. This is where things get interesting. Erectus was taller, averaging around 1.8 meters. More importantly, their brains were substantially larger, ranging from 800 to over 1,000 cubic centimeters. They made more sophisticated tools, the Acheulean hand axes, carefully crafted teardrop-shaped implements that required planning and skill. And Homo erectus walked out of Africa. Fossils have been found in Georgia, China, Indonesia. This species, or closely related forms, spread across the Old World, adapting to environments from tropical forests to temperate grasslands. They likely controlled fire, though the evidence is debated. They hunted cooperatively. They may have had basic language. Homo erectus was successful. Incredibly successful. They lasted for over 1.5 million years, far longer than our species has existed so far. They were the first truly cosmopolitan hominin, the first to demonstrate that our lineage could adapt to wildly different environments. But they weren't modern humans. Their brains, while large, were still structured differently. Their skulls were thick-boned with prominent brow ridges. Their bodies were robust, built for strength rather than endurance running. They made the same basic tool types for hundreds of thousands of years with little innovation. What happens next is complicated. Between about 800,000 and 300,000 years ago, Homo erectus populations in different regions began diverging. In Africa, they evolved toward forms with more gracile skeletons and larger, rounder skulls. In Europe and Western Asia, they evolved into Neanderthals. In Eastern Asia, they became Denisovans and possibly other groups. The human family tree during this period wasn't a straight line. It was a bush, multiple species existing simultaneously, sometimes in the same regions. And they didn't stay isolated. Genetic evidence shows they interbred when they met. Neanderthals appeared around 400,000 years ago in Europe and Western Asia. They weren't brutish cavemen. That's Victorian mythology. Neanderthals had brains as large as or larger than modern humans, averaging around 1,400 cubic centimeters. They made sophisticated tools, controlled fire expertly, built shelters, buried their dead with apparent ritual. They survived ice ages in some of the harshest environments on Earth. They hunted mammoth and woolly rhinoceros. They may have made symbolic art, though the evidence is contested. They were formidable survivors. Denisovans are more mysterious. We know them primarily from DNA extracted from a few bone fragments found in a cave in Siberia. Genetic analysis shows they were distinct from both Neanderthals and modern humans, yet they interbred with both. Their genes persist in modern populations, particularly in Melanesia and Australia, suggesting they ranged across much of Asia. Meanwhile, in Africa, our direct ancestors were evolving. The earliest fossils that look anatomically modern, Homo sapiens, date to around 300,000 years ago. Sites in Morocco and Ethiopia show skulls with the rounded cranium, flat face, and small teeth characteristic of our species. But here's something crucial. Early Homo sapiens weren't behaviorally modern. For over 200,000 years, they made the same types of tools their ancestors did. They didn't create complex art. They didn't develop sophisticated symbolic culture. Anatomical modernity came first. Behavioral modernity took much longer. What changed? Around 70,000 years ago, something happens in the archaeological record. Suddenly we see evidence of symbolic thinking. Engraved ochre, shell beads used as ornaments, more complex tools made from bone and antler. This intensifies around 50,000 years ago. Cave paintings appear. Sculptures. Musical instruments. Elaborate burial practices. This is often called the Upper Paleolithic Revolution, though it's more of a gradual acceleration than a sudden shift. The key innovation was probably language. Not simple communication, but full syntactic language capable of expressing abstract concepts, discussing things not immediately present, telling stories about the past and planning for the future. Language transforms cognition. It allows information to accumulate across generations far more efficiently than imitation alone. It enables cooperation at scales impossible without it. Once language evolved, culture could evolve faster than biology. Around 60,000 years ago, modern humans began leaving Africa in significant numbers. They moved along coastlines into southern Asia, reaching Australia by around 50,000 years ago. They spread north into Europe, arriving around 45,000 years ago where they encountered Neanderthals. They pushed east across Asia, eventually crossing into the Americas, probably around 15 to 20,000 years ago. And everywhere they went, they replaced the existing hominin species. Neanderthals disappeared around 40,000 years ago. Denisovans vanished. Homo erectus, if any population still existed in remote areas, went extinct. Within a remarkably short time, geologically speaking, Homo sapiens became the only surviving human species on Earth. Why? What made us successful where other human species failed? It wasn't brain size. Neanderthals had brains as large as ours. It probably wasn't individual intelligence. A Neanderthal child raised in modern society would likely function normally. The advantage was social. Modern humans appear to have been better at cooperation in large groups, better at cultural transmission, better at innovation. Our tools became more sophisticated not because our brains suddenly got bigger, but because we shared information more efficiently. Each generation built on the previous one's knowledge. Neanderthals made essentially the same tools for 200,000 years. Modern humans went from stone tools to space stations in 50,000 years. That's not biological evolution. That's cultural evolution enabled by language and social structure. But here's the uncomfortable part. When modern humans and Neanderthals met, they didn't just peacefully coexist. Genetic evidence shows they interbred. Most non-African people today carry 1 to 2% Neanderthal DNA. Some carry Denisovan DNA as well. But those hybrids were absorbed into modern human populations, not the reverse. The Neanderthal genome essentially went extinct except for small fragments preserved in us. Whether this replacement was violent or not is debated. There's no clear evidence of warfare, no mass graves showing conflict. But absence of evidence isn't evidence of absence. What we know is this: when modern humans and Neanderthals occupied the same regions, Neanderthals disappeared within a few thousand years. Competition for resources probably played a role. If modern humans were even slightly more efficient hunters, slightly better at exploiting the environment, they would gradually outcompete other species. Disease might have been a factor. When previously isolated populations meet, pathogens can devastate the group with no immunity. Climate change probably contributed. The period between 50,000 and 40,000 years ago was climatically unstable, with rapid temperature swings. Species already stressed by environmental shifts would be more vulnerable to competition. Whatever the exact mechanism, the result was clear. By 30,000 years ago, we were alone. For the first time in millions of years, only one species of human walked the earth. That isolation is unusual in our lineage's history. For most of hominin evolution, multiple species coexisted. Australopithecus afarensis shared East Africa with Australopithecus ethiopicus and Kenyanthropus. Homo erectus lived alongside Homo habilis and Paranthropus. Neanderthals, Denisovans, and modern humans overlapped for tens of thousands of years. We're used to being the only humans, but it's a recent condition. Once alone, modern humans didn't stop evolving. Evolution never stops. Over the past 30,000 years, we've adapted to new diets, new climates, new diseases. Populations that adopted agriculture developed higher frequencies of genes for digesting lactose and processing starches. Populations in high altitudes evolved better oxygen utilization. Populations in different latitudes evolved varying levels of skin pigmentation to balance vitamin D production against UV radiation damage. These are minor changes, nothing approaching speciation. But they're real. The human species isn't static. We're still evolving, though cultural change now vastly outpaces biological change. And then something unprecedented happened. Around 12,000 years ago, humans began deliberately cultivating plants and domesticating animals. Agriculture emerged independently in multiple locations: the Fertile Crescent, China, Mesoamerica, the Andes, Sub-Saharan Africa. This wasn't progress in any moral sense. Early agriculture was hard work, probably harder than hunting and gathering. It led to worse nutrition, more disease, social inequality. But it allowed denser populations. Agricultural societies could support more people per square kilometer than hunter-gatherers. Numbers matter in competition. Agricultural populations grew and spread, absorbing or displacing hunter-gatherer groups. With agriculture came permanent settlements, then cities, then civilization with all its benefits and horrors. Writing appeared around 5,000 years ago, enabling information storage beyond individual memory. Suddenly knowledge could accumulate without loss between generations. Science became possible, systematic investigation and recording of natural phenomena. Technology accelerated. We went from bronze to iron to steel. From animal power to steam to electricity to nuclear energy. From signal fires to telegraph to internet. The pace of change became exponential. A human from 10,000 years ago, transported to 5,000 years ago, would find the world different but comprehensible. A human from 5,000 years ago transported to today would think they'd entered a realm of magic. Yet biologically, we're nearly identical to humans from 50,000 years ago. Our brains haven't changed significantly in size or structure. What's changed is culture, accumulated knowledge passed down and built upon. We're not smarter than our ancestors. We just know more. A Paleolithic human with their brain intact, raised in modern society, would function normally. They'd learn language, mathematics, technology just like anyone else. The hardware hasn't upgraded much. The software has exploded. This is why the human story is so strange. For most of our history, we evolved like every other species, through random mutation and natural selection, slowly adapting to changing environments. Then culture took over. We began shaping our environment rather than being shaped by it. We created new selection pressures. We moved into environments we weren't adapted for and invented technologies to survive there. We are now the primary force shaping Earth's biosphere, whether we intended that or not. And that brings us to now. 7.8 billion humans covering the planet, living in environments from Antarctic research stations to space stations orbiting above. We've eliminated smallpox. We've split the atom. We've walked on the moon. We've sequenced our own genome and begun editing it. The question becomes, what happens next? We're standing at a junction unlike any species has ever encountered. For the first time in Earth's history, one organism has the capacity to consciously direct its own evolution and reshape the planet's entire biological future. That's not metaphor. That's measurable reality. The last century alone has altered Earth more than the previous 10,000 years combined. We've moved more sediment than all natural erosion processes. We've changed atmospheric chemistry faster than any geological event except major asteroid impacts. We've created materials that will persist in the geological record for millions of years. Plastic, concrete, radioactive isotopes from nuclear testing. Future geologists will identify a distinct layer marking our presence, a boundary as clear as the one separating dinosaurs from mammals. Population growth has been exponential. It took all of human history until 1804 to reach 1 billion people. We hit 2 billion by 1927, 3 billion by 1960, 4 billion by 1974. The curve keeps climbing, though growth rates are finally slowing in developed nations. Current projections suggest we'll peak somewhere between 10 and 11 billion before stabilizing or declining. That's assuming current trends continue, which is never guaranteed. Resource consumption has grown even faster than population. The average person today uses more energy, more water, more materials than at any point in history. This creates obvious problems. Fossil fuels that took hundreds of millions of years to form are being burned in centuries. Aquifers that filled over millennia are being drained in decades. Topsoil that accumulated over thousands of years is eroding in generations. These aren't sustainable trajectories. Something has to change. Climate change is the most visible consequence. By burning fossil carbon and releasing it into the atmosphere, we've increased CO2 concentrations from about 280 parts per million before industrialization to over 420 today. That's higher than any point in the last 3 million years. The greenhouse effect is basic physics. More CO2 means more trapped heat. Global average temperatures have risen about 1.2 degrees Celsius since pre-industrial times. That sounds small until you realize it's an average across the entire planet, oceans included. Land temperatures have risen more. Arctic temperatures have risen much more. The effects cascade. Ice sheets melt. Sea levels rise. Weather patterns shift. Ecosystems that evolved under specific temperature ranges suddenly face conditions they're not adapted for. Species migrate toward the poles or higher altitudes, seeking familiar climates. Those that can't migrate fast enough face extinction. Current extinction rates are estimated at 100 to 1,000 times the background rate. We're in the opening phase of Earth's sixth mass extinction, and we're causing it. But here's what makes this different from previous extinctions. We know it's happening. We can measure it. We can model future scenarios. And we have the technological capacity to respond. Whether we actually will is a separate question, one that depends on economics, politics, human psychology, factors far outside the scope of geology or biology. The science is clear. The response is uncertain. Technology continues accelerating. Artificial intelligence is advancing faster than most predicted. Quantum computing is moving from theory to application. Genetic engineering has progressed from science fiction to routine laboratory procedure. CRISPR allows precise editing of DNA sequences. We've already used it to cure genetic diseases in individual patients. We're discussing using it for enhancement, not just therapy. The boundary between treating illness and improving capability is philosophically blurry and getting blurrier. Space exploration has resumed after decades of relative stagnation. Private companies are launching rockets that land themselves. Plans exist for permanent lunar bases and crewed missions to Mars within the next 2 decades. These aren't fantasies anymore. They're engineering projects with timelines and budgets. If humanity becomes multiplanetary, that changes the equation entirely. No single catastrophe could end our species. That's never been true before. Synthetic biology is creating organisms with no natural counterpart. Bacteria engineered to produce insulin. Yeast modified to generate spider silk proteins. Algae designed to capture carbon more efficiently than natural photosynthesis. We're not just modifying existing life anymore. We're designing new life from scratch. The implications are staggering and largely unexplored. Meanwhile, we still carry the legacy of our evolutionary past. Our brains evolved for small group dynamics, not global civilization. We're wired to respond to immediate threats, not slow-moving catastrophes like climate change. We form tribal identities easily, treating outsiders with suspicion or hostility. We're susceptible to cognitive biases that served us well in the Paleolithic but cause problems now. Confirmation bias. Availability heuristic. Tribalism. These aren't bugs in human psychology. They're features that increased survival in ancestral environments. They just don't match the challenges we face today. Social media has amplified these tendencies. Algorithms optimized for engagement end up promoting outrage and polarization because those emotions drive clicks. Information spreads faster than ever, but misinformation spreads just as fast. We have access to more knowledge than any previous generation, but also more noise. Distinguishing signal from noise requires skills our education systems haven't caught up with yet. The question of artificial intelligence deserves separate consideration. If we create machines that match or exceed human intelligence, what happens next? Do they remain tools we control? Do they become partners we collaborate with? Do they replace us entirely? Nobody knows. The trajectory is unclear because we're still debating what intelligence actually means and how consciousness emerges. These aren't just technical questions. They're philosophical ones with no obvious answers. Some argue we're approaching a technological singularity, a point where change happens so rapidly that prediction becomes impossible. Others think that's overblown speculation. What's certain is that the next century will differ from the last more than the last differed from the one before it. Extrapolating current trends is probably futile. Surprises are guaranteed. Humanity's future branches into scenarios wildly different from each other. In optimistic projections, we solve climate change through renewable energy and carbon capture. We cure aging through genetic medicine and cellular repair. We spread throughout the solar system, then beyond. We merge with our technology, enhancing our capabilities far beyond biological limits. We become something new, something that would be unrecognizable to our ancestors but still carries forward the core of what we are. In pessimistic scenarios, we fail to address existential risks. Climate change triggers cascading ecosystem collapses. Resource wars destabilize global civilization. A pandemic worse than COVID-19 spreads before we can respond. Nuclear weapons are used in regional conflicts that spiral out of control. Artificial intelligence is developed without adequate safety measures. Any of these could dramatically reduce human population or technological capacity, potentially permanently. Most likely, the future lies somewhere between extremes. Muddy. Complicated. Neither utopia nor apocalypse, but a messy continuation of what we've always done, solving problems while creating new ones, advancing in some areas while regressing in others. That's been the human pattern for millennia. No reason to expect it to change now. What we can say with confidence is this: the story that began with single cells in ancient oceans, that continued through the Cambrian explosion and the colonization of land, that survived 5 mass extinctions and countless smaller catastrophes, that produced dinosaurs and mammals and eventually us, that story isn't over. It's still being written. We're writing it now, whether we realize it or not. Every choice we make, individual and collective, shapes what comes next. 4 billion years of evolution produced a species capable of understanding its own origins, of reconstructing the deep history of life on this planet, of recognizing its place in the vast sweep of biological time. That understanding changes nothing about the facts themselves. The rocks don't care if we study them. The fossils don't care if we interpret them correctly. But it changes us. Knowing where we came from affects how we think about where we're going. We are not separate from nature. We are nature, evolved through the same processes as every other organism, subject to the same physical and chemical laws. Our intelligence, our technology, our civilization, all of it emerged from natural processes operating over deep time. We're not above the system. We're part of it. An unusual part, granted, one with unprecedented impact. But still part of the same system that produced stromatolites and trilobites and Tyrannosaurus and every other form life has ever taken. The Earth will continue with or without us. Life survived worse than anything we can do short of physically destroying the planet. After we're gone, whether that's 1,000 years from now or 1,000,000, evolution will continue. New species will emerge. Ecosystems will reorganize. The biosphere will persist in some form until the sun expands and sterilizes the surface in about 1 billion years. That's the timeline we're working with. Our impact will be measurable in the geological record, a thin layer marking the Anthropocene, the age when one species briefly dominated the planet's systems. What that layer will show depends on what we do next. Whether it records a mass extinction followed by recovery, or marks a transition to something genuinely new, or represents a boundary after which the trajectory of life on Earth changed permanently, that's still being determined. The story continues. We're living in the latest chapter, writing it in real time. What happens next isn't predetermined. It depends on choices we haven't made yet, technologies we haven't invented, problems we haven't solved. The deep past teaches us that life adapts, persists, transforms. The future remains open. Looking back across this immense span of geological time reveals something unsettling. The Permian extinction wasn't an isolated anomaly. It was part of a pattern that's repeated throughout Earth's history. Life builds complexity over millions of years, ecosystems stabilize, species diversify, and then something shatters it all. The planet resets. What survives isn't necessarily what deserves to survive by any moral standard. It's what happens to have the right traits at the right moment. The survivors of the Permian weren't superior organisms. They were lucky. Small size, low metabolic rates, generalist diets, these traits meant nothing special in stable times. They became everything when conditions turned hostile. The same principle applies to every mass extinction. The traits that ensure survival during catastrophe are often useless or even disadvantageous during normal times. Evolution doesn't prepare for disasters. It can't. Natural selection optimizes for current conditions, not hypothetical future ones. This creates a fundamental vulnerability in complex ecosystems. The more specialized organisms become, the more efficient they are at exploiting their specific niches, the more fragile they become when those niches disappear. The Permian Ocean was full of highly specialized filter feeders, predators adapted to specific prey, organisms with complex life cycles requiring stable conditions. When the chemistry changed and oxygen vanished, that specialization became a death sentence. The generalists, the unspecialized, the organisms doing moderately well at many things rather than excelling at one thing, they persisted. We see echoes of this pattern in modern conservation biology. Species with narrow habitat requirements, specialized diets, small populations, those are the ones going extinct first as humans alter the planet. Generalist species, rats, crows, coyotes, cockroaches, they're thriving. Not because they're better in any absolute sense, but because they're flexible. When environments change rapidly, flexibility matters more than optimization. The Permian extinction also demonstrates how interconnected Earth's systems are. The volcanic eruptions didn't directly kill most organisms. They triggered cascading failures. Atmospheric changes led to ocean warming. Ocean warming caused oxygen depletion. Oxygen depletion enabled hydrogen sulfide production. Hydrogen sulfide poisoned the remaining life. Each step amplified the previous one. The system had feedback loops that, once triggered, became self-reinforcing. The planet wasn't just damaged. It was actively hostile, generating conditions that prevented recovery. Modern climate change shows similar dynamics. We're not just warming the atmosphere. We're acidifying oceans, disrupting circulation patterns, melting ice that reflects sunlight, thawing permafrost that releases more greenhouse gases. Each change triggers others. The system has tipping points where positive feedback loops take over and changes become self-sustaining regardless of what triggered them initially. The Permian shows what happens when those loops engage fully. It took millions of years for the planet to stabilize. But here's what the Permian extinction ultimately proves. Life doesn't give up easily. Even when 96% of species vanish, when the oceans turn toxic and the atmosphere becomes nearly unbreathable, when the planet seems utterly hostile to complex organisms, life finds a way. Not through any mystical force or intention. Through sheer probability. With enough individual organisms, enough genetic diversity, enough geographic spread, some will survive almost anything. And from those survivors, complexity eventually rebuilds. The recovery wasn't immediate or smooth. It took fits and starts, false recoveries followed by setbacks, millions of years of ecological simplicity before the biosphere regained its previous complexity. But it happened. The Triassic world that emerged was different from the Permian world that died, but it was just as complex, just as diverse. Different players, different rules, same fundamental processes. That's the pattern visible across all of Earth's history. Destruction, survival, recovery, diversification. The specific organisms change. The underlying dynamics don't. Life as a planetary phenomenon is remarkably resilient. Individual species, even entire families or orders, are expendable. The system continues. Which brings us back to our current situation. We're changing the planet faster than any species except possibly some ancient photosynthetic bacteria billions of years ago. We're driving extinction rates to levels comparable with the worst events in geological history. We're altering ocean chemistry, atmospheric composition, global temperatures. The parallels to the Permian are uncomfortable and increasingly obvious. The difference is awareness. The organisms dying in the Permian had no comprehension of what was happening. They just lived and died according to their biology while the world became increasingly hostile. We know. We can measure the changes in real time. We can model future trajectories. We can, in principle, alter our behavior to avoid the worst outcomes. Whether we actually will remains the defining question of our era. The Permian extinction teaches us that planetary systems have limits. Push them hard enough and they break in ways that are catastrophic, long-lasting, and affect everything alive. It also teaches us that recovery is possible but measured in geological time scales that are meaningless to individual organisms or even entire species. The planet will be fine eventually. The question is whether we'll be around to see it. The survivors of the Permian were small, unspecialized organisms hiding in refuges. That's probably not the future most humans envision for themselves. Earth's history is written in stone, in fossils, in chemical signatures left by organisms dead for hundreds of millions of years. Those records don't lie. They show a planet that cycles through periods of stability and catastrophe with reliable regularity. They show that dominance is temporary, that no group remains on top forever, that the traits ensuring success in one era become liabilities in the next. They show that life persists but individual lineages don't. Everything alive today descends from survivors of previous catastrophes. Everything alive today is temporary, including us. The Permian was Earth's deadliest catastrophe, but it wasn't the last. It won't be the last. The planet will experience future disruptions, whether from volcanic activity, asteroid impacts, or slower processes we haven't identified yet. Over geological timescales, catastrophe is normal. Stability is the anomaly. We evolved during an unusually stable period and built a civilization assuming that stability would continue indefinitely. The deep past suggests that's optimistic. What we do with this knowledge is up to us. We can recognize our place in Earth's long history, acknowledge that we're subject to the same rules as every other organism, and act accordingly. Or we can assume we're somehow exempt, that our technology makes us immune to planetary-scale disruptions, that the patterns visible across billions of years somehow don't apply to us. The rocks suggest otherwise. The fossils suggest otherwise. Every previous dominant group thought it would last forever. None did. We're not special in that regard. We're just the current experiment, playing out in real time, with an ending yet to be determined. The planet you're standing on right now has died and been reborn more times than you can imagine. 252 million years ago, Earth crossed a threshold so catastrophic that 9 out of every 10 species simply vanished. What came after wasn't recovery. It was reinvention. The Triassic period emerged from that apocalypse, and the creatures that rose to fill the silence were unlike anything that had come before. This wasn't the age of dinosaurs yet. Not really. This was something stranger, more experimental, more desperate. Life was figuring itself out again from scratch, and the results were terrifying. At the dawn of the Triassic, Earth resembled a planet-sized wound trying to heal. The supercontinent Pangaea stretched from pole to pole, a single massive landmass surrounded by the Panthalassa Ocean. There were no ice caps. No polar bears waiting at the ends of the Earth. Just endless desert sprawling across the interior, where temperatures could spike beyond what most modern animals could survive. The Permian-Triassic extinction had just torn through the biosphere like a cosmic eraser. Volcanic eruptions in what's now Siberia had pumped gigatons of carbon dioxide and sulfur into the atmosphere for hundreds of thousands of years. The oceans acidified. Oxygen levels plummeted. Even insects, those nearly indestructible survivors, were pushed to the brink. So when life finally crawled back, it did so cautiously. The early Triassic was a shadow of what had been. Ecosystems were simple, almost primitive. Small reptiles and amphibians dominated, not because they were superior, but because they were what remained. Lystrosaurus, a pig-sized herbivore with a turtle's beak, made up roughly 95% of land vertebrates. Imagine a world where nearly every animal you encounter is the same species. That's how depleted Earth had become. But survival has a way of breeding innovation. As carbon dioxide levels stayed elevated and the planet remained hot, something unexpected happened. Life didn't just recover. It exploded into forms that had never existed before. The Middle Triassic saw the emergence of entirely new body plans, new strategies, new predators. And among them were the archosaurs, the ruling reptiles that would dominate for the next 150 million years. These weren't the archosaurs you're picturing. Not yet. Early forms like Euparkeria were small, maybe a meter long, with long tails and sprawling limbs. But they had something critical, an ankle joint that allowed more efficient movement, a more upright stance. This wasn't just anatomy. It was potential. While archosaurs were finding their footing, another group was already thriving. The cynodonts, distant cousins of modern mammals, were diversifying rapidly. They had differentiated teeth, whiskers, possibly even fur. Some paleontologists believe they were warm-blooded, a massive advantage in the volatile Triassic climate. These creatures weren't dominant, but they were persistent, occupying niches that larger predators ignored. Then there were the temnospondyls, massive amphibians that refused to give up their aquatic dominance. Mastodonsaurus could reach lengths of 6 meters, with a skull alone stretching over a meter. These weren't the frogs and salamanders you know. They were apex predators in rivers and lakes, crushing prey with bone-shattering jaws. But the real story of the Triassic isn't about who survived. It's about what they became. By the late Triassic, the world had changed again. Pangaea was beginning to fracture, though it would take millions more years to fully split apart. Rainfall increased in some regions, turning barren deserts into lush forests of conifers, ferns, and cycads. With more vegetation came more herbivores. And with more herbivores came larger, more sophisticated predators. This is when the monsters arrived. Postosuchus stalked the landscape of what's now North America, a quadrupedal predator built like a crocodile but acting like a wolf. For meters long, with powerful jaws and serrated teeth, it was an apex hunter, perfectly adapted to ambush prey in forested environments. Postosuchus wasn't a dinosaur. It was a Rauisuchian, part of that broader archosaur family that was experimenting with dominance. And it wasn't alone. Saurosuchus prowled South America, even larger, reaching up to 9 meters. These creatures moved on all fours but could rear up on their hind legs when attacking, combining power with flexibility. Their skulls were massive, reinforced to withstand the stress of crushing bone. They were, in every functional sense, the top of the food chain. Here's the strange part. These apex predators weren't dinosaurs, and they weren't destined to become dinosaurs. They were a separate lineage, one that would eventually go extinct. But for tens of millions of years, they ruled. Dinosaurs during this time were smaller, less specialized, still figuring out their niche. They weren't the kings yet. They were the understudies. So what were the early dinosaurs doing? Eoraptor, one of the earliest known dinosaurs, was about the size of a dog. It lived in what's now Argentina around 231 million years ago. Eoraptor had a lightweight frame, grasping hands, and a diet that was probably omnivorous. It wasn't dominating anything. It was surviving, adapting, learning. Herrerasaurus was another early dinosaur, slightly larger, more predatory. It had a flexible jaw that allowed it to grip struggling prey, a feature that would become more refined in later theropods. But even Herrerasaurus wasn't at the top. It coexisted with much larger predators, avoiding direct competition by targeting smaller animals. What's fascinating is that dinosaurs during the Triassic weren't inevitable. There was no sign they'd eventually take over. They were one experiment among many. Crocodile relatives were larger, more successful. Mammal ancestors were more adaptable. Dinosaurs were just another group trying to make it work. Then something shifted. The late Triassic brought another wave of extinction, smaller than the Permian catastrophe but significant. Volcanic activity surged again, this time associated with the breakup of Pangaea. Climate became more unpredictable. Sea levels fluctuated wildly. And in that chaos, many of the dominant groups faltered. Rauisuchians began to decline. Large amphibians lost ground. But dinosaurs, with their more efficient respiratory systems, upright posture, and flexible diets, started expanding. Not overnight. Not in some dramatic takeover. Just slowly, persistently, filling gaps as other groups weakened. By the end of the Triassic, dinosaurs were no longer marginal. They were ascending. Plateosaurus appeared in the late Triassic, one of the first large herbivorous dinosaurs. It could reach lengths of up to 10 meters and weighed several tons. Plateosaurus was a prosauropod, a precursor to the giant sauropods that would later dominate the Jurassic. It moved on all fours but could rear up on its hind legs to reach high vegetation, a body plan that hinted at future gigantism. And then there was Coelophysis, a small, agile carnivore that hunted in packs. Fossil sites in New Mexico have revealed dozens of Coelophysis skeletons together, suggesting social behavior. These weren't solitary killers. They were coordinated, adaptable, capable of taking down prey much larger than themselves through cooperation. This is the pattern that defines the Triassic. Life wasn't dominated by a single strategy. It was a chaotic competition of body plans, metabolisms, and survival tactics. Every group had a chance. Every lineage was testing the limits of what was possible. But there's another layer to this story, one that's often overlooked. The Triassic wasn't just about land. The oceans were undergoing their own transformation. Marine reptiles exploded in diversity during this period. Ichthyosaurs, dolphin-like predators, evolved from land-dwelling ancestors and returned to the sea, developing streamlined bodies, powerful tails, and sharp teeth for catching fish. Some species grew to over 15 meters in length. They weren't fish. They were air-breathing reptiles that had fully committed to an aquatic lifestyle, a transition that happened remarkably fast in evolutionary terms. Nothosaurs patrolled coastal waters, smaller than ichthyosaurs but equally adapted. They had webbed feet, long necks, and needle-like teeth for snagging slippery prey. These creatures occupied the shallow marine environments, hunting in estuaries and lagoons where the boundary between land and sea blurred. And beneath them, in the deeper waters, placodont's grazed on shellfish. These bizarre reptiles had flat, crushing teeth designed to crack open mollusks. Some species developed turtle-like shells, armored protection against the increasing number of marine predators. The Triassic oceans were becoming crowded, competitive, and dangerous. Just like on land, the rules were being rewritten. Predators were getting faster. Prey was getting smarter. And every evolutionary innovation triggered a counter-response. This is what makes the Triassic so critical. It's not just a prelude to the age of dinosaurs. It's the laboratory where modern ecosystems were forged. The Triassic tested carnivory, herbivory, gigantism, pack hunting, marine adaptation, and dozens of other strategies. Most failed. A few succeeded. And those successes shaped everything that followed. And then it ended. Not gradually. Not through slow decline. The Triassic closed with another mass extinction around 201 million years ago, erasing roughly 70 to 80% of terrestrial species. Volcanic eruptions associated with the breakup of Pangaea released massive amounts of carbon dioxide. Global temperatures spiked. Ocean acidification returned. Ecosystems that had stabilized after the Permian were shattered once more. The difference this time was what survived. Dinosaurs made it through. Most of their competitors did not. Rauisuchians vanished completely. Large amphibians were decimated. Many marine reptile lineages disappeared. When the dust settled, the playing field had been cleared. The Jurassic period began around 200 million years ago, and for the first time, dinosaurs weren't just participants. They were dominant. This is where the popular image of prehistory begins to take shape. Giant sauropods grazing on towering conifers. Massive predators stalking through dense forests. But the reality was more nuanced than the simplified picture we often see. The early Jurassic wasn't an instant explosion of giants. It was a gradual expansion. Dinosaurs diversified into nearly every terrestrial niche. Some became enormous. Others stayed small. Some hunted alone. Others moved in herds. The key advantage dinosaurs possessed was efficiency. Their upright stance meant less energy wasted on locomotion. Their respiratory systems, with air sacs that allowed continuous airflow through the lungs, provided more oxygen per breath than mammalian lungs could manage. This wasn't a minor edge. It was fundamental. It allowed dinosaurs to sustain activity levels that other groups couldn't match, especially at larger sizes. By the Middle Jurassic, sauropods had grown truly massive. Brachiosaurus stood over 13 meters tall and weighed as much as 50 tons. Its long neck allowed it to browse vegetation that no other herbivore could reach, creating a feeding strategy that minimized competition. Diplodocus stretched even longer, reaching lengths of up to 30 meters, though much of that was tail. These weren't clumsy, slow-moving creatures. Recent biomechanical studies suggest sauropods could move at reasonable speeds, and their tails functioned as effective defensive weapons. A full-force tail strike from a diplodocus could shatter bone. Predators had to adjust. Allosaurus emerged as one of the dominant carnivores of the late Jurassic. At around 9 meters long and weighing up to 2 tons, Allosaurus wasn't the largest predator ever, but it was built for efficiency. Sharp, serrated teeth designed to tear flesh. Powerful forelimbs with large claws. A skull structure that allowed it to deliver slashing bites rather than crushing ones. Fossil evidence shows Allosaurus targeted sauropods, despite the size difference. Bite marks on sauropod bones match Allosaurus teeth. Some researchers suggest pack hunting, though the evidence remains debated. What's clear is that Allosaurus didn't need to bring down a full-grown sauropod alone. Juveniles, sick individuals, or isolated stragglers would have been easier targets. One successful kill could feed a predator for weeks. But not every dinosaur followed the path toward gigantism. Compsognathus, a contemporary of Allosaurus, was chicken-sized. Fast, agile, likely warm-blooded or at least capable of maintaining elevated body temperatures. It hunted insects, small lizards, and early mammals. Compsognathus represents the other end of the spectrum. Size wasn't everything. Speed and adaptability mattered just as much. The Jurassic also saw the rise of stegosaurs. Stegosaurus itself, with its distinctive double row of plates along its back and spiked tail, has become one of the most recognizable dinosaurs. But those plates weren't armor. They were likely thermoregulatory structures, helping control body temperature through blood flow. The real defense was the tail. For long spikes arranged in a cluster, capable of being swung with devastating force. Fossil evidence shows at least one Allosaurus died from a Stegosaurus tail wound. Penetrated vertebrae. Fatal injury. This wasn't prey waiting passively to be eaten. This was a creature that could fight back effectively. Meanwhile, in the skies above, pterosaurs were diversifying. These weren't dinosaurs, but archosaurs, a related group that had taken a different evolutionary path. Pterosaurs ranged from sparrow-sized insectivores to massive gliders with wingspans exceeding 10 meters. Pteranodon, though technically from the later Cretaceous, represents the culmination of this lineage. But even in the Jurassic, pterosaurs like Rhamphorhynchus were highly successful. Long tails for stability, sharp teeth for catching fish, membranes stretched between elongated fingers forming wings. Flight had evolved independently multiple times in Earth's history, but pterosaurs were the first vertebrates to truly master it. And then there's Archaeopteryx. Discovered in Germany in 1861, Archaeopteryx is one of the most famous transitional fossils ever found. It had feathers, clearly visible in the fossil impressions. It had wings. But it also had teeth, claws on its wings, and a long bony tail. Was it a bird? Was it a dinosaur? The answer is both. Archaeopteryx represents the evolutionary bridge between non-avian dinosaurs and modern birds. It couldn't fly like a modern bird. Its flight muscles were weaker, its wings less refined. But it could glide, possibly flap for short bursts. And that was enough. Flight didn't emerge fully formed. It evolved incrementally, each small improvement providing a slight advantage. Archaeopteryx lived around 150 million years ago, in the late Jurassic. By that point, feathers had already been around for millions of years, originally evolving for insulation or display rather than flight. Flight was a secondary adaptation, a repurposing of existing structures. This pattern repeats throughout evolution. Features evolve for one reason, then get co-opted for another. Feathers for warmth became feathers for flight. Fins for stability became limbs for walking. Evolution doesn't plan ahead. It tinkers with what's already there. The Jurassic world wasn't static. Climates shifted. Sea levels rose and fell. Pangea continued breaking apart, creating new coastlines, new ocean currents, new weather patterns. As continents separated, populations became isolated. Species that once could migrate freely were now cut off. This drove further diversification. Different environments selected for different traits. Dinosaurs in what would become North America evolved differently from those in Europe, Africa, or Asia. By the end of the Jurassic, around 145 million years ago, the stage was set for an even more dramatic period. The Cretaceous was approaching, an era that would see dinosaurs reach their absolute peak in size, diversity, and ecological dominance. But it would also be their last. Before we get there, though, there's something else worth examining. While dinosaurs dominated the land and pterosaurs ruled the air, life in the oceans was undergoing its own revolution. Marine reptiles had filled nearly every aquatic niche. Ichthyosaurs continued their reign as fast-swimming predators. But they were joined by plesiosaurs, creatures with long necks, small heads, and 4 powerful flippers. Plesiosaurs weren't fast swimmers. They were ambush predators, using their necks to dart forward and snatch fish. Some species had necks longer than their bodies, an adaptation that seems almost absurd until you consider the hunting strategy. Slow approach, sudden strike. And then there were the pliosaurs, the short-necked relatives of plesiosaurs. These were the apex predators of the Jurassic seas. Liopleurodon, though often exaggerated in popular media, was still a formidable hunter. Estimates put it at around 7 meters long with a bite force comparable to modern saltwater crocodiles. It fed on large fish, other marine reptiles, and possibly even smaller plesiosaurs. The oceans were just as competitive as the land. Every advantage mattered. Every weakness was exploited. The Jurassic represents a peak in biological experimentation. Dinosaurs had proven their dominance on land. Pterosaurs owned the skies. Marine reptiles controlled the seas. Mammals still existed, but they were small, nocturnal, and largely irrelevant to the larger story unfolding around them. Yet those mammals were learning, evolving, waiting. The Jurassic ended not with a catastrophe but with a transition. Climates continued shifting. New species emerged. Old ones faded. And as the Cretaceous began, the world entered the final act of the dinosaur era. The Cretaceous period began around 145 million years ago. It would last for 79 million years, making it the longest period of the Mesozoic era. And during that time, dinosaurs reached their absolute zenith. This wasn't just more of the same. The Cretaceous brought new families, new body plans, new extremes. Sauropods grew even larger. Theropods became more specialized. Herbivores developed unprecedented defenses. The arms race between predator and prey intensified to levels never seen before or since. One of the defining features of the Cretaceous was the rise of flowering plants. Angiosperms appeared around 130 million years ago and spread rapidly. Before this, the world was dominated by ferns, conifers, and cycads. Flowering plants changed everything. They grew faster, reproduced more efficiently, and offered new food sources. Herbivorous dinosaurs adapted. New species evolved specifically to exploit these plants. Hadrosaurs, the duck-billed dinosaurs, became incredibly diverse during this time. They had complex dental batteries, hundreds of tiny teeth packed together, perfect for grinding tough plant material. Some species developed elaborate crests on their heads, hollow structures that likely amplified sound. These weren't just for display. They were communication tools. Hadrosaurs lived in herds, and being able to signal across distances was crucial for survival. Ceratopsians also flourished. Triceratops is the most famous, but it was just one of many. These dinosaurs had massive frills and horns, features that served both defensive and social purposes. The frills weren't solid bone. They had large openings covered by skin, which reduced weight. This suggests they weren't purely defensive. Display mattered. Intimidation mattered. In a world full of predators, looking dangerous could be just as important as actually being dangerous. And the predators? They were more lethal than ever. Tyrannosaurus rex appeared late in the Cretaceous, around 68 million years ago. It's often called the ultimate predator, and for good reason. Rex could grow up to 13 meters long and weigh over 8 tons. Its bite force has been estimated at over 12,000 pounds, strong enough to crush bone. But size wasn't its only advantage. Recent studies suggest T. Rex had excellent vision, a keen sense of smell, and could move surprisingly fast for its size. Estimates range from 17 to 25 miles per hour. Not cheetah fast, but fast enough to run down most prey. T. Rex also had tiny arms, a feature that's been mocked endlessly. But those arms weren't useless. They were heavily muscled and could lift several hundred pounds. Their function is still debated. Gripping prey during feeding, helping the animal stand after resting. We don't know for sure. What we do know is that T. Rex didn't need them for hunting. Its jaws did all the work. Other theropods took different paths. Spinosaurus, living around 95 million years ago in what is now North Africa, was possibly the largest theropod ever. Some estimates put it at 15 meters long. It had a massive sail on its back, formed by elongated vertebrae. The purpose of this sail is still debated. Thermoregulation, display, fat storage, all are possible. But what's most striking about Spinosaurus is its lifestyle. Unlike most theropods, it was semi-aquatic. Its teeth were conical, better suited for catching fish than tearing flesh. Its nostrils were positioned high on its skull, allowing it to breathe while partially submerged. Fossil evidence suggests it spent significant time in water, hunting large fish and possibly smaller dinosaurs that came to drink. This adaptability is key. Dinosaurs weren't locked into rigid roles. They experimented. They adapted. They filled niches that hadn't existed before. The Cretaceous also saw the rise of the dromaeosaurs, the raptors. The Velociraptor is the most famous, though popular media gets it wrong. The real Velociraptor was about the size of a turkey, not the human-sized monster from movies. But it was still a formidable predator. It had a large sickle-shaped claw on each foot, used for gripping and slashing. Its arms were long and flexible, with three-fingered hands capable of grasping prey. And it likely hunted in packs, coordinating attacks on larger animals. This level of social behavior suggests intelligence, at least relative to other dinosaurs. Larger dromaeosaurs did exist. Deinonychus, discovered in Montana, was around 3 meters long and weighed up to 70 kilograms. Utahraptor was even bigger, possibly reaching 7 meters and weighing half a ton. These weren't just scavengers. They were active hunters, using speed, coordination, and those devastating claws to bring down prey. Meanwhile, in the skies, pterosaurs reached their largest sizes ever. Quetzalcoatlus, appearing in the late Cretaceous, had a wingspan of up to 11 meters. That's wider than most small planes. It likely weighed around 200 kilograms, though some estimates go higher. How did something that large fly? Its bones were hollow and incredibly light. Its wings were made of a flexible membrane stretched between elongated finger bones. It probably spent more time gliding than flapping, riding air currents like modern albatrosses. What did it eat? Fossil evidence suggests fish, small dinosaurs, and carrion. It may have stalked shorelines, using its long neck to probe for prey. The oceans, too, were dominated by giants. Mosasaurs have replaced earlier marine reptiles as the top predators. These weren't dinosaurs. They were marine lizards, relatives of modern monitor lizards. The largest species, Mosasaurus hoffmanii, could reach 17 meters long. They had powerful jaws lined with sharp teeth, adapted for gripping slippery prey. They fed on fish, sharks, sea turtles, and even other mosasaurs. Bite marks on fossils show they weren't gentle. They were aggressive, dominant hunters. But the Cretaceous wasn't just about size. It was about diversity. Ecosystems became more complex. Food webs deepened. Interactions between species became more nuanced. Herbivores developed better defenses. Predators developed better attacks. Plants evolved chemical defenses, tough leaves, and toxic compounds. Herbivores evolved better digestion, detoxification systems, and behavioral strategies. This is coevolution in action. Each side pushes the other to adapt. Neither can afford to stop. And through all of this, the continents continued drifting. By the late Cretaceous, the world looked more recognizable. South America and Africa were fully separated. India was an island continent, drifting northward toward Asia. North America and Europe were still connected intermittently by land bridges, but the Atlantic Ocean was widening. These geographic changes had biological consequences. Populations isolated on different continents evolved independently. South American dinosaurs looked different from Asian ones. African species had their own unique traits. This geographic isolation drove further diversification. Climate during the Cretaceous was warmer than today. There were no polar ice caps. Sea levels were high, flooding low-lying areas and creating shallow inland seas. Forests extended into polar regions. Dinosaurs lived in Antarctica, which at the time was temperate, not frozen. This greenhouse climate was driven by high atmospheric carbon dioxide, likely from volcanic activity. The breakup of Pangaea created new volcanic zones, new mountain ranges, new sources of CO2. The planet was warmer, wetter, and more dynamic than at any point in the Mesozoic. But warmth doesn't mean stability. The Cretaceous experienced its own fluctuations. Ocean circulation patterns changed. Regional climates shifted. Sea levels rose and fell. These changes weren't catastrophic, but they were constant. Species had to adapt continuously. Those that couldn't went extinct. Turnover rates were high. New species appeared, old ones vanished. Evolution never stopped. Toward the end of the Cretaceous, around 70 million years ago, something else was happening. Volcanic activity was increasing. The Deccan Traps in what is now India began erupting, releasing massive amounts of lava and gas. These eruptions would continue for hundreds of thousands of years, pouring out enough lava to cover an area larger than France. The environmental impact was significant. Sulfur dioxide and carbon dioxide flooded the atmosphere. Temperatures fluctuated. Acid rain became common. Ecosystems were stressed. But they endured. Dinosaurs were still thriving. The fossil record from the latest Cretaceous shows no sign of decline. Diversity remained high. New species were still evolving. There was no slow fade, no gradual weakening. Right up until the end, dinosaurs were doing what they had always done. Adapting. Competing. Surviving. And then, 66 million years ago, everything changed. An asteroid roughly 10 kilometers in diameter struck what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear bombs. The immediate effects were apocalyptic. A shockwave flattened forests for hundreds of kilometers. Tsunamis hundreds of meters high swept across coastlines. Debris blasted into the atmosphere, then rained back down as molten rock, igniting global wildfires. Within hours, much of the planet was burning. But the real killer wasn't the immediate impact. It was what came after. Dust and ash filled the atmosphere, blocking out sunlight. Temperatures plummeted. Photosynthesis stopped. Plants died. Herbivores starved. Carnivores followed. This wasn't a quick extinction. It unfolded over months, years, possibly decades. The darkness lasted long enough to collapse food chains from the bottom up. By the time the skies cleared, 75% of all species were gone. Every non-avian dinosaur vanished. Pterosaurs disappeared. Mosasaurs went extinct. The Cretaceous ended not with a gradual decline, but with a single, catastrophic blow. Yet some things survived. Birds made it through. Small mammals endured. Crocodiles persisted. Turtles survived. These weren't random survivors. They shared traits that mattered when the world went dark. Small body size meant lower energy needs. Burrowing behavior provided shelter from temperature extremes. Omnivorous diets allowed flexibility when food chains collapsed. The ability to enter dormancy, to slow metabolism and wait out the crisis, proved invaluable. Birds survived because they were small, adaptable, and could fly to wherever resources remained. Mammals survived because they were already living in the margins, already adapted to scavenging, already capable of exploiting whatever was available. The extinction didn't choose the strongest. It chose the most flexible. In the immediate aftermath, Earth was unrecognizable. Forests were gone, replaced by ferns and pioneer plants that could colonize bare ground quickly. The fern spike, a layer of fern spores found in rock strata worldwide, marks this moment. It's a geological signature of devastation, a planet resetting itself from scratch. For perhaps 1,000,000 years, ecosystems remained simple. Food webs were short. Biodiversity was low. The survivors spread out, filling niches left empty. Mammals, no longer constrained by dinosaur dominance, began to diversify. Within 10 million years, they had radiated into forms that would eventually lead to whales, bats, primates, ungulates. Birds did the same, splitting into lineages that would become songbirds, raptors, seabirds, flightless giants. Life didn't pause. It exploded into the vacuum. But this wasn't a return to what came before. The Mesozoic was over. The age of dinosaurs had ended. What followed was something entirely new. The Cenozoic era, the age of mammals, had begun. And with it came a different set of rules. Mammals didn't dominate immediately. For the first few million years of the Paleocene, they remained small. The largest mammals were about the size of modern dogs. But they were experimenting. Some became herbivores, developing teeth suited for grinding plants. Others became carnivores, refining hunting strategies. Still others took to the trees, developing grasping hands and forward-facing eyes. The evolutionary paths that would lead to modern biodiversity were being laid down in real time. By 55 million years ago, during the Eocene, mammals had grown larger. Forests have returned, denser and more complex than before. Flowering plants, which had begun their rise in the Cretaceous, now dominated. They brought with them insects, specifically pollinators, creating intricate relationships that reshaped ecosystems. Mammals adapted to these new forests. Primates evolved, moving through the canopy. Burly horses appeared, small forest dwellers nothing like their modern descendants. Whales began their transition from land to sea, a process documented in fossil sequences showing progressive adaptations. The planet was warm again, warmer than today. Palm trees grew in Alaska. Crocodiles lived in the Arctic. This was the Paleocene-Eocene thermal maximum, a period of rapid warming driven by massive carbon release, possibly from volcanic activity or methane clathrates destabilizing on the ocean floor. Temperatures spiked by 5 to 8 degrees Celsius in just a few thousand years. Ecosystems shifted rapidly. Some species went extinct. Others migrated toward the poles. Mammals continued adapting, some growing larger to cope with heat stress, others becoming more specialized. Then the planet began to cool. Gradually at first, then more dramatically. By 34 million years ago, Antarctica had frozen over. Ice sheets formed at the poles for the first time since the Mesozoic. Ocean currents changed. Climate zones sharpened. Tropical forests retreated toward the equator. Grasslands began to spread. This cooling trend, driven by shifting continental positions and declining atmospheric CO2, fundamentally altered life on land. Forests gave way to open plains. Mammals that had thrived in dense vegetation now faced new challenges. Some adapted by becoming faster, developing long legs for running. Others grew larger, using size as defense against predators. Horses evolved from small forest browsers into larger grassland grazers. Their teeth changed, becoming taller and harder to withstand the abrasive silica in grass. Their legs lengthened, their bodies streamlined for speed. This wasn't random. It was direct adaptation to a changing environment. Predators evolved in response. Carnivores became faster, more coordinated, more efficient. Pack hunting emerged as a strategy. Canids, ancestors of modern wolves and dogs, began working together to bring down prey larger than themselves. Cats refined ambush tactics, developing retractable claws and powerful builds suited for explosive attacks. The grasslands became arenas of predator-prey dynamics more intense than anything in the forests. Meanwhile, other lineages took different paths. Elephants and their relatives grew massive, developing trunks, tusks, and complex social structures. Whales, now fully aquatic, diversified into filter feeders and toothed predators, dominating the oceans in ways no marine reptile ever had. Bats refined echolocation, becoming the only mammals capable of true flight. Each group found its niche, exploited it, and diversified. By 20 million years ago, the planet looked more familiar. Continents were approaching their modern positions. India had collided with Asia, forming the Himalayas. Africa was moving toward Europe. North and South America were still separated, but the gap was closing. These geographic changes continued to drive evolution. Species isolated on different continents evolved in isolation. South America, cut off from other land masses, developed its own unique fauna. Giant ground sloths, armadillo relatives the size of cars, terror birds, flightless predatory birds standing 3 meters tall. These were the dominant animals of South America for millions of years. Africa had its own distinct groups. Early elephants, hippos, giraffes. Asia had rhinos, giant apes, saber-toothed cats. North America had camels, horses, mastodons. Each continent was its own evolutionary laboratory. Then, about 3 million years ago, the Isthmus of Panama formed, connecting North and South America. Animals began moving between continents. The Great American Interchange had begun. North American predators, more efficient and aggressive, moved south. South American herbivores, unused to such pressure, declined. Many unique South American groups went extinct. Ground sloths and armadillos moved north, but most didn't last long. The exchange was asymmetrical. North American species generally outcompete their southern counterparts. This wasn't because they were inherently superior. They came from ecosystems with higher competition, more predators, more pressure. They were battle-tested. Around 2.5 million years ago, the Pleistocene began. Ice ages returned, not as permanent features but as cycles. Glaciers advanced and retreated in roughly 100,000-year intervals, driven by variations in Earth's orbit and axial tilt. During glacial periods, ice sheets covered much of North America, Europe, and Asia. Sea levels dropped as water locked into ice. Land bridges appeared, connecting continents. Animals migrated across these bridges, spreading into new territories. Mammoths moved from Africa into Eurasia, then across Beringia into North America. Humans would follow the same route tens of thousands of years later. During interglacials, the ice retreated. Forests returned to high latitudes. Sea levels rose, flooding coastlines and isolating populations. This constant cycling drove rapid evolution. Species adapted to cold climates during glacials, then had to adapt again when warmth returned. Those that couldn't keep up went extinct. Megafauna thrived during this time. Giant mammals dominated every continent. Mammoths, mastodons, giant ground sloths, saber-toothed cats, dire wolves, short-faced bears, giant beavers, enormous kangaroos in Australia, elephant birds in Madagascar. These weren't anomalies. They were the norm. Large body size was advantageous in fluctuating climates. It allowed for better heat retention during cold periods and longer fasting during resource scarcity. But size also made them vulnerable. They reproduced slowly, needed vast territories, and required large amounts of food. When conditions changed rapidly, they struggled. And then, something new appeared. A small bipedal primate, originating in Africa, began spreading across the globe. Humans didn't seem like much at first. They were weak compared to the megafauna, slow compared to predators, lacking any obvious physical advantages. But they had something else. Intelligence. Tool use. Language. Cooperation. These traits allowed humans to hunt animals far larger than themselves, to adapt to environments from tropical rainforests to Arctic tundra, to survive where other species couldn't. As humans spread, megafauna began disappearing. The pattern is striking. In Africa, where humans evolved gradually alongside large animals, megafauna persisted. Animals there had time to adapt to human hunting pressure. But in regions humans entered suddenly, extinctions followed quickly. Australia lost its giant kangaroos, wombats, and reptiles within a few thousand years of human arrival. The Americas saw similar losses. Mammoths, ground sloths, saber-toothed cats, all gone within millennia of humans crossing into the continent. The debate continues over how much humans contributed versus climate change, but the correlation is undeniable. Where humans went, giants fell. By 10,000 years ago, the Pleistocene was ending. The last ice age was retreating. Glaciers melted, sea levels rose, climate stabilized. And in this new, warmer world, humans did something unprecedented. They stopped moving. They settled. They began farming. Agriculture wasn't an invention. It was a necessity. As megafauna disappeared, hunting became harder. Reliable food sources vanished. Humans turned to plants, domesticating wheat, rice, maize. They domesticated animals too. Sheep, goats, cattle, pigs. These weren't random choices. They were species that could thrive near human settlements, that bred quickly, that provided consistent resources. Farming changed everything. It allowed populations to grow. It created surplus, which led to specialization. Not everyone had to hunt or gather. Some could build, some could craft, some could organize. Settlements became villages. Villages became cities. Cities became civilizations. And with civilization came new pressures. Humans began shaping the environment deliberately. Forests were cleared for farmland. Rivers were diverted for irrigation. Animals were hunted not just for survival but for trade. The planet, which had been shaped by geological and biological forces for billions of years, was now being reshaped by a single species. This brings us to the present. The Holocene, the epoch we've lived in for the past 10,000 years, has been remarkably stable. Temperatures haven't fluctuated wildly. Ice ages haven't returned. This stability allowed human civilization to flourish. But stability is ending. We're entering what scientists call the Anthropocene. A new geological epoch defined not by ice or heat, but by human impact. The evidence is everywhere. Carbon dioxide levels in the atmosphere are higher than they've been in 3 million years. Global temperatures are rising faster than at any point in the last 10,000 years. Species are going extinct at rates 1,000 times higher than the natural background rate. The oceans are warming, acidifying, losing oxygen. Ice sheets are melting. Sea levels are climbing. Weather patterns are destabilizing. This isn't speculation. It's measured, documented, undeniable. The question isn't whether humans are changing the planet. We are. The question is what happens next. Climate change gets framed as a future problem, but it's already here. We're living through it now. Arctic ice is vanishing. Permafrost, frozen for millennia, is thawing, releasing methane. Coral reefs, ecosystems that support a quarter of all marine life, are bleaching and dying. Forests are burning with increasing frequency and intensity. Droughts are lasting longer. Storms are growing stronger. These aren't isolated events. They're connected, part of a system pushed out of balance. And unlike past climate shifts that unfolded over thousands of years, this one is happening in decades. Species can't adapt that fast. Ecosystems can't adjust. We're conducting an experiment with no control group, no way to reverse course if things go wrong. The parallels to past mass extinctions are uncomfortable. The Permian extinction, the worst in Earth's history, was triggered by volcanic eruptions that released massive amounts of carbon dioxide. The oceans warmed, became acidic, lost oxygen. 90% of species died. Today, we're releasing carbon even faster than those ancient volcanoes. Not from lava, but from burning fossil fuels, coal, oil, gas. The difference? Volcanoes couldn't turn themselves off. We can. But we're not. Not fast enough, anyway. Emissions keep rising. Temperatures keep climbing. The longer we wait, the harder it becomes to stop. Some argue technology will save us. Carbon capture, geoengineering, solutions that sound promising in theory. But technology isn't magic. It requires energy, resources, time. And even if we develop these tools, deploying them at planetary scale is another challenge entirely. Others suggest adaptation. Humans are resilient, they say. We've survived ice ages, droughts, disasters. We'll figure it out. And maybe we will. But survival isn't the same as thriving. Civilizations have collapsed before when climates shifted. The Maya, the Akkadians, societies that seemed powerful until suddenly they weren't. They didn't have global supply chains, interconnected economies, cities housing millions. We do. Which makes us more vulnerable, not less. Agriculture, the foundation of civilization, depends on stable climate. Crops need predictable rainfall, consistent temperatures, healthy soil. As climates shift, growing seasons change. Droughts strike breadbasket regions. Floods destroy harvests. Pests and diseases spread to new areas. Food security becomes fragile. When food becomes scarce, people migrate. When people migrate, tensions rise. History shows what happens when resources dwindle. Conflict. War. Collapse. We're seeing early signs already. Droughts contributing to civil wars. Floods displacing millions. Fires forcing evacuations. This is just the beginning. If temperatures rise by 2, 3, 4 degrees, the disruptions will be far worse. The ocean tells its own story. It's absorbed 90% of the excess heat we've added to the system. That sounds helpful until you realize what it means. Warmer water expands, raising sea levels. Warmer water holds less oxygen, creating dead zones. Warmer water disrupts currents that regulate global climate. The ocean isn't infinite. It has limits. We're pushing those limits. Marine ecosystems are unraveling. Fish populations are crashing. Plankton, the base of the ocean food web, are struggling. If the ocean fails, we fail. We depend on it for food, for oxygen, for climate regulation. Half the oxygen we breathe comes from ocean plankton. When we damage the ocean, we're damaging ourselves. Then there's the sixth mass extinction. We're in it now. Species are vanishing not from asteroids or volcanoes, but from habitat destruction, pollution, climate change, human activity. Every species lost is a thread pulled from the web of life. Ecosystems are resilient to a point, but redundancy has limits. Remove enough threads and the web collapses. We don't know where that point is. We won't know until we've crossed it. And once crossed, there's no going back. Extinction is permanent. The species we're losing took millions of years to evolve. They won't return in any time frame that matters to us. But here's what makes this moment different from past extinctions. We know it's happening. Past species didn't see the asteroid coming, couldn't predict the volcanic eruptions. We can see what's coming. We have the data, the models, the evidence. We understand cause and effect. That means we have a choice. We can continue on our current path, hoping technology or luck saves us. Or we can change course. The window for change is closing, but it hasn't closed yet. The next few decades will determine the trajectory of the next few centuries. What does changing course look like? It starts with energy. Fossil fuels built modern civilization, but they're killing the planet. Transitioning to renewable energy, solar, wind, hydro, isn't just possible, it's happening. Solar costs have dropped 90% in a decade. Wind power is now cheaper than coal in many places. The technology exists. What's missing is political will, investment, urgency. Every year we delay makes the transition harder and more expensive. Waiting isn't cautious. It's reckless. Transportation is another piece. Cars, planes, ships, they all burn fuel, emit carbon. Electric vehicles are spreading but not fast enough. Public transportation needs expansion. Cities need redesigning around people, not cars. Air travel is trickier. Batteries can't yet power commercial jets for long distances. That means finding alternatives, biofuels, hydrogen, or accepting that some things need to change. Maybe we fly less. Maybe we find other ways to connect. Agriculture needs transformation too. Industrial farming is a massive carbon source. Fertilizers release nitrous oxide. Livestock produce methane. Deforestation for farmland destroys carbon-absorbing forests. Sustainable farming practices exist. Regenerative agriculture, crop rotation, reduced tillage. They work. They're just not standard practice. Changing how we grow food could sequester carbon, restore soil health, support biodiversity. But it requires rethinking our entire food system. That's daunting. It's also necessary. Then there's consumption. We live in a culture of waste. Products designed to break, trends that change seasonally, convenience prized over sustainability. This isn't sustainable. Not economically, not environmentally. A circular economy, where products are designed to last, to be repaired, to be recycled, isn't utopian fantasy. It's practical necessity. Resources are finite. Treating the planet like an infinite supply depot was always going to end badly. We're reaching that end. Individual actions matter, but systemic change matters more. You can recycle, drive less, eat plant-based, and it helps. But without large-scale policy changes, corporate accountability, global cooperation, individual efforts aren't enough. Governments need to regulate emissions, subsidize clean energy, penalize pollution. Corporations need to prioritize sustainability over short-term profits. International agreements need teeth, enforcement, commitment. The Paris Agreement was a start. It's not enough. We need more ambition, more urgency, more action. This isn't about saving the planet. The planet will survive. It survived worse. Asteroid impacts, ice ages, volcanic eruptions. Earth endures. Life endures. What's at stake is human civilization. The stable climate that allowed us to build cities, grow crops, thrive. That's what's threatened. We're not fighting for the planet. We're fighting for ourselves. The stakes are enormous, but the situation isn't hopeless. Human ingenuity got us into this mess. It can get us out. We've solved massive problems before. Eradicated diseases, split atoms, sent people to the moon. We can do this too. But it requires collective effort on a scale we've never attempted. It requires reimagining how we live, how we build, how we interact with the natural world. It requires seeing ourselves not as separate from nature, but as part of it. The same rules that apply to every other species apply to us. We're not exempt from ecological limits. We're subject to them. What gives me hope? The fact that change is already happening. Renewable energy is booming. Electric vehicles are multiplying. Reforestation projects are underway. Plastic bans are spreading. Climate awareness is growing. Young people especially are demanding action, refusing to accept the world as it is. That energy, that urgency, that refusal to give up, that's what drives progress. Change doesn't come from resignation. It comes from determination. The future isn't written. It's being decided now. By the choices we make, the actions we take, the systems we build or dismantle. We're at a crossroads. One path leads to catastrophe. The other leads to adaptation, resilience, a different way of living. Neither path is easy, but one is survivable. The question is whether we have the courage to take it. So what does taking that path actually look like? Not in abstract terms, but in concrete reality. Start with infrastructure. Cities aren't just collections of buildings. They're systems. Transportation, energy, water, waste. Every component connects. Redesigning them isn't about tearing everything down and starting over. It's about strategic retrofitting, smart planning, gradual transformation. Copenhagen didn't become a cycling capital overnight. It invested in bike lanes, prioritized pedestrians, made cars less convenient. Now cycling is faster, easier, safer than driving. That didn't require futuristic technology. It required political will and urban planning. Other cities can replicate that. Many are trying. The results speak for themselves. Less congestion, cleaner air, healthier populations. It works because it addresses the system, not just individual behavior. Energy grids need similar thinking. Centralized power plants feeding vast networks made sense when fossil fuels were cheap and climate impacts were ignored. That model is outdated. Distributed generation, microgrids, localized storage, these aren't fringe concepts anymore. They're practical solutions being implemented globally. A neighborhood with solar panels, battery storage, smart meters can generate its own power, share excess with the grid, reduce transmission losses. Scale that up. Communities, cities, regions. The technology exists. The barriers are regulatory, financial, political. Those can be overcome. They're being overcome. Slowly, unevenly, but steadily. Buildings themselves offer enormous potential. Most existing structures are energy sieves. Heat escapes in winter, enters in summer, requiring constant heating and cooling. Retrofitting with insulation, efficient windows, smart thermostats cuts energy use dramatically. New buildings can be designed to passive house standards, requiring minimal heating or cooling. Green roofs absorb rainwater, reduce urban heat islands, provide insulation. These aren't experimental ideas. They're established practices. The challenge is making them standard, not optional. Transportation is harder because it's so embedded in how we live. Sprawling suburbs designed around cars can't be fixed with bike lanes alone. But they can be densified, connected with public transit, integrated with mixed-use development. That takes time. Decades, not years. But the alternative is continuing a pattern that's unsustainable and increasingly unaffordable. Electric vehicles help, but they're not a complete solution. Fewer cars overall, more shared mobility, better urban design, these matter just as much. A city where you can walk to work, bike to the store, take a train across town, that's a city that doesn't need everyone to own a car. That's a city with lower emissions, less traffic, more livable public spaces. Agriculture presents its own complexities. Industrial farming feeds billions, but at a cost. Soil degradation, water depletion, chemical runoff, greenhouse gas emissions. Alternatives exist. Agroforestry integrates trees into farms, improving soil, sequestering carbon, supporting biodiversity. Precision agriculture uses data to apply fertilizers and pesticides only where needed, reducing waste and runoff. Vertical farming grows food in controlled environments, using less water and land. These methods aren't universally applicable. Some work better in certain climates, for certain crops, at certain scales. But collectively, they represent a shift toward farming that works with ecosystems, not against them. Diet matters too. Meat production, particularly beef, is resource intensive. Massive land use, water consumption, methane emissions. Reducing meat consumption, especially in wealthy countries where intake is highest, would significantly lower agriculture's climate impact. That doesn't mean everyone needs to go vegan. It means shifting toward plant-heavy diets, treating meat as occasional rather than constant, valuing quality over quantity. Cultural resistance to this is real. Food is identity, tradition, comfort. But cultures evolve. Diets have changed throughout history. They can change again. Waste is another frontier. Linear economy models, take, make, dispose, are fundamentally flawed. Resources extracted, products made, waste generated, repeat. That's not sustainable with finite resources and limited disposal options. Circular economy principles, designed for durability, repairability, recyclability, close the loop. Products become resources for new products. Waste is minimized. This requires rethinking manufacturing, incentivizing longevity over obsolescence, creating systems for collection and reprocessing. Some companies are moving this direction. Not many, not fast enough, but it's starting. Consumer demand can accelerate it. Regulations can mandate it. Technology will play a role, but it's not a magic bullet. Carbon capture, geoengineering, fusion power, these are often presented as future solutions that will fix everything. Maybe they will. Maybe they won't. Banking on unproven technologies while delaying action on proven solutions is reckless. We need to deploy what works now while continuing to innovate. Solar and wind are proven. Batteries are improving rapidly. Electric vehicles are viable. Efficient buildings are standard practice in some places. These aren't waiting for breakthroughs. They're waiting for adoption. Finance is crucial. Climate action requires investment. Trillions, not billions. That sounds impossible until you consider how much is already spent on fossil fuel subsidies, military budgets, bank bailouts. It's not about finding new money. It's about redirecting existing flows. Subsidizing clean energy instead of coal. Investing in public transit instead of highways. Funding efficiency retrofits instead of new power plants. The money exists. The question is priorities. International cooperation is essential. Climate change doesn't respect borders. Emissions anywhere affect everywhere. Wealthy nations, which industrialized first and contributed most to historical emissions, have a responsibility to lead and support developing nations in transitioning sustainably. That means technology transfer, financial assistance, capacity building. Not charity. Justice. The global north profited from fossil fuels. The global south shouldn't have to choose between development and climate stability. Green technology should be accessible, not locked behind patents and profit margins. Policy mechanisms matter. Carbon pricing, cap and trade, regulations, subsidies, these aren't abstract economic theories. They're tools that change behavior at scale. Make pollution expensive, clean alternatives cheap, and markets respond. This isn't about controlling every aspect of life. It's about correcting market failures, internalizing costs that have been externalized onto the environment and future generations. Social equity can't be ignored. Climate impacts hit the poorest hardest. They have the least resources to adapt, the least responsibility for emissions, the most to lose. Climate action that ignores this isn't just unfair. It's unstable. Transitions need to be just, supporting workers and communities dependent on fossil fuel industries, ensuring benefits are widely shared, not concentrated among the already privileged. Education and communication are foundational. Understanding climate science, recognizing misinformation, evaluating solutions, these skills matter. A population that understands the stakes and the options can demand better from leaders and corporations. Misinformation is pervasive, well-funded, deliberately confusing. Countering it requires clarity, patience, credibility. Science communication isn't about dumbing down. It's about translating complexity without losing accuracy. Political engagement is non-negotiable. Voting, advocacy, activism, these drive policy. Elected officials respond to pressure. Corporations respond to regulation and consumer demand. Change at scale requires political power, and political power comes from organized, persistent effort. Cynicism is a luxury we can't afford. Systems feel immovable until they move. History is full of rapid transformations that seemed impossible until they happened. Individual actions still matter, not because they'll solve the crisis alone, but because they reinforce commitment, build habits, create culture. Choosing public transit, reducing consumption, supporting sustainable businesses, these aren't futile gestures. They're part of a broader shift. Culture changes when enough people change. Norms shift. What was unusual becomes common. What was accepted becomes unacceptable. The path forward isn't linear or easy. There will be setbacks, resistance, failures. Progress is messy. But the alternative, continuing as we are, isn't an option. The climate is changing regardless of what we do now. The question is how much, how fast, how catastrophically. Every fraction of a degree matters. Every ton of emissions avoided matters. Every policy implemented, every technology deployed, every behavior shifted, they add up. This isn't about returning to some imagined past. Pre-industrial life wasn't idyllic. It was hard, short, limited. Progress is real. Technology improves lives. The goal isn't reversal. It's redirection. Using our capabilities wisely, building systems that work long-term, creating prosperity that doesn't come at the expense of future generations. That's not naive optimism. It's pragmatic survival. We've been here before, facing existential threats that seemed insurmountable. Ozone depletion, acid rain, lead poisoning. CFCs were banned. Emissions were regulated. Leaded gasoline was phased out. These weren't easy wins. They required science, advocacy, international cooperation, political courage. But they happened. The ozone layer is recovering. Lakes are healing. Air is cleaner. These victories prove that large-scale environmental problems can be solved when there's will to act. Climate change is bigger, more complex, more entrenched in global systems. But the principles remain. Identify the problem. Understand the solutions. Build political will. Implement policy. Adapt as you learn. It's not hopeless. It's hard. There's a difference. The future being decided now isn't predetermined. It's being shaped by choices made today, tomorrow, next year. By governments, corporations, communities, individuals. Every decision point is an opportunity. Every setback is temporary unless we surrender. The question isn't whether we can avoid all impacts. We can't. Some are already locked in. The question is whether we limit them, adapt to them, build resilience against them. Whether we create a world that's livable, stable, just. That's the path worth taking. Not because it's easy or guaranteed, but because it's necessary and possible. The courage required isn't superhuman. It's simply human. The willingness to face hard truths, make difficult changes, work towards something larger than immediate comfort. That's always been how progress happens. This time is no different. Except the stakes are everything. The Triassic, Jurassic, and Cretaceous weren't just chapters in a textbook. They were experiments. Tests of what's possible when life is given time, pressure, and an unstable planet to work with. Dinosaurs dominated for 165 million years. Humans have been around for maybe 300,000. We're not the pinnacle. We're just the latest iteration. And if the past teaches anything, it's that dominance is temporary. Every extinction event, every climate shift, every asteroid impact, they all reset the board. What survives isn't always the strongest or the smartest. It's the most adaptable. The ones that can shift when the world shifts. Dinosaurs thrived until they couldn't. Mammals waited in the margins until their moment came. The lesson isn't that we're special. It's that nothing is permanent. Right now, we're living through a transition as significant as any in Earth's history. Not because of volcanoes or asteroids, but because of us. We've become a geological force. Our impact is measurable in ice cores, ocean chemistry, atmospheric composition. Future geologists will. 7 planets orbit a star 40 light-years away. Not scattered randomly like our solar system, but compressed into a space smaller than Mercury's orbit around our sun. If you stood on one of these worlds and looked up, neighboring planets would appear larger in the sky than our moon. This isn't science fiction. This is TRAPPIST-1. In 2017, NASA announced the discovery of 7 Earth-sized planets around a single star. 3 of them sit in a habitable zone where liquid water could exist. Within weeks, TRAPPIST-1 became the most studied planetary system beyond our own. Scientists redirected telescopes, reprioritized missions, and rewrote research proposals. Because this system isn't just interesting, it's a laboratory for understanding whether life exists elsewhere in the universe. The star itself defies everything we assume about solar systems. TRAPPIST-1 is an ultra-cool dwarf star, barely larger than Jupiter, burning at temperatures that make it glow deep red rather than yellow like our Sun. It produces less energy in a year than our Sun emits in a day. Yet around this dim ember orbit 7 rocky worlds, each locked in gravitational resonance, their orbits synchronized like a cosmic clockwork mechanism that's been running for billions of years. Distance creates problems. 40 light-years means the light we see from TRAPPIST-1 today left that star before the internet existed. Any signal we send would take 40 years to arrive, and we'd wait another 40 for a response. Even our fastest spacecraft would need hundreds of thousands of years to reach it. This isn't a place we'll visit anytime soon. But distance doesn't mean irrelevance. The James Webb Space Telescope changed everything. For the first time in human history, we can analyze the atmospheres of planets orbiting other stars. We're not guessing anymore about what exists on distant worlds. We're measuring it directly. And TRAPPIST-1, with its compact system and frequent planetary transits, offers the best opportunity we have to detect signs of life beyond Earth. Here's what makes this system extraordinary. The planets don't just orbit randomly. They're locked in what astronomers call orbital resonance. For every 8 orbits TRAPPIST-1b completes, planets C, D, E, F, G, and H complete 5, 3, 2, 1, and 1 orbits respectively. This mathematical precision isn't coincidence. It's the signature of a system that has stabilized over billions of years, where gravitational interactions have pulled planets into synchronized motion. Think of it like pushing someone on a swing. Push at random times and nothing happens. Push at exactly the right moment in each cycle and the swing goes higher. The TRAPPIST-1 planets push and pull on each other at precisely the right times, stabilizing their orbits and potentially creating conditions that could support life. The innermost planet, TRAPPIST-1b, completes an orbit in just 1.5 Earth days. It's too close to the star, receiving 4 times more radiation than Earth gets from the Sun. Surface temperatures likely exceed 400 degrees Fahrenheit. Any water that once existed has long since evaporated. But move outward and conditions change rapidly. TRAPPIST-1e sits in the middle of the habitable zone. It's almost exactly Earth's size, slightly more massive, with a density suggesting a rocky composition similar to our own planet. If water exists anywhere in this system, this is where we'd expect to find it. Scientists have focused enormous attention on this single world because it represents our best chance of finding life around an ultra-cool dwarf star. But there's a problem nobody expected. The first atmospheric measurements came back essentially blank. The James Webb Space Telescope detected no significant atmosphere on TRAPPIST-1b or C. For planets that should theoretically hold on to their atmospheres, this absence is troubling. It suggests something is stripping away these gaseous envelopes faster than planets can retain them. The star itself might be the culprit. Ultra-cool dwarf stars like TRAPPIST-1 are violent in ways our Sun isn't. They produce intense stellar flares, bursts of radiation and charged particles that slam into nearby planets. These flares can be thousands of times more powerful than solar flares. When they strike a planet, they don't just heat the surface. They strip away atmospheric particles, molecule by molecule, potentially rendering worlds uninhabitable despite being in the so-called habitable zone. This creates a paradox. Ultra-cool dwarf stars are the most common type of star in the galaxy. They make up roughly 75% of all stars. They also live for trillions of years, far longer than our sun's projected 10 billion-year lifespan. If life needs time to develop, these stars offer more of it than any other stellar type. But if their flares destroy atmospheres, then the most common stars in the galaxy might also be the least likely to host life. Yet dismissing TRAPPIST-1 would be premature. Planets might protect themselves in ways we haven't considered. Strong magnetic fields could deflect stellar wind. Thick atmospheres could regenerate faster than flares strip them away. Oceans could provide a reservoir of gases that replenish atmospheric losses. And some planets in the system, particularly those farther from the star, might avoid the worst of the stellar violence while still receiving enough energy for liquid water. TRAPPIST-1F and G occupy positions at the outer edge of the habitable zone. They receive less radiation than Earth, but not so little that water must freeze. These worlds might be covered in ice with liquid oceans beneath frozen crusts, similar to Jupiter's moon Europa or Saturn's moon Enceladus. Such environments could be remarkably stable, shielded from stellar flares by kilometers of ice while maintaining liquid water in contact with rocky cores where chemical reactions could support life. The density measurements tell us something unexpected. These planets aren't identical copies of Earth. Their densities vary significantly, suggesting different compositions. Some might be water worlds with deep global oceans. Others could be desiccated rocks stripped bare by stellar radiation. A few might have retained thick atmospheres of hydrogen and helium. The system isn't uniform. It's diverse, offering multiple pathways for habitability or multiple ways for planets to fail at supporting life. Tidal forces add another layer of complexity. Because the planets orbit so close to their star and are likely tidally locked, one side permanently faces the star while the other side remains in eternal darkness. This creates extreme temperature gradients. The day side might be scorching hot while the night side freezes. Any atmosphere would constantly circulate, trying to redistribute heat from day to night. This circulation could create permanent storms, winds that never stop, weather patterns unlike anything Earth experiences. But tidal locking isn't necessarily bad for life. The twilight zones, the regions between permanent day and permanent night, could be remarkably stable. Temperatures there might remain moderate, avoiding the extremes of either hemisphere. If liquid water exists, it would likely pool in these twilight regions, creating narrow bands where conditions stay relatively constant. Life, if it exists, might be confined to these transitional zones, thriving in the permanent sunset of a tidally locked world. Scientists debate whether we could ever know for certain if these planets host life. Detecting an atmosphere is one thing. Proving that atmosphere contains biosignatures, gases produced by living organisms, is far more challenging. Oxygen is the classic example. On Earth, oxygen exists in our atmosphere because photosynthetic organisms constantly produce it. Without life, oxygen would quickly react with surface rocks and disappear. Finding oxygen in TRAPPIST-1E's atmosphere would be compelling evidence for life. But oxygen alone isn't enough. Geological processes can produce oxygen without life. We need combinations of gases, chemical signatures that only make sense if biology is present. Oxygen combined with methane, for instance, would be powerful evidence because these gases react with each other and shouldn't coexist unless something continuously produces them. Life produces both. Geology typically doesn't. The James Webb Space Telescope will spend years studying TRAPPIST-1. Each time a planet passes in front of the star, starlight filters through its atmosphere and reaches us carrying information about what gases exist there. By analyzing this light, scientists can identify atmospheric components. But the signals are faint. Detecting them requires hundreds of observations, patient accumulation of data, building up evidence piece by piece until a picture emerges. Recent observations of TRAPPIST-1b have been discouraging. The planet appears to have no substantial atmosphere. This doesn't doom the entire system, but it raises questions about how well any of these planets have retained their atmospheres. If the innermost planet lost its gases, what about the others? Are we searching for life in a system where stellar activity has already stripped away the very atmospheres we need to study? TRAPPIST-1c faces similar scrutiny. Early measurements suggested the possibility of a thick carbon dioxide atmosphere. Subsequent observations found no evidence for it. Either the atmosphere is incredibly thin or composed of gases we haven't detected yet. Or perhaps it simply doesn't exist. Each negative result narrows the possibilities but doesn't eliminate hope. We're still learning how to interpret these observations, still understanding the limitations of our instruments. The system's age compounds these uncertainties. TRAPPIST-1 is roughly 7.6 billion years old, significantly older than our solar system. That's billions of additional years for stellar flares to pummel planets, for atmospheres to erode, for conditions to change. But it's also billions more years for life to emerge, evolve, and potentially leave detectable traces. Age cuts both ways. What happens next depends on what we find. If TRAPPIST-1e has an atmosphere, the focus shifts to characterizing it completely. Scientists will search for water vapor, carbon dioxide, methane, oxygen, and dozens of other compounds. Each detection or non-detection refines our understanding of what kind of world exists there. If we find nothing, attention might shift to the outer planets where conditions could be less hostile despite receiving less stellar energy. Human nature drives us to find patterns, to imagine what these worlds look like, to picture oceans and mountains and alien skies. But we need to resist premature conclusions. TRAPPIST-1 might host life. It might be completely dead. It might fall somewhere in between, with environments capable of supporting life but currently empty through cosmic accident. The only way to know is through methodical observation, collecting evidence without rushing to judgment. The implications extend beyond 7 planets around a dim star. TRAPPIST-1 is common in the galaxy. Not this exact system, but ultra-cool dwarf stars with compact planetary systems. If we determine that TRAPPIST-1 planets can't support life, we're effectively ruling out billions of similar systems. If we find that life can exist there despite the challenges, we're opening up vast regions of the galaxy as potential habitats. Either answer reshapes our understanding of life's prevalence in the universe. Human outlined these possible outcomes. What actually exists at TRAPPIST-1 remains unknown. But each observation brings clarity, each measurement constrains possibilities. We're moving from speculation to data, from wondering to knowing. And the journey has barely started. The challenge isn't just detecting atmospheres. It's understanding what those atmospheres tell us about the planets beneath them. An atmosphere doesn't exist in isolation. It's shaped by volcanic activity, weathering of rocks, biological processes, and the relentless bombardment of stellar radiation. Consider what happens when starlight passes through a planetary atmosphere. Different molecules absorb specific wavelengths of light. Oxygen absorbs certain frequencies. Water vapor absorbs others. Methane has its own signature. By measuring which wavelengths are missing from the light that reaches us, scientists can deduce what gases are present. But this requires the planet to pass directly between us and its star, creating a transit. During those few hours when the geometry aligns, telescopes collect as much data as possible. Then the planet moves on, and we wait weeks or months for the next opportunity. The signal we're measuring is incredibly weak. Imagine trying to detect a single grain of sand added to a beach by measuring the beach's total weight. That's the scale we're working with. The atmosphere of an Earth-sized planet adds roughly 1 part in 10,000 to the total light blocked during a transit. Within that tiny signal, we're searching for even tinier variations caused by specific molecules. It's technically possible, but it requires perfect conditions, flawless calibration, and patience. TRAPPIST-1 doesn't make this easy. The star itself is variable, with surface features that change over time. Star spots, the cooler regions on a star's surface, can mimic or obscure atmospheric signals. When a planet transits across a star spot, the light curve changes in ways that have nothing to do with the planet's atmosphere. Separating these effects requires multiple observations and sophisticated modeling. We're essentially trying to subtract the star's natural variations to isolate the planet's contribution. The James Webb Space Telescope was designed for exactly this kind of work. Its infrared capabilities allow it to detect molecules that are invisible to optical telescopes. Carbon dioxide, for instance, has strong absorption features in the infrared. Water vapor shows up clearly. Methane becomes detectable. But even Webb has limitations. Observing a single planet requires multiple transits. Building up enough signal to confidently detect an atmosphere can take dozens of hours of telescope time. With 7 planets to study and limited observing windows, the process stretches across years. Early results from Webb have been humbling. The instrument works brilliantly, but the planets aren't cooperating. TRAPPIST-1b shows no sign of a thick atmosphere. TRAPPIST-1c remains ambiguous. These aren't instrument failures. They're real results telling us something important about how planets survive around red dwarf stars. Maybe atmospheres around these stars are rare. Maybe they exist but are composed of gases we haven't thought to look for. Or maybe we need more data before drawing conclusions. The habitable zone planets present a different puzzle. TRAPPIST-1e receives roughly the same amount of energy from its star as Earth receives from the Sun. If it has an atmosphere, that atmosphere could support liquid water on the surface. But the planet is tidally locked, with one side permanently facing the star and the other side in eternal darkness. This creates extreme temperature gradients. The day side could be scorching, the night side frozen. Only in the narrow band between them, the terminator region, might temperatures allow liquid water. Unless the atmosphere redistributes heat. A thick atmosphere with strong winds could transport warmth from the day side to the night side, moderating temperatures across the entire planet. Earth's atmosphere does this to some extent. Venus does it far more effectively, with winds so powerful they circle the planet in just 4 days despite the planet's slow rotation. If TRAPPIST-1e has similar atmospheric circulation, the entire surface could be habitable. But if the atmosphere is thin or non-existent, the terminator might be the only refuge. This matters for more than just temperature. Atmospheric circulation affects where water accumulates. On a tidally locked planet with poor heat transport, all the water could freeze on the night side, leaving the day side as a scorched desert. With good circulation, water could remain liquid across much of the surface. The difference between these scenarios determines whether the planet could support life, and whether that life might be detectable from Earth. Detecting life itself requires finding biosignatures, gases that are produced by living organisms and wouldn't persist in the atmosphere without continuous replenishment. Oxygen is the classic example. On Earth, photosynthetic organisms produce vast amounts of oxygen. Without them, oxygen would rapidly combine with rocks and disappear from the atmosphere. Finding oxygen around another planet doesn't guarantee life, but it strongly suggests biological activity. Methane is another candidate. On Earth, methane comes from both biological and geological sources. Bacteria in swamps produce methane. Volcanic activity releases it. Finding methane alone doesn't prove life exists. But finding methane and oxygen together creates a stronger case. These gases react with each other, so their simultaneous presence suggests something is actively producing them. Life is the most obvious explanation. The problem is false positives. Geological processes can produce oxygen under certain conditions. Photochemistry in the upper atmosphere can generate small amounts. Methane can accumulate if volcanic activity is high and chemical reactions are slow. We need multiple lines of evidence, combinations of gases that can't be easily explained by non-biological processes. And we need to understand the planet's geology, its stars' activity, and its atmospheric chemistry well enough to rule out alternative explanations. TRAPPIST-1's stellar activity complicates biosignature detection. The star's flares produce ultraviolet radiation that can break apart atmospheric molecules, creating fragments that recombine in unexpected ways. This can generate false biosignatures, gases that look biological but are actually products of stellar radiation. Distinguishing between life and stellar chemistry requires understanding both processes in detail. The search extends beyond just looking for familiar gases. Life on Earth produces thousands of different compounds. Some, like dimethyl sulfide, are produced almost exclusively by marine organisms. Others, like certain chlorinated compounds, come from specific types of bacteria. These trace gases are harder to detect than oxygen or methane, but they're more specific. Finding them would provide stronger evidence for life. But it also requires knowing what to look for and having instruments sensitive enough to detect gases present at parts per billion. Computer models help predict what atmospheres around TRAPPIST-1 planets might look like under different conditions. Scientists simulate planets with various compositions, different amounts of volcanic activity, different ocean coverage, and different types of life. Each simulation produces a predicted spectrum, a pattern of light absorption that would result from that specific combination of conditions. By comparing observed spectra to these models, researchers narrow down which scenarios match reality. These models reveal surprising possibilities. A planet covered entirely by ocean might have an atmosphere dominated by water vapor and nitrogen. A volcanic world could have a thick carbon dioxide atmosphere with sulfur compounds. A planet with extensive forests might show strong oxygen signals alongside organic vapors. Each possibility requires different observational strategies and different interpretations of the data we collect. The outer planets, TRAPPIST-1F and G, orbit in the system's outer habitable zone. They receive less stellar energy, making them colder than the inner worlds. But cold doesn't mean lifeless. Jupiter's moon Europa and Saturn's moon Enceladus both have subsurface oceans beneath icy crusts, maintained by tidal heating. TRAPPIST-1's outer planets might follow similar patterns, with frozen surfaces hiding liquid water oceans below. Life in these oceans wouldn't show up in atmospheric observations, but it could still exist. detecting subsurface oceans requires different techniques. Scientists look for magnetic fields generated by conductive fluids moving through the planet's interior. They search for evidence of geological activity that might indicate internal heat. They measure how the planet's gravity changes as it orbits, which can reveal whether a liquid layer exists beneath the surface. These observations are harder to make than atmospheric studies, but they're possible with sufficiently powerful telescopes and patient observation. The timeline for answering these questions stretches far into the future. Webb will observe TRAPPIST-1 planets for years, accumulating data transit by transit. Future telescopes, currently in the planning stages, will build on this foundation. The extremely large telescope, under construction in Chile, will have a mirror 39 meters across, dwarfing any existing ground-based telescope. It could directly image planets around nearby stars and study their atmospheres with unprecedented detail. But it won't be operational until the 2030s. Meanwhile, the search continues with existing tools. Ground-based telescopes track the system constantly, measuring changes in stellar activity and refining our understanding of planetary orbits. Space telescopes like Hubble and Spitzer have contributed observations, though neither was optimized for this kind of work. Webb carries the immediate burden, producing results that will shape the next decade of research. What we learn at TRAPPIST-1 will influence how we approach thousands of other planetary systems. If red dwarf planets can maintain atmospheres despite stellar activity, it validates searching for life around the galaxy's most common stars. If they can't, our focus shifts to sun-like stars, which are rarer but potentially more hospitable. Either outcome provides crucial information, but one expands our search space while the other constrains it dramatically. The 7 worlds of TRAPPIST-1 aren't just interesting objects. They're test cases for planetary habitability, laboratories where we can study how planets form, devolve, and maintain conditions suitable for life. Each observation adds another piece to a puzzle that spans astronomy, geology, atmospheric science, and biology. And somewhere in that puzzle lies an answer to whether we're alone. The search for biosignatures at TRAPPIST-1 depends on understanding what counts as proof. Oxygen in an atmosphere sounds like clear evidence of life, but nature produces oxygen through non-biological processes too. Ultraviolet radiation can split water molecules, releasing hydrogen into space and leaving oxygen behind. Photochemistry in carbon dioxide-rich atmospheres can generate small amounts of oxygen. The presence of oxygen alone isn't enough. Scientists need to find combinations of gases that can't coexist without constant replenishment from biological activity. Methane and oxygen together create such a combination. In Earth's atmosphere, these two gases react with each other, destroying both within years. Yet both persist because life constantly produces them. Plants generate oxygen. Bacteria in wetlands and animal digestive systems produce methane. Without this continuous input, both gases would vanish. Finding them together on a distant planet would suggest something actively maintains that chemical imbalance. But even this signature has caveats. Volcanic activity produces methane. Subsurface chemical reactions can release it. The ratio matters. The concentrations matter. The presence of other gases that might explain the pattern matters. A complete biosignature profile requires multiple lines of evidence converging on the same conclusion. No single measurement proves life exists. Only patterns that become progressively harder to explain through geology alone build a convincing case. Water vapor presents another layer of complexity. Every habitable planet should have water in its atmosphere, but how much? Too little suggests a dry world with limited liquid water on the surface. Too much might indicate a runaway greenhouse effect, where oceans evaporate and the planet becomes Venus-like. The amount of water vapor, its distribution through the atmosphere, and how it changes with planetary seasons all provide clues about surface conditions. Clouds complicate everything. They block light, making it harder to analyze atmospheric composition beneath them. They reflect starlight, changing how bright the planet appears during transit. They form at different altitudes depending on temperature and pressure, creating layers that absorb different wavelengths. A planet with permanent cloud cover might hide its most interesting features. Scientists develop techniques to peer through clouds, using wavelengths less affected by water droplets or ice crystals, but every cloud layer reduces the quality of data collected. TRAPPIST-1's variability adds another challenge. The star dims and brightens as dark spots rotate across its surface. It produces flares that temporarily increase its brightness. These changes affect how much light reaches each planet and how that light interacts with planetary atmospheres. When the star flares, it pumps extra energy into the upper atmosphere, potentially driving chemical reactions that wouldn't normally occur. To identify biosignatures, scientists must separate signals caused by stellar activity from signals caused by planetary processes. This requires observing the system repeatedly over months and years. A single transit shows what the atmosphere looks like at one moment. Multiple transits reveal patterns. Does the atmospheric composition change with seasons? Does it respond to stellar flares in predictable ways? Does it remain stable over time, suggesting established cycles rather than temporary events? Only long-term monitoring answers these questions. The inner planets, especially TRAPPIST-1b and C, face the harshest conditions. They orbit so close that stellar radiation strips away their atmospheres over geological timescales. Computer models show that planets this close to active red dwarfs lose massive amounts of atmosphere, potentially evaporating entire oceans worth of water into space. Yet these planets might retain thick atmospheres if they started with enough volatile material. Or they might be airless rocks, stripped bare billions of years ago. Webb's first observations of TRAPPIST-1b suggested minimal atmosphere, but the data wasn't conclusive. The planet absorbed light consistent with bare rock, but certain atmospheric compositions could produce similar results. Carbon dioxide-rich atmospheres without clouds might appear nearly identical to no atmosphere at all. Distinguishing between these scenarios requires additional observations at different wavelengths, building a complete picture of what light the planet absorbs and reflects. TRAPPIST-1c showed slightly more promise. Observations hinted at possible atmospheric features, though again, the data remained ambiguous. The challenge with these inner planets isn't just detecting atmospheres. It's determining whether any detected atmosphere is primordial, left over from the planet's formation, or secondary, produced by volcanic outgassing after the primordial atmosphere was lost. A secondary atmosphere would indicate ongoing geological activity, which requires internal heat. Internal heat suggests a molten core, which could generate magnetic fields, which might protect against stellar radiation. The middle planets, TRAPPIST-1d, E, and F, occupy the sweet spot where temperatures could allow liquid water. Computer models place them in or near the habitable zone, but models depend on assumptions. How reflective is the surface? How much greenhouse warming occurs? What's the atmospheric composition? Small changes in these parameters shift the habitable zone boundary significantly. A planet right at the edge might be habitable or frozen depending on factors we haven't measured yet. TRAPPIST-1e draws particular attention because it receives stellar energy similar to what Earth receives from the Sun. Its size and density closely match Earth's. Its orbital period of 6 days means it's tidally locked, with one side permanently facing the star and the other in eternal darkness. This creates extreme temperature gradients that drive powerful atmospheric circulation. Air heated on the day side rises and flows toward the night side, where it cools and sinks, creating planet-wide wind patterns unlike anything Earth experiences. These winds might actually help maintain habitable conditions. They transport heat from the scorched day side to the frozen night side, moderating temperatures across the planet. Without this heat redistribution, the day side might be too hot for liquid water while the night side freezes solid. But with strong enough winds, a band of moderate temperature could exist between the two extremes, possibly sustaining liquid water in a ring around the terminator, the boundary between day and night. Testing this hypothesis requires measuring how temperature varies across the planet's surface. As TRAPPIST-1e orbits, different parts of its surface face Earth. By observing how much infrared light the planet emits during different parts of its orbit, scientists can map temperature variations. A planet with strong heat redistribution shows less temperature variation than one without. These observations are challenging because the planet is small and the temperature difference is subtle, but Webb's infrared instruments are designed precisely for this work. Tidal locking also affects magnetic fields. Earth's magnetic field comes from its rotating molten core. TRAPPIST-1e doesn't rotate relative to its star, though it does rotate once per orbit relative to the rest of the universe. Whether this slower rotation can sustain a magnetic field remains uncertain. Some models suggest yes, others no. Without a magnetic field, stellar wind and radiation could strip the atmosphere over time. Detecting or ruling out magnetic fields on exoplanets requires observing how stellar wind interacts with the planet, looking for signatures of deflection that would indicate a protective magnetic bubble. The possibility of moons adds another variable. Earth's moon stabilizes our planet's axial tilt, preventing wild climate swings. It drives tides that might have been important for the origin of life. TRAPPIST-1's planets could have moons, though detecting them is nearly impossible with current technology. A large moon would affect the planet's orbit in measurable ways, creating tiny variations in transit timing that repeat with the moon's orbital period. Searching for these signals requires years of precise observations and sophisticated data analysis. Water worlds represent another scenario that might exist at TRAPPIST-1. If a planet formed farther from the star and migrated inward, it might have started as an icy body that melted as it entered warmer regions. The result would be a planet with global oceans potentially hundreds of kilometers deep, with no exposed land. Such planets might be common around red dwarfs, and they present unique habitability questions. Deep oceans with no seafloor contact limit the availability of nutrients. On Earth, life depends on cycles that involve both land and sea. Minerals weather from rocks, wash into oceans, and feed marine ecosystems. A water world lacks this cycle. Life might still exist near hydrothermal vents on the ocean floor, similar to Earth's deep-sea ecosystems, but it would face constraints. Whether complex life could evolve under these conditions remains speculative. High-pressure ice adds another twist. At sufficient depth, water pressure becomes so intense that water molecules form exotic ice structures that remain solid despite warm temperatures. A water world might have a liquid ocean layer sitting atop a thick shell of high-pressure ice, which itself rests on a rocky core. This creates isolated environments. Life in the upper ocean couldn't access nutrients from the core. Life near the core couldn't access energy from the star. Understanding whether such planets exist at TRAPPIST-1 requires measuring their densities precisely and modeling their internal structures. The outermost planet, TRAPPIST-1h, remains the least studied. It orbits every 20 days, making transits rare. Less data means less certainty about its properties. It might be a frozen world, or it might receive enough tidal heating from gravitational interactions with other planets to maintain subsurface liquid. Each observation slowly fills in details, but years of work remain before we understand this distant member of the system. The search for life doesn't stop at finding water or oxygen. Those are starting points, not conclusions. Life leaves traces beyond basic chemistry. On Earth, organisms have transformed the planet's surface in ways detectable from space. Forests change reflectivity. Phytoplankton alter ocean color. Seasonal cycles create patterns. Cities glow at night. Finding life on TRAPPIST-1's planets won't come from a single measurement, but from accumulating evidence that something beyond geology and chemistry is happening. Biosignatures fall into categories. Atmospheric biosignatures involve gases that shouldn't persist without constant replenishment. Oxygen is one example, but it's not the only one. Methane in the presence of oxygen is intriguing because these gases react and destroy each other on geological timescales. Finding both together suggests something continuously produces them. On Earth, that something is life. Microbes produce methane. Plants produce oxygen. Together they create an atmospheric imbalance. Surface biosignatures involve changes visible when observing the planet's surface. Vegetation reflects infrared light differently than bare rock or water. This creates a signature called the red edge, named for the sharp increase in reflectivity at specific wavelengths. Detecting this requires observing the planet as it rotates, watching how light changes as different regions face the observer. Seasonal biosignatures involve patterns that repeat with the planet's orbit. If TRAPPIST-1e has seasons, vegetation might grow and recede, changing the planet's appearance. Monitoring this requires observations spread across multiple orbits, watching for repeated patterns that match environmental cycles. But every biosignature has false positives. Oxygen can come from water molecules breaking apart under ultraviolet light. Methane seeps from geological processes. Surface changes might be dust storms or ice formation. Seasonal patterns could be atmospheric circulation. The challenge is distinguishing biology from everything else. This requires multiple independent measurements. If oxygen appears alongside other gases in unusual ratios, if surface features change in ways consistent with growth rather than weather, if patterns persist across years in stable configurations, the case for life strengthens. No single observation proves anything. The weight of evidence accumulates. Technosignatures represent another approach. Rather than searching for life's chemical traces, we look for technology. Radio signals, laser pulses, atmospheric pollution from industrial processes, structures large enough to see from interstellar distances. This assumes life not only exists but has developed technology. That's a much stronger assumption than looking for microbes, but it has advantages. Technology produces signals far stronger than biology. A radio transmitter can outshine a star at specific frequencies. Industrial pollution creates atmospheric signatures unlike anything natural. The challenge is knowing where to look and what to look for. TRAPPIST-1's proximity makes it an obvious target. The Breakthrough Listen initiative has already scanned these planets for radio signals. So far, nothing. But absence of evidence isn't evidence of absence. Maybe they don't use radio. Maybe they do, but we haven't listened at the right time or frequency. Maybe technology is rare. Maybe it's common, but civilizations don't last long enough to overlap with our listening period. Contamination concerns work both ways. When humans eventually send probes to other star systems, we risk contaminating those worlds with Earth life. Hardy microbes could survive spaceflight. If they reach a habitable planet, they might multiply, potentially destroying or altering native ecosystems before we even know those ecosystems exist. Planetary protection protocols exist to prevent this, but they're designed for solar system exploration. Interstellar missions face different challenges. Travel times span decades or centuries. Sterilization must last that long. We also worry about contaminating our own measurements. If we send a probe that lands on TRAPPIST-1e and later detects organic molecules, how do we know those molecules weren't brought from Earth? Future missions will require extreme care in design, construction, and operation to ensure any discoveries are real. Time introduces profound complications. TRAPPIST-1's life takes 40 years to reach us. When we observe these planets, we see them as they were 4 decades ago. If we detect a biosignature today, it represents life that existed when humanity had just begun studying exoplanets. If we send a signal and receive a reply, nearly a century passes. This delay affects how we plan observations and interpret results. It also raises philosophical questions. What if life existed but went extinct? What if it's about to emerge but hasn't yet? We're looking at a snapshot, not a live feed. Everything we learn is historical. The TRAPPIST-1 system's age matters too. The star is roughly 8 billion years old, nearly twice the Sun's age. Life on Earth appeared within the first billion years after the planet formed. If the same happened at TRAPPIST-1, life there has had billions of years longer to evolve. This cuts both ways. More time means more opportunity for life to arise, adapt, and diversify. But it also means more time for catastrophes. Asteroid impacts, stellar flares, atmospheric loss, any number of events could have wiped life out multiple times. Ancient systems might be graveyards. Or they might host biospheres far more complex than Earth's, with ecosystems that ever find themselves across eons of selection and adaptation. Comparing timelines between systems reveals how contingent everything is. Earth's history includes 5 major mass extinctions, countless minor ones, and several near-total sterilizations. Each reset evolution's progress. If TRAPPIST-1's planets experienced fewer catastrophes, life might be more advanced. If they experienced more, it might be simpler or absent. We have no way to predict this without observing. The Fermi paradox looms over all discussions of life beyond Earth. If planets are common and life arises readily, where is everyone? Why don't we see evidence of civilizations? TRAPPIST-1 offers a test case. If we search thoroughly and find nothing, that tells us something about how rare or fragile complex life is. If we find microbes but no technology, that suggests biological life is common but technological civilizations are rare. If we find both, it challenges our assumptions about how often intelligence emerges. Observation strategies continue evolving. Early work focused on basic planet detection and characterization. Current efforts target atmospheric composition. Future missions will map surfaces, search for seasonal changes, and monitor long-term atmospheric stability. Each generation of instruments reveals new details. Webb's observations will continue for years, building datasets that allow comparison across seasons and orbits. Ground-based telescopes, especially the upcoming extremely large telescopes, will complement space observations. These giant instruments, with mirrors 30 to 40 meters across, can detect faint atmospheric signals Webb might miss. They'll also observe at different wavelengths, providing independent measurements. Direct imaging remains a distant goal. Current instruments can't separate a planet's light from its star's glare except in rare cases involving young, hot planets orbiting far from bright stars. TRAPPIST-1's planets are too close and too cool for this technique. But future technologies might succeed. A space telescope equipped with a star shade, a precisely positioned screen that blocks starlight while allowing planet light through, could image these worlds directly. This would reveal surface features, cloud patterns, and possibly even continents and oceans. Such missions are being designed now but won't launch for decades. When they do, TRAPPIST-1 will be among the first targets. Sample return missions, though far beyond current capability, represent the ultimate goal. A probe that travels to TRAPPIST-1, lands on a planet, collects samples, and returns to Earth would answer questions no remote observation can. It would take centuries with current propulsion technology. Faster systems are theoretical. Breakthrough Starshot proposes using powerful lasers to accelerate tiny probes to 20% of light speed, reducing travel time to 40 years. These probes couldn't slow down or return, but they could transmit data during a brief flyby. Even this ambitious concept faces enormous engineering challenges. Whether it's practical remains uncertain. Regardless of technical hurdles, the scientific motivation is clear. TRAPPIST-1 offers the best near-term opportunity to answer whether life exists beyond Earth. The discovery of this system changed how we think about planetary systems. Before TRAPPIST-1, we knew planets could orbit red dwarfs, but we didn't expect systems this compact or this rich. Its existence suggests similar systems are common. Thousands of red dwarfs lie within 100 light-years. If even a fraction host planet systems like TRAPPIST-1, nearby habitable worlds might number in the hundreds. This changes the scale of the search. We're not looking for rare exceptions but for common outcomes of planet formation. The question shifts from whether habitable planets exist to which ones host life. Cultural impact extends beyond science. TRAPPIST-1 appears in fiction, art, and public imagination as a symbol of possibility. It represents a place we can almost touch, close enough that future generations might visit, real enough that we can study it seriously. Unlike vague discussions of life in the universe, TRAPPIST-1 is specific. It has coordinates. It has planets with names. It has properties we can measure. This concreteness makes the search for life feel tangible rather than abstract. When we ask whether life exists elsewhere, we can point to an actual place and say, we're checking there. The answer matters not just scientifically but philosophically. Finding life would confirm we're not alone. Finding nothing would raise questions about how rare life is and whether intelligence is a cosmic accident. Either way, the search itself transforms us. The process of looking forces us to confront assumptions about life's requirements, challenges our understanding of habitability, and tests the limits of our technology. Every observation teaches us something new, whether or not we find what we're searching for. The data we collect today forms the foundation for discoveries decades from now. Results from Webb's observations won't arrive in a single dramatic announcement. Science rarely works that way. Instead, papers will appear describing atmospheric compositions, temperature structures, and chemical inventories. These technical reports will gradually build a picture of what these worlds are actually like. Some findings will exclude certain possibilities. If a planet shows no water vapor, we'll know its surface is dry. If another shows abundant methane without oxygen, we'll know it's not Earth-like. Negative results matter as much as positive ones. They narrow the search space and guide future observations. Other findings will open new questions. Detecting unexpected molecules might indicate processes we don't understand. Seeing atmospheric patterns that change with time could reveal weather systems or seasonal cycles. Each answer generates new questions, pushing the investigation deeper. The real challenge lies in interpretation. Atmospheric chemistry is complex. The same molecule can form through biological or geological processes. Oxygen, often considered a biosignature, can be produced without life through water vapor dissociation if ultraviolet radiation is strong enough. Methane can emerge from volcanic activity or serpentinization, a chemical reaction between water and certain rocks. Distinguishing between these scenarios requires careful modeling and multiple lines of evidence. Context matters enormously. A small amount of oxygen might be geological noise. Large amounts combined with methane would be harder to explain without life. Phosphine, a molecule that breaks down quickly, would be especially interesting because it needs constant replenishment. On Earth, life produces it. Whether geological processes can generate significant quantities remains debated. Finding it on TRAPPIST-1e would trigger intense scrutiny and follow-up observations. Temperature measurements provide crucial context for interpreting chemistry. If a planet's surface is too hot, water can't remain liquid. If it's too cold, life as we know it can't function. Webb can estimate surface temperatures by measuring thermal emission, the infrared glow objects emit based on their heat. Comparing these temperatures to models tells us weather conditions allow liquid water. Clouds complicate this analysis. They reflect starlight and trap heat, altering surface temperatures in ways that depend on their altitude, composition, and coverage. Thick cloud decks might make a planet's surface warmer than expected, while high-thin clouds could cool it. Detecting clouds requires observing how a planet's brightness changes at different wavelengths. Water clouds scatter blue light more than red. Sulfuric acid clouds behave differently. By measuring these spectral signatures, we can infer cloud properties. This matters because clouds affect habitability. Too much cloud cover blocks starlight, reducing photosynthesis. Too little allows harmful radiation to reach the surface. The right amount creates a stable climate. Magnetic fields play a role we can't yet measure directly but must infer. A planet's magnetic field shields its atmosphere from stellar wind, streams of charged particles that erode atmospheres over time. Earth's magnetic field protects our atmosphere. Mars lost most of its atmosphere because it lacks a strong field. Red dwarfs produce powerful flares that accelerate atmospheric loss. Without magnetic protection, even a planet in the habitable zone might lose its atmosphere within hundreds of millions of years. Whether TRAPPIST-1's planets have magnetic fields depends on their internal structure. Planetary magnetic fields are generated by liquid metal cores churning through convection. This requires a planet to be large enough to stay geologically active and have the right composition. TRAPPIST-1e and F might meet these criteria. The others might not. Tidal heating, caused by gravitational squeezing as planets orbit, could keep interiors molten even if they'd otherwise cool. This might generate magnetic fields where they wouldn't normally exist. We won't know until we develop techniques to detect planetary magnetic fields remotely. One proposed method involves measuring how stellar wind particles interact with a planet's magnetosphere, creating radio emissions we could detect. This technology doesn't exist yet but could emerge within decades. Tidal locking introduces unique challenges and opportunities. If these planets always show the same face to their star, they experience permanent day on one side and permanent night on the other. Heat distribution becomes critical. Without efficient atmospheric circulation, the day side could be too hot while the night side freezes solid. Water would evaporate on one side and condense as ice on the other, eventually leaving the planet dry. But if the atmosphere is thick enough, winds could transport heat from day to night, creating a habitable twilight zone between extremes. This band, where temperatures remain moderate, might be the most favorable region for life. Ocean worlds would handle tidal locking differently. Water's high heat capacity allows it to store and transport thermal energy efficiently. Global oceans could circulate heat around the planet, preventing extreme temperature differences. This makes ocean worlds potentially more stable than rocky planets with thin atmospheres. Whether TRAPPIST-1's planets have global oceans depends on their formation history and subsequent evolution. If they formed beyond the snow line and migrated inward, they might have started water-rich. Subsequent atmospheric loss and surface processes would determine how much water remains today. Geological activity offers another piece of the habitability puzzle. Active geology recycles nutrients, releases gases that replenish atmospheres, and creates diverse environments. Volcanism on Earth releases carbon dioxide, which regulates climate over geological timescales. Without volcanism, carbon dioxide gets locked in rocks and the greenhouse effect weakens, eventually making the planet too cold. Plate tectonics, Earth's system of moving crustal plates, drives this recycling. Whether small planets can maintain plate tectonics is uncertain. Earth might be near the lower size limit for this process. TRAPPIST-1's planets, being slightly smaller, might not have plate tectonics. But they could have other forms of geological activity. Stagnant lid tectonics, where a single rigid crust covers a convecting interior, could still drive volcanism. Tidal heating from gravitational interactions with neighboring planets could provide additional energy for geological processes. This might keep smaller planets active longer than they'd otherwise remain. Biosignatures fall into several categories. Gas phase biosignatures are molecules in the atmosphere that life produces. Oxygen, methane, and phosphine are examples. Surface biosignatures are features visible on a planet's surface that indicate life, such as vegetation's distinctive reflectance spectrum. Temporal biosignatures are changes over time that suggest biological cycles, like seasonal variations in atmospheric composition. Each type requires different observation techniques. Gas phase biosignatures are most accessible now because we can study them through transit spectroscopy. Surface biosignatures need direct imaging, which isn't yet possible for these planets. Temporal biosignatures require long-term monitoring, observing the same planet repeatedly over months or years to detect changes. Webb can provide some temporal coverage, but dedicated missions would do better. False positives remain a serious concern. A false positive occurs when we detect something that looks like a biosignature but actually has a non-biological origin. This could mislead us into announcing the discovery of life when none exists. The scientific community would require extraordinary evidence before making such a claim. Multiple independent observations, thorough modeling to rule out non-biological explanations, and peer review by experts would all be necessary. Even then, uncertainty would remain until we could study the planet more directly. False negatives are equally important. A false negative happens when life exists but we fail to detect it. This could occur if life uses biochemistry different from Earth's, producing molecules we don't recognize as biosignatures. It could also happen if life exists but doesn't produce detectable atmospheric signatures, perhaps because it's confined to subsurface oceans or exists in small quantities. We might miss life simply because we're not looking in the right way. The possibility of non-Earth-like life expands the search dramatically. All our biosignature concepts are based on Earth life, which uses carbon-based chemistry, liquid water, and specific metabolic pathways. Life elsewhere might work differently. Silicon-based biochemistry, liquid methane as a solvent, or completely different metabolic processes could exist. We wouldn't recognize these as biosignatures because we don't know what to look for. This limitation means our search is biased toward finding life like ours. We might fly right past evidence of alien life without recognizing it. Addressing this requires creativity and open-mindedness. Some researchers propose looking for disequilibrium rather than specific molecules. Disequilibrium occurs when atmospheric chemistry is out of balance, with reactive gases coexisting when they should react and disappear. On Earth, oxygen and methane shouldn't coexist because they react chemically. They do because life constantly produces both. Detecting similar disequilibria elsewhere might indicate life even if the specific molecules differ from Earth's biosignatures. Artificial intelligence and machine learning are being applied to biosignature detection. These algorithms can analyze vast datasets, identifying patterns humans might miss. They can also model thousands of possible atmospheric compositions, helping distinguish biological from geological signatures. Training these systems requires careful work. They learn from examples, so if we only show them Earth-like biosignatures, they'll only recognize those. Expanding their training to include hypothetical non-Earth biochemistries improves their flexibility. As these tools mature, they'll become essential for processing the enormous amounts of data future telescopes will collect. Human intuition and machine analysis will work together, each compensating for the other's weaknesses. The timeline for answers stretches across decades. Webb's observations will continue for years, gradually building a comprehensive picture of TRAPPIST-1's planets. Follow-up missions will launch in the 2030s and 2040s, each more capable than the last. By mid-century, we might have definitive answers about whether these worlds host life. Or we might find the question is more subtle than we expected, requiring even more sophisticated observations. Either outcome advances our understanding. The search for life around TRAPPIST-1 sits within a broader revolution in how we understand planets and their potential for habitability. 50 years ago, we knew of no planets beyond our solar system. Today, we've confirmed over 5,000 exoplanets, with thousands more candidates awaiting verification. This explosion of discovery fundamentally changed our perspective. Planets aren't rare cosmic accidents. They're the natural outcome of star formation, appearing around most stars we examine closely enough. Rocky planets in particular seem common, suggesting the raw materials for life are widespread throughout the galaxy. TRAPPIST-1's system represents something special within this abundance. Most exoplanets we've found orbit much hotter stars than TRAPPIST-1. Hot stars age quickly and emit intense radiation that can strip planetary atmospheres. They also produce more ultraviolet light, which damages biological molecules. TRAPPIST-1's cool, stable nature provides a gentler environment. Its planets won't face the radiation bombardment that plagues worlds around hotter stars. The star will shine for trillions of years, far longer than our sun's remaining lifespan. If life needs time to evolve complexity, TRAPPIST-1 offers nearly unlimited patience. The system's architecture also matters. Having 7 planets packed so closely creates gravitational interactions that could prove beneficial. Tidal forces from neighboring planets might generate internal heating, keeping subsurface oceans liquid even on worlds that receive little starlight. This expands the habitable zone beyond simple calculations based on surface temperature. A planet might look too cold to support life when considering stellar radiation alone, yet maintain liquid water underground through tidal heating. Europa and Enceladus in our solar system demonstrate this principle. Both moons orbit far from the Sun where surface temperatures plunge below -100 degrees Celsius, yet both harbor subsurface oceans kept liquid by tidal flexing. TRAPPIST-1's planets might experience similar conditions, creating multiple environments where life could emerge and persist. Understanding these worlds requires thinking beyond Earth-based assumptions. Our planet's history shapes how we imagine habitability. We picture continents and oceans, a nitrogen-oxygen atmosphere, and a protective magnetic field. But these features aren't universal requirements. Venus-like worlds with crushing atmospheric pressure and sulfuric acid clouds seem hostile, yet life adapted to those conditions would thrive. Ocean worlds with no land whatsoever could support rich biospheres beneath kilometers of water. Planets with thin atmospheres and low gravity might develop life in underground caves where conditions remain stable. The challenge lies in recognizing life signatures when they emerge from these alien contexts. We're building a library of possibilities, modeling how different planetary conditions produce different atmospheric chemistries. This library will help interpret observations when we finally collect them. If we detect an atmosphere that doesn't match any known geological process but fits a biological model, we'll have found something significant. The strength of that claim depends on how thoroughly we've ruled out alternatives. Geology can mimic biology in frustrating ways. Volcanic outgassing produces many of the same molecules life creates. Lightning can generate complex organic compounds without any biological involvement. Photochemistry driven by stellar ultraviolet light creates chemical reactions that might look like metabolism. Distinguishing true biosignatures from these false positives requires detailed modeling and multiple lines of evidence. No single observation will suffice. We need patterns, consistency across different measurements, and explanations that make sense given what we know about the planet's geology and atmospheric physics. The scientific method demands skepticism. When we think we've found something extraordinary, we must work harder to disprove it than to confirm it. This approach frustrates those who want quick answers, but it protects against embarrassment and ensures that when we do announce a discovery, it stands on solid ground. The search for life around TRAPPIST-1 will proceed with appropriate caution. Future missions will expand our capabilities dramatically. Concepts under development include star shades, massive spacecraft that fly in formation with telescopes, blocking starlight to reveal faint planets more clearly. Interferometry, combining light from multiple telescopes to create a virtual instrument larger than any single telescope could be, will provide unprecedented resolution. Direct imaging missions could photograph TRAPPIST-1's planets as distinct points of light rather than inferring their properties indirectly. Each technological advance brings us closer to definitive answers. Ground-based telescopes continue improving as well. Extremely large telescopes currently under construction will have mirrors 30 meters across, dwarfing today's largest instruments. Adaptive optics systems correct for atmospheric distortion in real time, sharpening images to approach theoretical limits. These facilities will contribute to TRAPPIST-1 studies, particularly for longer-term monitoring and follow-up observations of interesting findings from space telescopes. The combination of space and ground-based observations creates a comprehensive picture. Space telescopes avoid atmospheric interference but have limited lifespans and can't be easily upgraded. Ground-based telescopes can be maintained and improved indefinitely but must contend with Earth's atmosphere. Using both together compensates for each approach's limitations. We're entering an era where planetary characterization becomes routine rather than exceptional. TRAPPIST-1 won't be studied in isolation but as part of a broader sample of potentially habitable worlds. Comparative planetology, examining many similar worlds to understand common patterns and unique variations, will reveal which planetary characteristics matter most for habitability. Does magnetic field strength correlate with atmospheric retention? Do planets with active plate tectonics develop more complex biosignatures? Does the presence of a large moon stabilize climate in ways that benefit life? These questions require large samples. TRAPPIST-1 provides 7 data points in a single system, making it invaluable for testing hypotheses about planetary habitability. Public interest in these discoveries remains intense. Each announcement about TRAPPIST-1 generates global attention. This enthusiasm reflects humanity's deep curiosity about our place in the universe. Are we alone? The question resonates across cultures and throughout history. Modern science finally has tools to answer it. The results will reshape philosophy, religion, and our understanding of life's significance. Finding life elsewhere, even simple microbial life, would demonstrate that biology emerges readily when conditions permit. This would suggest the universe teems with life, most of it probably simple, but some fraction potentially complex or even intelligent. Not finding life would also teach us something important. If we examine dozens of seemingly habitable worlds and detect no biosignatures, we'd need to reconsider our assumptions. Perhaps life requires conditions rarer than we thought. Perhaps the transition from chemistry to biology involves improbable steps. Perhaps life emerges commonly but rarely persists long enough to produce detectable signatures. Each null result narrows the range of possibilities, guiding future searches toward more promising targets. The TRAPPIST-1 system will remain a focus of astrobiology for generations. Its proximity, the number of potentially habitable planets, and the relatively easy observing conditions make it an ideal laboratory for testing our methods and assumptions. Whatever we learn there will inform searches around other stars, building a framework for understanding planetary habitability across the galaxy. This knowledge serves practical purposes beyond satisfying curiosity. As we contemplate humanity's long-term future, the question of where else we might live becomes increasingly relevant. Understanding which worlds could support life helps identify potential destinations for future exploration or even colonization. These considerations remain distant, but they motivate current research. We study TRAPPIST-1 not just to find life elsewhere but to understand life's requirements and possibilities. This understanding might one day help us recognize or even create habitable conditions on worlds that initially seem barren. The line between studying exoplanets and studying Earth blurs as we realize the same principles govern both. Atmospheric chemistry, climate dynamics, and the interplay between geology and biology operate by universal physical laws. Insights gained from examining TRAPPIST-1 improve our understanding of our own planet's history and future. Climate science benefits particularly from exoplanet research. Studying worlds with different atmospheric compositions, stellar inputs, and planetary characteristics tests our climate models under extreme conditions. If our models accurately predict TRAPPIST-1's atmospheric behavior, we gain confidence in their predictions for Earth's changing climate. The exchange flows both ways. Our detailed knowledge of Earth's atmosphere and biosphere informs how we interpret observations of distant worlds. 40 light-years now feels simultaneously vast and intimate. Vast because even traveling at unrealistic speeds, reaching TRAPPIST-1 would take centuries. Intimate because we can study its planets in detail, watching their atmospheres change with seasons, measuring their compositions, and searching for signs of life. Technology has collapsed the observational distance even as the physical distance remains unbridgeable with current capabilities. We've become neighbors with TRAPPIST-1 in a way that would astonish astronomers from just decades ago. Their wildest dreams about characterizing distant worlds have become our routine observations. The next generation of instruments will push boundaries we can barely imagine today. What seems impossible now might become straightforward in 20 years. The pace of discovery accelerates as technology and understanding advance together. TRAPPIST-1's secrets will gradually yield to our persistent questioning, revealing whether those distant worlds harbor the universe's most profound mystery or remain silent, waiting for life to arrive from elsewhere. The answer matters less than the journey itself. We stand at a threshold previous generations could only imagine. 7 worlds orbit a dim star close enough to study yet far enough to remain mysterious. Whether they harbor life or stand barren, whether their atmospheres persist or have vanished, whether oceans cover their surfaces or ice locks their water away, each discovery reshapes what we know about planets, habitability, and our own existence. TRAPPIST-1 represents more than coordinates in space. It's a mirror reflecting our assumptions back at us, forcing us to confront what we think we know about life's requirements. Every observation challenges conventional thinking. Every measurement refines theories built on studying a single example, Earth. We're learning that planets don't follow simple rules, that habitability isn't binary, and that nature experiments with configurations we never anticipated. The telescopes currently pointed at this system will continue their work for years. Data accumulates slowly, each transit adding fragments to an incomplete picture. Future instruments will fill gaps, answer questions the current generation of telescopes can't address, and pose new mysteries we haven't yet imagined. The process feels frustratingly slow measured against human lifespans, but it's remarkably fast compared to the billions of years these worlds have existed. What we find at TRAPPIST-1 will influence how we search elsewhere. If red dwarf planets retain atmospheres despite stellar violence, thousands of nearby systems become prime targets. If they don't, our focus shifts to rarer, sun-like stars. Either way, we gain knowledge that directs future efforts and resources. The search expands or contracts based on what these 7 planets reveal about planetary survival around the galaxy's most common stellar type. Somewhere in the accumulated observations, patterns will emerge. Atmospheric compositions that make sense given the planet's histories. Temperature distributions that reveal how energy moves through alien air. Chemical signatures that either suggest biology or don't. The absence of life matters as much as its presence. Both outcomes advance understanding. Both guide the next phase of exploration. We're no longer wondering whether other worlds exist. We're studying specific places, measuring their properties, and determining whether they could host life. This shift from philosophical speculation to empirical investigation represents one of science's great transitions. The question of whether we're alone moves from metaphysics to physics, from belief to data, from wondering to knowing. TRAPPIST-1's planets won't yield their secrets quickly or easily. They'll make us work for every answer, forcing us to build better instruments, develop more sophisticated models, and think more carefully about what constitutes evidence. This struggle drives progress. The harder the question, the more we learn in pursuing it. 40 light-years away, 7 worlds orbit a star that will outlive our sun by trillions of years. They've existed for billions of years already. They'll continue existing long after human civilization has transformed or disappeared. Right now, in this brief window of time, we're looking at them. We're measuring them. We're learning what they are and what they might become. The universe doesn't care whether we find life elsewhere. Planets orbit stars according to gravity's laws regardless of what we discover or conclude. But we care. The question drives us to build telescopes, launch missions, and spend decades analyzing data. It pushes our technology and understanding forward. And eventually, we'll know. Not through revelation or assumption, but through patient observation and careful analysis. TRAPPIST-1 will tell us its story. We just have to listen long enough to hear it. Right now, somewhere in the darkness between stars, invisible predators drift through our galaxy. They have no light, no sound, no warning of their approach. And if one passed close enough to our solar system, we wouldn't see it coming until it was far too late. These are rogue black holes. Stellar corpses torn from their birthplaces, now wandering the Milky Way in complete silence. Scientists estimate there could be hundreds of millions of them out there, and we've barely detected a handful. The rest remain hidden, moving through space like cosmic ghosts, bending light around themselves, swallowing anything that crosses their path. What makes them truly terrifying isn't just their power. It's that we have almost no way to track them until they're already here. And when astronomers finally developed methods to spot these wanderers, what they found was deeply unsettling. Black holes form when massive stars collapse. We've known this for decades. A star 20 times the mass of our sun burns through its fuel, its core implodes, and gravity crushes everything into a point of infinite density. What's left behind is an object so dense that not even light can escape its pull. Most of these black holes stay where they formed, anchored in place by the remnants of their stellar neighborhood. But not all of them. When a massive star explodes as a supernova, the blast isn't always symmetrical. If the explosion throws more material in one direction than another, the newborn black hole gets kicked hard. Astronomers call these natal kicks, and they can launch a black hole across the galaxy at speeds exceeding 600 kilometers per second. That's more than 2 million kilometers per hour. Fast enough to escape the gravitational grip of its birthplace entirely. Once free, these objects become nomads. They don't orbit anything. They don't belong to any star system. They simply drift through the galaxy, following trajectories set by that violent birth moment, invisible and utterly indifferent to whatever lies in their path. Here's where it gets worse. Our galaxy has been forming stars for over 13 billion years. Millions of massive stars have lived and died in that time. Each one that met the right conditions created a black hole. And a significant fraction of those black holes received kicks strong enough to send them wandering. Do the math, and you arrive at a disturbing conclusion. The Milky Way should be filled with these things. Early estimates suggested tens of millions. More recent models push that number higher, potentially into the hundreds of millions. Picture that for a moment. Between 100 million and 400 million rogue black holes, drifting silently through the same space we occupy. Most are stellar mass black holes, between 5 and 50 times the mass of our Sun. Small by cosmic standards, but devastating by any measure that matters to us. And we can't see them. A black hole by definition emits no light. It's a hole in space where light goes to die. The only way we typically detect black holes is by watching how they affect their surroundings. If a black hole is pulling gas from a companion star, that gas heats up as it spirals inward, glowing brilliantly in X-rays before it vanishes beyond the event horizon. Binary systems like this are relatively easy to spot. We've cataloged dozens of them. But a rogue black hole traveling alone through empty space has nothing to feed on. No companion star. No accretion disk. No telltale X-ray signature. It's just a gravitational knot in the fabric of spacetime, moving silently through the void. For decades, astronomers assumed these objects were essentially undetectable. They were out there, sure, but finding them seemed impossible. Then someone realized we'd been thinking about the problem wrong. Even invisible objects reveal themselves through gravity. Einstein showed us this more than a century ago. Mass warps spacetime, and light follows those curves. When light from a distant star passes near a massive object, the object's gravity bends that light like a lens. If the alignment is precise enough, the background star appears to brighten temporarily as its light is magnified and focused toward us. Astronomers call this gravitational microlensing. The technique had been used successfully to find planets, distant stars, even other black holes in binary systems. But using it to hunt lone rogue black holes required a different approach entirely. You'd need to monitor millions of stars continuously, waiting for one to brighten in exactly the right way. The chances of catching such an event are microscopically small. The alignment has to be perfect, the timing has to be right, and you have to be watching that exact star at that exact moment. In 2011, a team of astronomers decided to try anyway. They pointed their telescopes toward the galactic bulge, the dense central region of the Milky Way where stars are packed close together. More stars mean more opportunities for alignment. They monitored the brightness of millions of stars simultaneously, searching for the characteristic signature of a black hole passing in front of them. For years, they found nothing conclusive. Hundreds of microlensing events, yes, but most could be explained by normal stars or brown dwarfs. Then in 2022, they announced something different. An event designated MOA-2011-BLG-191. The light curve was perfect. A star had brightened over several weeks, peaked, then faded back to normal. But the duration and shape of that brightening suggested something unusual. The lensing object wasn't a star. It was too massive and too dark. After ruling out other possibilities, the team concluded they detected a rogue black hole. Somewhere between 2 and 7 solar masses, drifting alone through the galaxy approximately 5,000 light-years from Earth. It had passed directly between us and a background star, briefly magnifying that star's light before continuing on its silent journey. This was the first time anyone had definitively detected an isolated black hole wandering through space. Not orbiting anything. Not feeding on anything. Just moving. And it raised an immediate question. If we found one, how many more are out there that we haven't found? The galaxy is enormous. 300 billion stars spread across 100,000 light-years. Even hundreds of millions of rogue black holes would be sparse in that volume. The chances of one passing close to any particular star are vanishingly small. But close is a relative term in space. A black hole doesn't need to hit something directly to affect it. Gravity works at a distance. If a rogue black hole passed within a few light-years of our solar system, we'd likely never notice. It would tug slightly on the orbits of distant comets in the Oort cloud, maybe nudge a few toward the inner solar system, but nothing catastrophic. Pass within 1 light-year, and the effects become more pronounced. Orbits destabilize. Long-period comets get redirected. The delicate gravitational balance that keeps our solar system stable starts to shift. Get closer than that, and things deteriorate rapidly. A black hole passing within the orbit of Neptune would gravitationally scatter the outer planets. Jupiter's orbit would shift. Saturn's rings might destabilize. The asteroid belt could be stirred into chaos, sending rocks careening through the inner solar system. Earth's orbit would change. Not immediately, not catastrophically in human terms, but enough to alter our climate over centuries. Enough to make our world unrecognizable. And if one passed within the orbit of Mars, we'd have months at best. Maybe weeks. The sun itself would be affected, its outer layers potentially stripped away as the black hole's gravity pulled at stellar material. Earth's orbit would become wildly elliptical or be ejected from the solar system entirely, flung into interstellar space to freeze in the darkness. The worst part isn't the destruction itself. It's the warning time. Or rather, the complete lack of it. Current detection methods only work when a rogue black hole passes directly in front of a background star from our perspective. By the time we detect that microlensing event, we're observing something that happened years or centuries ago, depending on the distance. The light we're seeing left that region of space long before we started watching. The black hole itself is already somewhere else entirely, continuing its journey along a path we can't predict. We have no early warning system. No way to scan ahead and spot an approaching threat. Gravitational wave detectors like LIGO can detect black hole mergers halfway across the universe, but a single black hole drifting through space produces no gravitational waves. It's silent on every wavelength we can measure, visible only through the brief distortion it causes when perfectly aligned with a distant light source. Astronomers are working on better detection methods. Upcoming surveys will monitor more stars more continuously, increasing the chances of catching microlensing events. The Vera Rubin Observatory, scheduled to begin operation soon, will photograph the entire visible sky every few nights, watching for anything that changes. That includes the subtle brightening caused by gravitational lensing. But even with better surveys, we're still looking at a reactive system. We find these objects after they've already passed, not before. And the galaxy is simply too large, too dark, too filled with empty space to monitor comprehensively. The number of rogue black holes out there almost certainly exceeds our ability to track them all. Which brings us to an uncomfortable probability calculation. With hundreds of millions of these objects wandering the Milky Way, and 13 billion years of galactic history behind us, what are the chances one has already passed close to our solar system? Or that one will in the future? The distances involved are staggering enough that the risk to any individual star system remains low over human timescales. But over millions of years, over billions, the odds shift considerably. And we're not just talking about direct hits. Even a distant passage could destabilize the Oort cloud, sending comets plunging toward the inner planets. Some researchers have suggested that periodic comet bombardments in Earth's history might be explained by exactly this mechanism. A rogue black hole passing through the outer solar system every few tens of millions of years, stirring up frozen debris and sending it inward. It's speculative, but it fits certain patterns in the geological record. And it suggests these invisible wanderers have been influencing our corner of space far longer than we've been here to notice. The galaxy's structure offers little comfort when you consider the mechanics. Rogue black holes don't travel in neat, predictable orbits like planets around a star. They follow paths determined by countless gravitational interactions over billions of years. A close encounter with another star system deflects the trajectory. Passage through a dense molecular cloud changes the velocity. The cumulative effect of these interactions creates something closer to a random walk than an orbital pattern. Which means prediction becomes functionally impossible beyond a certain distance. What makes this particularly unsettling is scale. We think of black holes as massive objects, and compared to everyday experience, they are. But in galactic terms, a stellar mass black hole is microscopic. The event horizon of a 10 solar mass black hole measures roughly 60 kilometers across. That's smaller than many cities. Now imagine trying to spot something that size, something that emits no light, against the backdrop of a galaxy 100,000 light-years in diameter. You're looking for a dark marble in an ocean at night. From another continent. The only reason we've detected any at all is because space isn't completely empty. Gas and dust exist between stars, thin beyond anything we'd call a vacuum on Earth, but present nonetheless. When a black hole moves through this tenuous material, it pulls some of it inward. That gas heats up through friction and compression, reaching temperatures where it emits X-rays. Not much. Not the brilliant accretion disks we see around supermassive black holes in galactic centers. Just a faint glow, barely detectable even with our most sensitive instruments. But here's the problem with using that detection method. It only works if the black hole happens to be passing through a region with enough gas to produce a visible signature. Most of interstellar space is far emptier than that. A black hole could pass within a light year of Earth, close enough to potentially affect the orbits of outer solar system objects, and we'd see nothing. No X-rays. No visible light. No radio emissions. Just gravitational effects we wouldn't notice until something started behaving strangely. The math on close approaches is genuinely disturbing. Researchers have calculated that a black hole passing within 50 astronomical units of the Sun, roughly the distance to the Kuiper belt, would disrupt the orbits of trans-Neptunian objects significantly. Within 20 astronomical units, orbital perturbations would extend to the giant planets. Closer than 10, and Earth's orbit itself becomes unstable over timescales ranging from centuries to millennia, depending on the exact trajectory and mass involved. These aren't extinction-level events in the immediate sense. The black hole doesn't need to hit us to cause catastrophic problems. Orbital changes of even a few percent would alter Earth's climate dramatically. Seasons would shift. The length of the year would change. If the orbit became more elliptical, we'd experience temperature swings between perihelion and aphelion far more extreme than current seasonal variations. Glaciation cycles would accelerate or halt entirely. Ocean currents would reorganize. Weather patterns would transform beyond recognition. Life on Earth has survived worse. Mass extinctions punctuate the fossil record, some far more severe than what an orbital disruption might cause. But those events unfolded over thousands or millions of years. Ecosystems had time to migrate, adapt, or collapse gradually. A black hole passage could destabilize things within decades. Too fast for agricultural systems to adjust. Too fast for species to migrate to new climate zones. Too fast for human civilization to reorganize around new realities. The truly nightmarish scenarios involve closer approaches. If a rogue black hole entered the inner solar system, say within Mars's orbit, the effects would be immediate and overwhelming. Earth's orbit wouldn't just shift slightly. It would change fundamentally. We might be ejected from the solar system entirely, flung into interstellar space along a trajectory determined by the exact angle and speed of the encounter. Or we might fall inward, spiraling toward the Sun over a timescale of centuries. Either way, Earth as a habitable planet would end. Ejection means freezing. Without the Sun's heat, surface temperatures would plummet to near absolute zero within years. The atmosphere would condense and freeze, falling as snow that would eventually cover the entire surface in a layer hundreds of meters thick. Oceans would freeze solid to their beds. Any life that survived would exist in deep subsurface environments, perhaps around geothermal vents, living off Earth's internal heat rather than solar energy. Human survival would require either impossible engineering or simply wouldn't happen. Falling inward carries its own horror. The journey toward the Sun would take time, but the end result is incineration. Earth's orbit decaying, bringing us closer to a heat source that already makes the equator brutal during summer. Temperatures would rise steadily. Oceans would boil away, The atmosphere would be stripped by solar wind. Eventually, the planet would be torn apart by tidal forces before ever reaching the solar surface, debris scattered across the inner solar system like a planetary corpse. The galaxy doesn't care about any of this. These events occur with statistical regularity across billions of star systems. Most stars will experience close encounters with rogue objects over their lifetimes. Some will be disrupted. Some will capture new planets or have existing ones stripped away. It's part of the normal evolution of galactic structure. We just happen to be conscious observers existing during a period when our particular star system hasn't experienced such an event recently. Recently, in this context, means within the last few 100 million years. The geological record shows no evidence of sudden orbital disruptions on that timescale. Earth's climate has varied, sometimes dramatically, but always within ranges consistent with predictable astronomical cycles. The Milankovitch cycles that drive ice ages operate over tens of thousands of years and result from subtle variations in Earth's orbital eccentricity and axial tilt. Not the kind of violent perturbations a black hole passage would cause. But absence of evidence isn't evidence of absence over longer timescales. Go back far enough, and the record becomes unclear. The early solar system was chaotic. Planets migrated. Giant impacts occurred. The late heavy bombardment around 4 billion years ago reshaped the inner solar system. Could some of that chaos have been influenced by a passing rogue black hole? Possibly. We have no way to determine that from current evidence. The gravitational signatures would have been erased long ago by subsequent evolution. What we can determine is frequency based on what we observe elsewhere. Studies of stellar velocities in our galactic neighborhood show occasional stars moving at speeds inconsistent with normal orbital patterns. Hypervelocity stars, traveling fast enough to escape the galaxy entirely. Some of these gained their speed through close encounters with the supermassive black hole at the galactic center. Others might have been accelerated by interactions with rogue black holes in the disk. The distribution of these fast-moving stars gives us clues about how often such encounters occur. The numbers suggest a close approach between a rogue black hole and a random star system happens perhaps once every few 100 million years within any given volume of space. That sounds reassuring until you remember we're talking about an entire galaxy containing hundreds of billions of stars. Multiply that out, and you get thousands of these encounters happening somewhere in the Milky Way right now. This moment. As you process these words, a black hole is likely disrupting a solar system dozens or hundreds of light years away. We'll never see it. Never detect it. Never know which star just had its planetary system torn apart. The speed at which these objects move creates additional problems for detection. Stellar velocities in our region of the galaxy average around 200 kilometers per second relative to the local standard of rest. A rogue black hole might be moving faster or slower, depending on its history, but it's in that general range. At those speeds, an object crosses 1 astronomical unit, the distance from Earth to the Sun, in about 2 months. It could traverse the entire solar system in less than a year. Detection, analysis, and response would need to happen within that window. Except we can't detect them reliably in the first place. And even if we could, what response exists? You can't deflect a black hole. You can't destroy it. You can't negotiate with fundamental physics. The only option would be evacuation, and evacuating Earth's population to somewhere safer runs into the obvious problem that there is nowhere safer within reach. Generation ships heading to other star systems would take thousands of years to reach destinations that might themselves be threatened by rogue black holes. Underground bunkers might preserve some fraction of humanity through orbital disruption, depending on severity, but only if Earth remains in a relatively stable orbit around the Sun. Ejection into interstellar space makes that impossible. The planet becomes uninhabitable too quickly for any bunker to matter. This is the situation we exist within. A galaxy filled with invisible threats following unpredictable paths at velocities that leave no time for meaningful response. The odds of a direct impact remain low over human timescales. Low enough that it doesn't make sense to lose sleep over it specifically. But the odds of an encounter somewhere in our cosmic neighborhood, close enough to affect our understanding of how stable planetary systems really are, sit much higher. The question becomes what kind of encounter would actually matter to us. Not just theoretically, but in ways we could measure or experience within human lifetimes. Start with gravitational influence at a distance. A stellar mass black hole passing within a few light years of the solar system wouldn't cause immediate catastrophe, but it would perturb the Oort cloud. That's the spherical shell of icy bodies extending roughly halfway to the nearest star, loosely bound to the Sun's gravity. Disturb that region, and you send comets falling inward toward the inner solar system. Not immediately. The journey takes thousands to millions of years depending on initial position and velocity. But once started, the process continues regardless of whether the black hole remains nearby. Historical impact records on Earth and the Moon show periodic increases in cratering rates. Some researchers have proposed these patterns correlate with the solar system's oscillation through the galactic plane, where stellar density runs higher. More stars means more gravitational perturbations. More perturbations means more comets get nudged loose. The mechanism makes sense even if the specific correlations remain debated. A rogue black hole passing through the Oort cloud would produce similar effects, just concentrated in time rather than spread across millions of years of gradual oscillation. The increased impact rate wouldn't sterilize Earth. Life has survived multiple impact events far worse than anything a perturbed Oort cloud could produce. But it would stress ecosystems, potentially triggering extinctions among larger organisms less able to shelter or adapt quickly. Human civilization, dependent on stable agriculture and infrastructure, would face serious challenges. Not extinction level, but enough to reshape societies and potentially set back technological development by centuries. That scenario assumes the black hole stays several light years away. Move it closer and effects intensify. At 1 light year out, roughly a quarter of the distance to Proxima Centauri, gravitational effects become more direct. The outer planets would experience measurable orbital perturbations. Nothing dramatic over human timescales, but enough to show up in precision tracking data. Jupiter's orbit might shift by fractions of a percent. Saturn's rings could develop new gaps or resonances as orbital periods change slightly. These aren't catastrophic alterations, but they'd be detectable, and they'd tell us something massive had passed nearby. The inner solar system would feel weaker effects at that distance. Earth's orbit wouldn't change noticeably within a single human lifetime. But over centuries, small perturbations accumulate. Climate patterns depend partly on Earth's orbital eccentricity and axial tilt. Alter those parameters even slightly and you change how solar energy distributes across the planet's surface. Ice ages have been triggered by orbital variations smaller than what a passing black hole at 1 light year might induce. Now bring it closer still. Half a light year. A tenth. At these ranges, we're talking about an object whose gravitational influence begins competing with the Sun's hold on the outer planets. Neptune and Uranus could experience significant orbital changes within decades. Their moons might be stripped away entirely, sent tumbling into new orbits around the Sun or ejected into interstellar space. The inner solar system would still remain relatively protected by distance and the sun's stronger local gravity, but relatively does heavy lifting in that sentence. At a tenth of a light year, maybe 3 months of travel time at typical stellar velocities, detection becomes theoretically possible through gravitational lensing. The black hole's gravity would bend light from background stars, creating a characteristic pattern of brightening and positional shifts as it moves across the sky. Dedicated surveys searching for such events could potentially spot it, given enough luck in the right observational geometry. But that requires the black hole to pass almost directly between us and cataloged background stars, and it requires astronomers to be looking at the right patch of sky at the right time with equipment sensitive enough to catch subtle lensing signatures. The odds aren't favorable. Even if detected, the warning time measured in months doesn't allow for much beyond observation and calculation. We'd watch it approach, model its trajectory, estimate its mass based on lensing strength, and project what effects it might have on planetary orbits. Then we'd wait to see if the models were right. If the black hole passes within the outer solar system itself, within Neptune's orbit, we've moved from theoretical concern to immediate crisis. At those ranges, orbital mechanics become chaotic in the technical sense. Small changes in initial conditions produce wildly different outcomes. Whether Earth remains in a stable orbit or gets perturbed into a more elliptical path, whether the perturbation is mild or severe, whether we end up closer to the Sun or farther away, all of this becomes sensitive to precise details of the black hole's mass, velocity, and trajectory. Run the simulation 1,000 times with slightly different starting parameters and you get 1,000 different results. Some show minimal impact. Others show Earth's orbit elongating enough to create extreme seasonal temperature swings. A few show ejection from the solar system entirely. The disturbing part isn't that ejection scenarios exist. It's that we couldn't predict which outcome would occur until the black hole was already here, moving through the system, its gravity actively reshaping orbital paths in real time. By then it's far too late for any response beyond documentation. Consider what ejection actually means. Earth doesn't crash into the black hole. It doesn't get torn apart by tidal forces unless the approach is extraordinarily close, within a few million kilometers. What happens instead is the planet gets gravitationally kicked, like a billiard ball struck at an angle. The velocity change might be only a few kilometers per second, but that's enough. Earth's orbital velocity around the Sun sits at about 30 kilometers per second. Add or subtract even a small fraction of that and you change whether the orbit remains bound to the Sun. Once unbound, Earth drifts into interstellar space. The Sun shrinks to just another bright star in the sky, eventually indistinguishable from the others except by position. Surface temperatures drop rapidly as solar heating cuts off. Oceans freeze within years. The atmosphere begins condensing as temperatures fall below the freezing points of various gases. Carbon dioxide snow falls first, then nitrogen, then oxygen. Eventually you're left with a ball of ice coated in frozen air, drifting through the void at several dozen kilometers per second relative to the galactic frame. Deep underground, residual heat from radioactive decay in Earth's core continues for billions of years. Hypothetically, life could persist in deep crustal environments or around hydrothermal vents on the ocean floor, sealed beneath kilometers of ice. These ecosystems already exist in darkness, independent of photosynthesis, powered by chemical energy from the planet's interior. They might not even notice the Sun's absence, at least not immediately. Surface life ends completely. Everything dependent on solar energy, which means everything humans need to survive, ceases functioning within months. No agriculture. No renewable energy. No ecosystem services. Survival would require moving underground with nuclear or geothermal power, growing food under artificial light, and maintaining sealed habitats indefinitely. The technical challenges are immense but theoretically solvable. What's not solvable is doing this for billions of people with no preparation time. Even if a fraction of humanity survived in deep bunkers or sealed cities, you've essentially ended human civilization as we understand it. The survivors would live in permanent artificial environments, cut off from any natural world, maintaining themselves through technology that must never fail because there's no outside to escape to. This is assuming the ejection is gentle enough to leave Earth intact as a physical body. A closer approach could generate tidal forces strong enough to cause massive earthquakes, trigger volcanic eruptions, or in extreme cases, literally crack the planet's crust. The threshold for tidal disruption depends on how close the black hole passes and how fast. A stellar mass black hole would need to come within a few 100,000 kilometers to tear Earth apart through tidal forces alone. That's close, closer than the Moon's orbit. It's unlikely but not impossible. What's more likely, if a rogue black hole passes through the inner solar system at all, is significant orbital disruption without physical destruction. Earth survives as a planet but ends up somewhere it wasn't before, in an orbit that no longer supports the climate patterns civilization developed around. Maybe the new orbit is more elliptical, creating extreme seasonal variations. Maybe it's slightly closer to the sun, triggering runaway greenhouse effects. Maybe it's farther out, pushing the planet toward permanent glaciation. Each scenario creates different challenges, some potentially manageable with advanced technology, others not. The fundamental problem remains unchanged. We can't predict these events with useful lead time. We can't prevent them. We can barely detect the objects responsible. And the consequences range from inconvenient to civilization ending depending on variables we can't control. So we exist in a galaxy where these objects drift through the dark, occasionally reshaping solar systems they pass near, and we have no systematic way of knowing where they are or where they're going. The best we can do is understand the physics, recognize the risk exists, and accept that some threats operate on scales beyond human ability to address. That acceptance doesn't mean ignoring the problem. It means acknowledging what we can and can't control, and focusing effort on the things that actually matter within our capability to influence. This brings us to something slightly more optimistic but equally strange. What happens if we reverse the scenario? Instead of losing the sun, what if Earth captured a second one? Binary star systems are common in the galaxy. Roughly half of all stellar systems contain two or more stars orbiting each other. If our solar system encountered a wandering star under precisely the right conditions, gravitational interactions could theoretically bind it into a stable configuration. The newcomer would need exactly the right mass, velocity, and trajectory. Too fast, and it simply passes through. Too slow or too close, and orbital chaos follows. Let's assume the best case. A star roughly half the Sun's mass approaches from a perpendicular angle to the solar system's plane, moving at just the right speed to be captured into a wide elliptical orbit. The two stars settle into a configuration where they orbit their common center of mass every few thousand years, staying far enough apart that planetary orbits remain mostly stable. Even in this ideal scenario, everything changes. First, there's no longer a single point in the sky that defines day and night, seasons, or climate stability. Depending on orbital positions, Earth might receive varying amounts of total radiation throughout the year. When both stars align on the same side, the planet gets hotter. When they oppose each other, one might be visible during what used to be night, eliminating true darkness for months at a time. Ecosystems evolved under predictable light cycles would face immediate stress. Plants time their growth, flowering, and dormancy to seasonal patterns that have remained consistent for millions of years. Disrupting that rhythm doesn't just inconvenience agriculture. It destabilizes the foundation of terrestrial food webs. Animals navigate, hunt, and reproduce based on day length and seasonal cues. Migratory birds use the sun's position for orientation. Nocturnal species depend on darkness. Coral reefs synchronize spawning to lunar cycles and water temperature patterns tied to solar radiation. All of these systems assume one sun following a predictable path. The climate effects cascade through every layer of atmosphere and ocean. Earth's climate system relies on differential heating between equator and poles to drive atmospheric circulation and ocean currents. Those patterns exist because solar radiation arrives at different angles across latitudes and varies predictably through the year. Adding a second star, even one much dimmer than the sun, introduces new heating patterns that don't align with the geography. Jet streams might shift latitude or weaken entirely. Ocean currents that distribute heat globally could alter course or speed. The intertropical convergence zone, which drives tropical weather patterns, might oscillate unpredictably or split into multiple bands. Then there's orbital mechanics. Even if Earth's orbit remains stable initially, long-term gravitational perturbations from the second star would accumulate. Over thousands of years, Earth's orbital eccentricity might increase, creating more extreme seasonal variations. The axial tilt that currently gives us moderate seasons could begin precessing faster or shifting to new angles. Other planets face worse outcomes. Mars, already in a precarious position with thin atmosphere and marginal temperatures, could be pushed into an orbit that makes it even less habitable. Jupiter and Saturn, the solar system's gravitational anchors, would experience altered orbits that ripple through the entire planetary arrangement. The asteroid belt, currently stable in gaps maintained by Jupiter's gravity, could destabilize. Resonances that previously kept asteroids in safe orbits might break down, sending debris inward toward the inner planets. Impact rates could increase significantly over geological timescales. None of this happens overnight. A captured star doesn't immediately scramble planetary orbits. The changes unfold over decades, centuries, millennia. But they're directional. The solar system wouldn't settle into a new stable state identical to the old one. It would transition toward a different equilibrium, one that might not include Earth in the habitable zone. From a human perspective, even the short-term effects present serious challenges. Agriculture depends on predictable growing seasons. Water resources rely on consistent precipitation patterns driven by stable atmospheric circulation. Infrastructure assumes certain temperature ranges and weather extremes. All of that gets recalibrated when the fundamental energy input to the climate system becomes variable. And we're still assuming the best case where the second star approaches gently and settles into a distant orbit. More likely scenarios involve closer approaches that don't result in capture but still perturb planetary orbit significantly during the encounter. A star passing through the outer solar system would gravitationally scatter comets from the Oort cloud, sending them falling inward. Some would miss Earth. Some wouldn't. The impact risk would spike for thousands of years after the encounter as these disturbed objects crossed the inner system. Planetary orbits themselves could shift. Not dramatically, not instantly, but enough to matter. Earth might end up in a slightly wider orbit, reducing solar radiation and triggering gradual cooling. Or a slightly tighter orbit, increasing temperatures and accelerating ice melt. Either direction creates a planet humans didn't evolve on and haven't built civilization around. The probability of capturing a second star remains extremely low. Space is vast, stellar encounters are rare, and the specific conditions needed for stable capture are narrow. But stellar flybys, close enough to disrupt things without capture, occur more frequently on geological timescales. The Sun will experience multiple close encounters with other stars over its remaining lifespan. Most will pass without incident. Some won't. And this assumes we're only dealing with normal stars. What if the intruder is a white dwarf, a stellar remnant much smaller but incredibly dense? Or a neutron star, packing more mass than the Sun into a sphere 20 kilometers across? The gravitational effects scale with mass, not volume. A neutron star passing through the outer solar system would wreak havoc despite being physically tiny. These objects are harder to detect at distance because they emit little light. A white dwarf shines dimly. A neutron star barely radiates in visible wavelengths. By the time we noticed one approaching, it might be too late to do anything beyond calculating the consequences. The galaxy contains billions of stellar remnants drifting through interstellar space. Most are isolated, moving on predictable paths that won't intersect our neighborhood. But on timescales of millions or billions of years, encounters become statistically inevitable. The solar system will interact with other massive objects. The question isn't if, but when and how severely. We can model these scenarios mathematically. We can run simulations showing what happens to planetary orbits under various perturbations. We can calculate impact probabilities and climate shifts. What we can't do is prevent them or predict them far enough in advance to matter. That leaves us in an odd position. We understand the risks. We know the mechanisms. We can describe in detail what would happen under different conditions. But we can't defend against threats operating at stellar scales with energies and masses that make human technology irrelevant. This isn't fatalism. It's recognition that some problems exist outside our ability to solve. You don't build contingency plans for events that would end technological civilization because there's no point. Either the event doesn't happen and the planning was unnecessary, or it does happen and the plans don't help. What matters instead is understanding our place in a dynamic galaxy where stability is temporary and change is guaranteed. The solar system occupies its current configuration because nothing has disturbed it recently. That's not a permanent state. It's a snapshot of one moment in an ongoing process that operates on timescales longer than human history but shorter than planetary lifespans. The Sun formed 4.6 billion years ago from a collapsing molecular cloud. It will continue fusing hydrogen for another 5 billion years before exhausting its core fuel and expanding into a red giant. Within that time span, the solar system will experience multiple gravitational encounters with passing stars, clouds of interstellar matter, and possibly rogue planets or stellar remnants. Most encounters will be minor. A slight tug on the Oort cloud. A tiny shift in planetary orbits too small to measure. Occasionally, something more significant occurs. A star passes within a light year, scattering comets inward. A molecular cloud drifts through the system, altering solar radiation through increased dust. A massive object transits nearby, pulling planets into new configurations. These are not hypothetical scenarios invented to frighten people. They're documented processes observed in other stellar systems and predicted by our understanding of galactic dynamics. We exist in a galaxy that doesn't care about preserving any particular arrangement of matter. Stars form, evolve, and die. Planets coalesce and get destroyed. Systems reorganize under gravitational influences that operate without regard for what lives on them. Acknowledging this doesn't mean giving up. It means recognizing which problems require solutions and which require acceptance. We can't prevent stellar encounters. We can understand them, model them, and perhaps detect them earlier with better observation networks. That knowledge serves a purpose even if it doesn't change outcomes. Human time operates on scales measured in decades or centuries. Stellar mechanics operate on scales measured in millions of years. That disconnect creates a perceptual problem. We evolved to recognize immediate threats. Predators, storms, drought. Our nervous systems weren't built to process dangers that unfold over timeframes longer than civilizations exist. A star passing within 2 light-years over the next million years doesn't trigger the same response as something happening next week. But the physics doesn't care about our perception. Gravity operates continuously. Orbits shift gradually. What seems stable on human timescales reveals itself as dynamic when viewed across proper intervals. Jupiter's orbit changes. Saturn's rings evolve. The Moon recedes from Earth at about 4 centimeters per year. These aren't static objects frozen in place. They're participants in an ongoing gravitational negotiation that never stops. Now scale that up to galactic levels. The Milky Way contains 200 billion stars, most with their own planetary systems. Add brown dwarfs, rogue planets, stellar remnants, molecular clouds, and regions of concentrated dark matter. Everything moves. Everything pulls on everything else within its gravitational influence. The result is a galaxy in constant motion, where encounters between systems happen regularly across cosmic timescales. Our Sun orbits the galactic center once every 230 million years. During each orbit, it passes through different regions of the galaxy. Spiral arms, interarm regions, areas of higher and lower stellar density. Each environment presents different risks. Spiral arms contain more massive stars, which means more supernovae, more stellar winds, more radiation. They also contain giant molecular clouds that can trigger ice ages by blocking sunlight. Interarm regions are quieter but not empty. Rogue objects drift through these spaces. Stellar remnants. Planets ejected from their original systems. Objects too dim to detect until they're relatively close. The galaxy doesn't maintain clear boundaries between safe and dangerous zones. It's all dangerous given enough time. What varies is the probability and severity of encounters. Right now, the solar system occupies a relatively calm neighborhood. The nearest star, Proxima Centauri, sits 4.2 light-years away. That's far enough that its gravitational influence on our planets is negligible. The next closest stars are also comfortably distant. This configuration is temporary. Stars move at different velocities relative to each other. In about 30,000 years, a red dwarf called Ross 248 will pass within 3.2 light-years of the Sun, becoming our closest neighbor for a time. Then it will continue on its path and something else will take its place. These close passes happen regularly on galactic timescales. Most are harmless. A star passing within 5 light-years exerts minimal gravitational influence on planets orbiting another star. The effects are measurable in simulations but negligible in practice. Closer encounters are rarer but more consequential. A star passing within 1 light-year would perturb the Oort cloud significantly, potentially sending comets into the inner solar system for millions of years afterward. A star passing within half a light-year could affect planetary orbits directly, though the changes would be subtle unless the encounter was extremely close. The problem is detection. We can track nearby stars with current technology, but only the relatively bright ones. Dim red dwarfs, brown dwarfs, and rogue planets are much harder to spot until they're already close. Infrared surveys have improved our ability to find these objects, but gaps remain. Something could be approaching that we won't notice until it's within a few light years. By then, we'd have thousands of years to study it but no ability to change its trajectory. Altering the path of a stellar mass object would require energy expenditures far beyond anything human technology can produce. You can't nudge a star the way you might deflect an asteroid. The mass difference is too large. The energies involved too extreme. Even if we had millions of years to prepare, the engineering challenges would be insurmountable. Which brings us back to the same conclusion. Observation and understanding, yes. Prevention, no. We can map nearby space. We can identify potential threats decades or centuries before they arrive. We can calculate exactly what will happen during an encounter. None of that changes the outcome. It just means we'll know what's coming. There's value in that knowledge even without the ability to act. Understanding allows for preparation of a different kind. Not physical defenses, but intellectual frameworks. If we know a stellar encounter will destabilize the Oort cloud in 50,000 years, that information becomes part of how future generations think about long-term survival. Maybe it influences where deep space probes are sent. Maybe it affects how astronomical databases are maintained. Maybe it does nothing practical but satisfies the human need to understand our environment. That need is real even when it doesn't lead to solutions. We study supernovae knowing we can't prevent them. We model black hole behavior knowing we'll never interact with one. We map the cosmic microwave background knowing it tells us about events we can't influence. Knowledge has value independent of utility. Stellar encounters fall into that category. They're important to understand because they're part of the environment we exist in. They shape planetary evolution. They influence the long-term habitability of solar systems. They determine which configurations of planets remain stable over billions of years. Earth exists in its current form partly because the solar system hasn't experienced a major gravitational disruption since planets finished forming. That stability allowed life to develop, evolve, and eventually produce technological civilization. It's not guaranteed to continue. At some point, something will pass close enough to change things. When that happens, the consequences depend entirely on what passes and how close it gets. A distant encounter might scatter some comets. A close encounter could reshape orbits. An extremely close encounter could eject planets from the solar system entirely. These aren't equally likely. The probability decreases dramatically as encounters get closer. But over billions of years, even low-probability events become near certainties. The Sun will experience multiple close encounters before it exhausts its hydrogen fuel. Some will be minor. At least one might be significant. The galaxy guarantees change over sufficient timescales. What it doesn't guarantee is survivability. Systems that get disrupted don't recover their original configurations. Planets that get ejected don't return. Once gravitational chaos reaches a certain threshold, the system reorganizes into a new stable state that might look nothing like the original. This has already happened to countless other systems. We observe planetary systems with highly eccentric orbits, planets too close to their stars, gas giants in locations where they couldn't have formed. These are signatures of past disruptions. Encounters with other stars. Planetary migrations triggered by gravitational interactions. Systems that reorganized after their original configurations became unstable. Our solar system shows signs of its own past reorganization. The NICE model suggests that Jupiter, Saturn, Uranus, and Neptune didn't form in their current positions. They migrated inward and outward after formation, possibly triggered by encounters with planetesimals or resonances between their orbits. This migration would have scattered smaller bodies throughout the solar system, explaining features like the late heavy bombardment 4 billion years ago. If that model is correct, the solar system has already experienced major gravitational reshuffling. What we see now is the result of that reorganization, not the original configuration. Which means change isn't hypothetical. It's already happened. The question is whether it will happen again during the remaining lifespan of the Sun. Probability suggests yes. Timing remains unknown. The galaxy contains too many variables to predict specific encounters far in advance. We can calculate general probabilities. We can identify nearby objects and track their movements. We can model what would happen under different scenarios. What we can't do is point to a specific date and say this is when the next major disruption occurs. That uncertainty is permanent. It's built into the nature of galactic dynamics. Too many objects moving in too many directions with too many possible interactions. Even perfect knowledge of current positions and velocities wouldn't allow precise predictions millions of years ahead because gravitational interactions are chaotic. Small changes in initial conditions produce large differences in outcomes over time. Free body problems are analytically unsolvable. Stellar neighborhoods involve millions of bodies. The math doesn't allow exact long-term predictions even in principle. We're left with statistical models and probability ranges. Useful for understanding general patterns but useless for predicting specific events. That's not a limitation of current technology. It's a fundamental feature of how gravity works in systems with multiple interacting masses. Chaos isn't something better computers can solve. It's an inherent property of the equations governing motion. Which means we'll never have certainty about future stellar encounters. We'll have better observations, more detailed models, improved probability estimates. We won't have schedules. The galaxy doesn't operate on schedules. It operates on physics, which produces patterns but not predictability. Stars move through space according to gravitational laws that allow probability calculations but resist precise forecasting over timescales measured in millions of years. The Sun's journey through the galaxy has already lasted 4.5 billion years. During that time, it's completed roughly 20 orbits around the galactic center. Each orbit takes between 200 and 250 million years, depending on the Sun's exact distance from the center and the distribution of mass in the galaxy. 20+ complete circuits means 20+ passages through the spiral arms, dozens or hundreds of close encounters with molecular clouds, and countless interactions with the changing gravitational landscape of the Milky Way. The solar system survived all of it. The planets remained in stable orbits. Earth maintained conditions suitable for life across geological timescales. Whatever encounters occurred during those billions of years, none were catastrophic enough to eject planets or sterilize Earth. That's not luck. It's statistics. Most stellar encounters are distant enough to cause minimal disruption. The dangerous ones are rare. Over billions of years, the rare events that do occur tend to fall within a range the system can absorb without complete destruction. But survival of past encounters doesn't guarantee immunity from future ones. Each passage through a spiral arm resets the probability. Each orbit through the galaxy exposes the Sun to new potential interactions. The gravitational environment changes constantly as stars move through their own orbits, Clusters form and dissolve, and the galaxy's structure evolves. What protected the solar system during previous orbits might not be sufficient during future ones. The distribution of stars changes. Regions that were once relatively empty can become more crowded as stellar populations shift. The Sun's current path through the galaxy might take it through denser neighborhoods than it experienced in the past. Or it might lead it into quieter regions. There's no way to know without detailed mapping of stellar trajectories across millions of years, which remains beyond current observational capabilities. One factor that does influence encounter probability is the Sun's vertical oscillation through the galactic plane. The Sun doesn't orbit the galactic center in a flat circle. Its path carries it above and below the galactic plane in a wave-like motion, crossing through the plane approximately every 30 to 40 million years. When the Sun passes through the galactic plane, it encounters higher stellar densities than when it's above or below. The plane contains most of the galaxy's visible matter, including stars, gas, and dust. Crossing through it increases the probability of close encounters simply because there are more objects present. Some researchers have suggested this oscillation might correlate with mass extinction events on Earth, proposing that encounters with molecular clouds or increased comet impacts occur more frequently during plane crossings. The evidence remains debated. Extinction patterns don't show clear periodicity matching the oscillation cycle. Even if a correlation exists, it would demonstrate that galactic position influences Earth's history, not that future crossings will necessarily produce similar effects. Each crossing involves different molecular clouds, different stellar configurations, different gravitational contexts. Past patterns don't predict future outcomes with certainty. Beyond stellar encounters, the Sun faces long-term changes in the galaxy's overall structure. The Milky Way is currently on a collision course with the Andromeda Galaxy. The two galaxies will begin interacting in approximately 4 billion years, with a full merger occurring over the following few billion years. During galactic mergers, stellar orbits get disrupted on massive scales. Stars that once followed predictable paths around their galactic centers get scattered into new configurations as the two galaxies' gravitational fields interfere with each other. The Sun will likely survive the merger physically. Galactic mergers don't involve stars actually colliding because the distances between stars are enormous compared to their sizes. Even when two galaxies interpenetrate completely, the probability of any given star hitting another star remains vanishingly small. What changes is orbital structure. The Sun's current orbit around the Milky Way's center will become meaningless as that center merges with Andromeda's center. The combined galaxy, sometimes called Melpomene, will have a different shape, different rotation, different gravitational architecture. The Sun will end up in a new orbit around the merged galaxy's center, potentially far from its current position. That repositioning might place the Sun in denser regions with higher encounter probabilities, or in sparser regions with lower probabilities. The outcome depends on details of the merger that can't be predicted precisely. Simulations show general patterns but can't specify where individual stars end up. Too many variables. Too many gravitational interactions occurring simultaneously. The merger timeline presents an interesting coincidence. 4 billion years from now, the Sun will be nearing the end of its main sequence lifetime. It will have exhausted most of its hydrogen fuel and begun transitioning toward the red giant phase. The Andromeda merger will commence around the same time the Sun starts expanding. Earth's fate might be sealed by solar evolution before galactic dynamics become the dominant concern. As the Sun expands into a red giant, it will engulf Mercury and Venus. Whether it reaches Earth's orbit remains uncertain and depends on exact mass loss rates during the expansion. Even if Earth's orbit isn't physically consumed, the increased solar radiation will vaporize the oceans and strip away the atmosphere long before the Sun's surface reaches Earth's position. By the time the galactic merger creates new gravitational dynamics, Earth will likely already be uninhabitable. That doesn't mean stellar encounters before then are irrelevant. Between now and the Sun's red giant phase, roughly 5 billion years remain. During that time, the Sun will complete another 20 orbits around the galaxy, 20 more passages through spiral arms, hundreds more opportunities for close encounters. The probability that at least one significant encounter occurs during those 5 billion years is not negligible. What constitutes a significant encounter? Definitions vary depending on what effects you're measuring. For disrupting the Oort cloud and potentially triggering comet showers, encounters within 1 or 2 light years matter. For perturbing planetary orbits directly, encounters need to be much closer, probably within a few thousand astronomical units. For ejecting planets entirely, encounters likely need to approach within hundreds of astronomical units. Each category has different probabilities and different consequences. Oort cloud disruptions are relatively common on million-year timescales. Direct planetary perturbations are rare but not impossible. Planetary ejections are extremely rare but have definitely occurred in other systems. The solar system probably won't experience a catastrophic close encounter during the next billion years. Probably. That's the strongest statement physics allows. The galaxy doesn't provide guarantees. Observation programs continue tracking nearby stars, measuring their positions, velocities, and trajectories. As data accumulates, predictions improve for specific stars over limited time periods. Gliese 710 will pass within 10,000 astronomical units in about 1.3 million years. HIP 85605 might come within 16,000 astronomical units in 240,000 years. These predictions carry uncertainty margins that increase with distance into the future. A star projected to pass at 10,000 astronomical units might actually pass at 8,000 or 12,000 depending on factors not fully constrained by current measurements. The difference matters when calculating gravitational effects on the Oort cloud. Small changes in closest approach distance produce large changes in the number of comets perturbed. Even with improving data, predictions beyond a few million years remain probabilistic rather than deterministic. The galaxy contains too many objects with too many possible interactions. The Sun's journey through the galaxy continues. Right now, it's moving toward the constellation Hercules at roughly 250 kilometers per second relative to the local standard of rest. That motion carries it through neighborhoods where stellar densities fluctuate, molecular clouds drift, and gravitational influences shift. Over the next 100 million years, the Sun will move several thousand light-years from its current position. New stars will become neighbors. Current neighbors will drift away. The gravitational landscape surrounding the solar system will transform completely multiple times before the Sun exhausts its hydrogen fuel. Each transformation brings new encounter possibilities. Each possibility carries a probability that can be calculated but not eliminated. The galaxy guarantees that change happens. It doesn't specify when or how severely. Our solar system exists in a dynamic environment where stability is temporary and disruption is eventual. Not immediate. Not predictable in detail. But inevitable given sufficient time. That's the nature of gravitational systems with many interacting bodies moving through space. Chaos emerges from deterministic laws. Probability replaces certainty. Patterns appear but predictions fail beyond certain timescales. The Sun will continue orbiting the galactic center, crossing through spiral arms, oscillating above and below the galactic plane, encountering molecular clouds and passing stars. Most encounters will be distant and inconsequential. Some will perturb the Oort cloud and send comets toward the inner solar system. A few might disturb planetary orbits enough to measure. One might eventually be close enough to fundamentally alter the solar system's architecture. We can't prevent it. We can't predict exactly when it will happen. We can only observe, calculate probabilities, and understand that the galaxy operates on timescales where rare events become commonplace. The question isn't whether the solar system will experience future disruption. The question is whether it will happen during a time frame that matters to us. For the next few million years, probably not. Beyond that, certainty dissolves into probability, and probability suggests that eventually, something significant will occur. The galaxy has 400 billion stars moving through space. The Sun is one of them, following its orbit through a constantly shifting gravitational landscape. Every orbit brings new encounters. Every encounter carries probabilities. Given enough orbits, those probabilities converge toward inevitability. That's not pessimism. That's mathematics applied to gravity operating across billions of years in a galaxy that never stops moving. The galaxy we inhabit operates without regard for our presence. Rogue black holes drift through the darkness between stars, following paths set by violent births millions or billions of years ago. Hundreds of millions of them, perhaps more, scattered across the Milky Way like invisible landmines in a cosmic ocean. We've detected a handful. The rest remain hidden, detectable only through rare gravitational lensing events that require perfect alignment and extraordinary luck. Detection methods improve. Surveys expand. Observation networks grow more sophisticated. None of it changes the fundamental problem. We're looking for objects that emit no light, produce no radiation, and reveal themselves only by bending the light of background stars during brief windows of alignment. Even when we catch these events, we're seeing something that happened years or centuries ago. The black hole itself has already moved on, continuing along a trajectory we can't predict with useful precision. The mathematics of galactic dynamics allows probability calculations but resists exact forecasting. Too many objects moving in too many directions with too many possible interactions. Free body problems are analytically unsolvable. Stellar neighborhoods involve millions of bodies. Chaos emerges from deterministic laws. Small changes in initial conditions produce wildly different outcomes over time. We can model general patterns but can't predict specific encounters millions of years ahead. That uncertainty is permanent. It's built into how gravity works in systems with multiple interacting masses. Better observations won't fix it. More powerful computers won't solve it. The galaxy doesn't operate on schedules we can map. It operates on physics that produces patterns but not predictability. What matters is understanding our position within this dynamic system. The solar system exists in its current configuration because nothing has disrupted it recently. That's not a permanent state. It's a temporary snapshot of one moment in an ongoing process that operates on timescales longer than human history but shorter than planetary lifespans. Change is guaranteed over sufficient time. What isn't guaranteed is survivability. Systems that get disrupted don't recover their original configurations. Planets that get ejected don't return. Once gravitational chaos reaches a certain threshold, everything reorganizes into a new stable state that might look nothing like what came before. This has happened to countless other systems. We observe the signatures in eccentric orbits, misplaced planets, and configurations that couldn't have formed naturally. Evidence of past encounters that reshaped entire solar systems. Our own system shows signs of reorganization in its past. the planets might not occupy their original positions. The late heavy bombardment 4 billion years ago suggests major gravitational reshuffling occurred. What we see now could be the result of that ancient chaos, not the initial arrangement. Which means change isn't hypothetical. It's already happened here. The question is whether it will happen again on timescales that matter to anything currently alive. Probability suggests yes, eventually. Timing remains unknown. The Sun will experience multiple close encounters with other stars, molecular clouds, and possibly rogue black holes before it exhausts its hydrogen fuel. Most will be minor. Some might be significant. One could potentially be catastrophic. The galaxy guarantees encounters over billions of years. It doesn't specify which ones will matter or when they'll occur. We can't defend against threats operating at stellar scales. We can't deflect a black hole or alter the trajectory of a passing star. The mass differences are too large. The energies involved too extreme. Even with millions of years to prepare, the engineering challenges would remain insurmountable. You can't nudge a stellar mass object the way you might deflect an asteroid. What we can do is observe, understand, and acknowledge which problems exist outside our ability to solve. Knowledge has value independent of utility. We study phenomena we can't influence because understanding our environment matters even when we can't control it. Rogue black holes are part of that environment. They shape galactic evolution. They influence which planetary configurations remain stable over billions of years. They determine, in ways we're only beginning to understand, which systems survive long enough for complex life to develop. Earth exists in its current form partly because the solar system hasn't experienced a major gravitational disruption since planets finished forming. That stability allowed life to develop, evolve, and eventually produce technological civilization. It's not guaranteed to continue. At some point, something will pass close enough to change things. When that happens, the consequences depend entirely on what passes and how close it gets. The galaxy contains 400 billion stars moving through space, countless stellar remnants, molecular clouds, rogue planets, and objects we haven't cataloged yet. Everything pulls on everything else within its gravitational influence. The result is a galaxy in constant motion where encounters between systems happen regularly across cosmic timescales. Most are harmless. Some aren't. The difference comes down to distance, mass, velocity, and timing. Variables we can measure in nearby objects but can't predict far in advance for the galaxy as a whole. So we exist in a dynamic galaxy where invisible predators drift through the darkness, occasionally reshaping solar systems they pass near. We have no systematic way of knowing where most of them are or where they're going. The best we can do is understand the physics, recognize the risk exists, and accept that some threats operate on scales beyond human ability to address. That acceptance isn't fatalism. It's recognition of what we can and can't control, and focusing effort on things that actually matter within our capability to influence. The galaxy operates according to physical laws that don't care about preserving any particular arrangement of matter. Stars form, evolve, and die. Planets coalesce and get destroyed. Systems reorganize under gravitational influences that operate without regard for what lives on them. We're participants in that process, not exempt from it. Understanding that doesn't change outcomes. It just means we'll know what we're looking at when the galaxy reminds us that stability is always temporary. Beneath a frozen shell thicker than Mount Everest is tall, an ocean larger than all of Earth's seas combined sits in complete darkness. You're probably picturing some distant exoplanet, maybe something thousands of light years away. Wrong. This ocean exists right here in our solar system, orbiting Jupiter every 3.5 days. Europa holds more liquid water than our entire planet, and NASA just launched a $5 billion mission to find out if anything is swimming in it. The numbers don't make sense at first. Europa is slightly smaller than our moon, yet somehow contains double the water volume of Earth. Where did it all come from? More importantly, how does it stay liquid when surface temperatures drop to -220 degrees Celsius? The answer involves one of the most violent gravitational relationships in the solar system, and it's the same force that might be creating the conditions for life to exist right now, roughly 390 million miles from the Sun. Jupiter's gravity doesn't just pull on Europa. It squeezes the Moon like a stress ball, over and over, every orbit. The result is tidal heating, a process so intense that it generates enough warmth to maintain a liquid ocean beneath an ice shell that would otherwise be frozen solid. But here's what makes this truly remarkable. The same gravitational torture that keeps the water liquid also cracks the ice above it, creating a dynamic surface that might be exchanging material between the frozen exterior and the hidden ocean below. Scientists discovered something strange when the Galileo spacecraft flew past Europa in the late 1990s. Jupiter's powerful magnetic field, which normally behaves in predictable ways, was getting disrupted near the Moon. Not scattered randomly, but in a pattern that suggested something conductive existed beneath the surface. The only substance that made sense was salt water, lots of it, creating its own induced magnetic field through interaction with Jupiter's magnetosphere. This wasn't speculation based on models. It was a direct measurement of something happening right then. The surface told its own story. Europa's ice shows almost no impact craters, which seems impossible for an object that's been orbiting Jupiter for billions of years. The solar system is full of debris, rocks, and ice chunks that should have been pounding this moon relentlessly. Yet Europa's surface is remarkably smooth, the smoothest solid object we've ever found. The only explanation that fits is resurfacing, ice that gets recycled and renewed, erasing old scars. Something beneath that crust is mobile enough to erase geological history. Look closer at Europa's surface and you'll see something that resembles pack ice on Earth's Arctic Ocean, except the pieces are the size of cities. These ice rafts have rotated, shifted, and refrozen in new positions. Some regions show what scientists call chaos terrain, areas where the surface has completely broken apart and reassembled into jumbled landscapes. The ice isn't just sitting there. It's moving, breaking, reforming. Underneath all that activity, an ocean is pushing upward. Then there are the streaks. Long linear features, reddish-brown in color, crisscross Europa's pale surface like veins. For years, scientists debated what these could be. Radiation damage, mineral deposits. The answer turned out to be salt, specifically magnesium sulfate, left behind when briny water from below erupted onto the surface and evaporated. The ocean isn't just sitting quietly in the dark. It's interacting with the ice shell above it, possibly in ways that could bring nutrients down and waste products up, exactly the kind of exchange that life would need. Water alone doesn't make a habitable world. You need the right chemistry, the right energy sources, the right conditions maintained over geological timescales. Europa's ocean started out wrong for life, too acidic, loaded with sulfates and carbon dioxide. But something changed. Over 4.5 billion years, chemical reactions transformed that harsh environment into something that resembles Earth's oceans. The water became chloride-rich, with dissolved magnesium, sodium, potassium, and chlorine floating in concentrations similar to our seas. The ocean evolved. In 2024, the James Webb Space Telescope detected carbon dioxide on Europa's surface, specifically in a region called Terra Regio. This wasn't just any carbon dioxide. Analysis showed it came from below, from the subsurface ocean, deposited recently in geological terms. Carbon is fundamental to life as we know it. Finding it concentrated in an area where the ice has clearly been disrupted, where material from the ocean appears to have reached the surface, isn't proof of life. But it's exactly what you'd want to see if you were looking for habitable conditions. Then came the ammonia discovery. Scientists re-examining old Galileo data found faint signals of ammonia-bearing compounds near fractures in the ice. Ammonia matters for two reasons. First, it's a nitrogen-bearing molecule, and nitrogen is essential for amino acids, DNA, proteins, all the molecular machinery that biology runs on. Second, ammonia acts as antifreeze, lowering water's freezing point. In Europa's environment, where temperatures hover around freezing even in the ocean, ammonia could create pockets of liquid water that would otherwise freeze solid. Life, if it exists, might be clustering around these ammonia-rich zones. The energy question looms over everything. On Earth, most life ultimately depends on sunlight, either directly through photosynthesis or indirectly through food chains built on photosynthetic organisms. Europa receives 25 times less sunlight than Earth, and none of that reaches the ocean anyway. So where would the energy come from? Tidal heating provides warmth, but life needs chemical energy, electrons moving from one molecule to another, reactions that release usable power. One possibility involves the same process that supports life at hydrothermal vents on Earth's ocean floor. Hot water, heated by geological activity, erupts from cracks in the seafloor, carrying dissolved minerals and chemicals. When this hot, chemically rich water meets cold ocean water, reactions occur spontaneously. Microbes harvest the energy from these reactions, building entire ecosystems in complete darkness. Europa might have similar vents if its seafloor remains geologically active. That's where the debate gets contentious. Recent calculations from Washington University in St. Louis suggest Europa's seafloor might be cold and geologically quiet. The tidal heating that keeps the ocean liquid might not penetrate deep enough to warm the rocky core below. Without volcanic activity, without fracturing and faulting that exposes fresh rock to water, the chemical reactions that microbes could feed on become much harder to sustain. Europa's core likely cooled billions of years ago, and unlike Earth's interior, which still churns with heat from radioactive decay, Europa might not have enough internal energy to power active geology at the seafloor. But other researchers aren't convinced the story ends there. Even without volcanic hydrothermal vents, chemical energy could come from different sources. Radiation from Jupiter constantly bombards Europa's surface, breaking apart water molecules and creating hydrogen peroxide, oxygen, and other oxidants. These chemicals could work their way down through the ice, eventually reaching the ocean. Meanwhile, the seafloor, even if cold, still contains minerals that can react with water through a process called serpentinization. Mix oxidants from above with reduced minerals from below, and you've got potential energy for life. There's another pathway that nobody predicted until recently. The ice shell itself might be producing nutrients. Jupiter's radiation doesn't just create oxidants, it also generates complex organic molecules from simpler compounds on the surface. Normally, these would just accumulate in the ice, chemically isolated from the ocean. But a process called crustal delamination could change that. As denser, salt-rich ice forms near the surface, it could sink through the lighter ice below, carrying those surface nutrients down into the ocean like a conveyor belt. The ice shell wouldn't just be a barrier. It would be a chemical factory and delivery system. The plume question adds another layer of mystery. In 2012, the Hubble Space Telescope captured what appeared to be water vapor erupting from Europa's south polar region, shooting 200 kilometers into space, more than 20 times the height of Mount Everest. If real, these plumes would be a gift to future missions. Instead of drilling through miles of ice, a spacecraft could simply fly through a plume and collect samples of ocean water directly. But proving the plumes exist has been surprisingly difficult. Hubble saw the plume signature once, maybe twice. The Galileo spacecraft might have flown through one in 1997, though that interpretation came decades after the fact from reanalysis of magnetic field data. The James Webb Space Telescope looked for plumes in 2023 and found nothing. Other observations using radio telescopes searched for the molecules that should be present in plumes and came up empty. Either the plumes are rare, episodic events that only happen under specific conditions, or they're much weaker than initially thought, or some of those early detections were misinterpretations of noisy data. The uncertainty doesn't diminish Europa's potential. Plumes or no plumes, the ocean exists. The chemistry appears favorable. The energy sources, while debated, seem sufficient for at least microbial life. What Europa needs now is not more speculation from a distance, but direct investigation up close. That's exactly what NASA launched on October 14, 2024. Europa Clipper is the largest spacecraft NASA has ever built for a planetary mission. With its solar arrays deployed, it stretches over 100 feet, roughly the length of a basketball court. Those enormous solar panels are necessary because Jupiter sits 5 times farther from the Sun than Earth, meaning sunlight there is 25 times weaker. Clipper will spend 6 years traveling 1.8 billion miles, using gravity assists from Mars and Earth to slingshot itself toward Jupiter, arriving in April 2030. The mission design is clever out of necessity. Jupiter's radiation environment is brutal, intense enough to fry electronics in a matter of hours if a spacecraft stayed near Europa continuously. Instead, Clipper will orbit Jupiter itself, swooping past Europa for close flybys, then retreating to safer distances. Over 4 years, it will complete 49 of these flybys, each one bringing it within 16 miles of the surface in some cases. During each pass, the 9 instruments on board will have just minutes to gather data before radiation levels become dangerous again. Those instruments represent the cutting edge of planetary science. Radar will peer through the ice, measuring its thickness and looking for water pockets within the shell. Magnetometers will map Europa's induced magnetic field in far greater detail than Galileo could, potentially revealing the ocean's depth and salinity. Spectrometers will analyze the surface composition, identifying organic molecules, salts, and other chemicals that might have come from below. Cameras will image the surface at resolutions high enough to see features the size of a car. One instrument stands out for its potential to make history. The Surface Dust Analyzer will collect ice grains and dust particles as Clipper flies through the space just above Europa's surface. By analyzing the composition and trajectories of these particles, scientists can determine where they came from and what they're made of. If plumes exist, SUDA will fly right through them, collecting samples of ocean water without the spacecraft ever touching the surface. Laboratory tests have shown something remarkable about instruments like SUDA. Scientists fired ice grains containing tiny amounts of bacterial cell material at a prototype mass spectrometer under conditions simulating a Europa flyby. Even when only 1% of a grain consisted of biological material, the instrument detected it. Clipper carries similar technology. If microbial life exists in Europa's ocean, and if that life gets ejected into space through plumes or surface fractures, and if SUDA happens to sample those particles, the instrument could detect alien biology directly. Nobody on the mission is publicly betting on that outcome. The odds of all those conditions aligning seem astronomical. But the fact that it's even possible, That we've built a spacecraft capable of detecting extraterrestrial life if it's there, represents a profound shift in space exploration. For perspective, we've never attempted anything quite like this before. Every previous mission to detect extraterrestrial life required landing, drilling, or direct sampling. Clipper could find it simply by flying through the right patch of space at the right moment. The margin for error is razor thin, but the payoff would rewrite biology textbooks. Understanding what makes this possible requires examining Europa's surface in detail. When Voyager 1 flew past in 1979, it sent back images that baffled scientists. Europa looked nothing like a typical moon. No impact craters pockmarked the surface. No mountains broke the horizon. Instead, the images showed a smooth, cracked sphere crisscrossed by dark reddish-brown streaks and linear fractures stretching hundreds of miles. Those features told a story. The lack of craters meant the surface was young, geologically speaking, probably only 40 to 90 million years old. On cosmic timescales, that's yesterday. Something was constantly resurfacing Europa, erasing ancient impact scars. The cracks suggested movement, tectonic activity driven not by internal heat alone but by the flexing of the ice shell as Jupiter's gravity squeezed and released the Moon every 3-5 days. The reddish-brown material coating those fractures became a mystery that took decades to solve. Early theories proposed sulfur compounds ejected from volcanic Io and deposited on Europa's surface. But spectroscopic analysis told a different story. The material appeared to be salts, magnesium sulfate primarily, mixed with other minerals. These weren't deposits from space. They came from below. When Europa's ice shell cracks under tidal stress, liquid water from the ocean can seep upward through the fractures. As it reaches the surface, the extreme cold and vacuum of space cause it to evaporate instantly, leaving behind dissolved salts and minerals. Those deposits form the reddish streaks we see. The color comes from radiation damage. Jupiter's intense magnetic field accelerates charged particles to enormous speeds, and when those particles slam into the surface, they break chemical bonds and create new compounds that absorb light differently. This process matters because it means Europa's surface isn't isolated from the ocean below. There's exchange happening, material moving between the deep ocean and the exposed surface. James Webb Space Telescope observations confirmed this in 2023 when astronomers detected carbon dioxide concentrated in a region called Terra Regio, an area of chaos terrain where the surface appears jumbled and disrupted. The carbon dioxide didn't come from space. Isotopic analysis showed it originated in the subsurface ocean and reached the surface recently, geologically speaking, probably within the last few hundred years. Terra Regio itself reveals how dynamic Europa's surface can be. Chaos terrain forms when warm ice or liquid water rises from below, melting or disrupting the overlying ice shell. The result looks chaotic because it is: blocks of ice tilted at odd angles, fractured and refrozen in new configurations, surface material replaced by fresher ice from deeper layers. These regions offer windows into Europa's interior composition. Then there's the question of plumes. In 2012, Hubble observations suggested water vapor erupting from Europa's south polar region, shooting 125 miles into space before falling back to the surface. The detection was tentative, based on ultraviolet spectroscopy showing what appeared to be hydrogen and oxygen atoms where none should be. Follow-up observations in 2016 provided additional evidence. Researchers analyzing old Galileo data discovered that when the spacecraft flew past Europa in 1997, it might have passed directly through a plume without anyone realizing it at the time. But plumes remain controversial. Later observations with more sensitive instruments found nothing. The James Webb Space Telescope examined Europa thoroughly and detected no active plumes. Radio telescope arrays saw no molecular emissions. Either the earlier detections were misinterpreted, or plumes on Europa are sporadic, erupting only occasionally under specific conditions. Models suggest that if plumes exist, they're most likely when Europa reaches the farthest point in its orbit from Jupiter. At that moment, tidal forces stretch the Moon maximally, potentially opening cracks wide enough for pressurized water to escape. The plumes wouldn't be steady geysers like those on Saturn's moon Enceladus. They'd be brief, localized eruptions that might occur every few orbits or less frequently still. This uncertainty actually increases Clipper's importance. The spacecraft will fly past Europa 49 times over 4 years, sampling different locations under different orbital conditions. If plumes exist, Clipper has excellent odds of encountering one. If they don't exist, or if they're too weak to detect remotely, Clipper will still gather material from Europa's exosphere, the thin envelope of gas and dust particles surrounding the Moon. Every object in space loses material to its surroundings. Solar radiation and Jupiter's magnetospheric particles constantly bombard Europa's surface, breaking molecular bonds and ejecting atoms and molecules into space. Some of that material escapes entirely. Some falls back. And some lingers in a thin cloud around the Moon. SUDA will sample that cloud, collecting particles that originated on the surface or potentially from the ocean itself if exchange processes are active. Recent discoveries add weight to the idea that Europa's surface and ocean communicate regularly. Analysis of old Galileo spectrometer data revealed ammonia-bearing compounds near surface fractures. Ammonia is significant for 2 reasons. First, it's a nitrogen compound, and nitrogen is essential for life as we know it, playing key roles in amino acids, DNA, and proteins. Second, ammonia lowers water's freezing point. An ocean containing dissolved ammonia could remain liquid at temperatures several degrees below 0 Celsius, potentially staying fluid even in regions where pure water would freeze. The ammonia detection came from reanalyzing data that had sat in archives for decades. Scientists applied modern processing techniques to old near-infrared observations and found faint spectral signatures that earlier analysis had missed. The compounds appeared concentrated near fractures and pits, exactly where you'd expect material from below to reach the surface. This pattern keeps repeating. Every time researchers look more carefully at Europa, they find more evidence of an active world. The surface isn't a static ice shell sitting atop a stagnant ocean. It's a dynamic interface where processes from below continuously reshape what we see from above. Cracks form and heal. Chaos terrain disrupts and refreezes. Salts and minerals migrate upward. Carbon dioxide deposits in specific locations. Ammonia appears near fractures. All of this paints Europa as a world where the ocean isn't sealed away forever beneath impenetrable ice. It's accessible, at least in principle. Material from the ocean reaches the surface through various processes. That's what makes Clipper's mission feasible without landing or drilling. The Moon itself brings samples to the surface. But here's what nobody can answer yet: how much exchange actually occurs? Is it constant and widespread, or rare and localized? Do these processes deliver enough material from the deep ocean to the surface that Clipper can sample it? Or does radiation and weathering destroy organic molecules before they can be detected? These questions matter because they determine what Clipper will find. If exchange is robust and frequent, the spacecraft should detect clear chemical signatures from the ocean, potentially including organic compounds or even biosignatures. If exchange is minimal or if surface conditions destroy delicate molecules quickly, Clipper might see only heavily altered material that doesn't reflect the ocean's true composition. The mission design acknowledges this uncertainty. Clipper's instruments are built to detect a wide range of compounds at very low concentrations. The radar can peer through several miles of ice, potentially detecting liquid water pockets trapped within the shell. Magnetometers will map the induced magnetic field with unprecedented precision, revealing ocean depth and conductivity. Cameras will image the surface at resolutions allowing scientists to identify the freshest terrain, where material from below reached the surface most recently. That last capability could prove crucial. If Clipper can identify very young surface features, areas that formed within the last few years or decades, those locations offer the best chance of finding pristine ocean material before radiation has had time to alter it significantly. Timing matters in ways that aren't immediately obvious. Europa's orbit creates predictable patterns. Every 3-5 days, the Moon completes one trip around Jupiter. That orbital period determines when tides peak, when ice flexes most dramatically, and potentially when material from below has the best chance of reaching the surface. Clipper's mission design accounts for this. The spacecraft won't arrive at random moments. Its flybys will be timed to capture Europa at different points in its orbital cycle, sampling conditions when tidal forces are strongest and when they're weakest. This approach should reveal whether surface activity varies with orbital position. But there's a complication. Europa's surface doesn't respond instantly to tidal forces. Ice has memory. When stress builds, cracks don't necessarily open immediately. They might propagate hours or days later. When tidal forces relax, fractures don't seal up right away. Material could continue rising through a crack long after the peak stress has passed. This delayed response makes prediction difficult. Scientists can calculate exactly when tidal forces reach maximum strength. They can't say with certainty when a particular crack will open or when water might breach the surface. Clipper will have to sample the Moon repeatedly, building statistical understanding of how surface activity correlates with orbital mechanics. The spacecraft's trajectory creates its own set of constraints. Radiation near Jupiter is intense. Europa orbits deep within Jupiter's magnetosphere, where trapped charged particles create a radiation environment that would destroy unshielded electronics within hours. Clipper can't orbit Europa directly because sustained exposure would kill the spacecraft. Instead, it orbits Jupiter on a highly elliptical path designed to bring it close to Europa periodically while spending most of its time farther out where radiation is less severe. Each close approach lasts only hours. The spacecraft swoops in, gathers data frantically, then retreats to a safer distance. Those brief encounters must be choreographed precisely. Different instruments need different viewing geometries. Cameras want sunlight illuminating the surface at specific angles to reveal topography. Spectrometers need different lighting to identify surface composition. The radar works best when looking straight down through the ice. Mission planners spent years designing a sequence of flybys that balances these competing needs. Some passes prioritize imaging. Others focus on spectroscopy or radar. A few are optimized for sampling material above the surface, flying through regions where plumes might be active. The word "might" appears frequently in mission documentation. Plumes remain one of Europa's biggest mysteries. Hubble spotted what appeared to be water vapor erupting from the surface in 2012. Additional observations in 2014 and 2016 found similar features. These weren't continuous geysers like those on Saturn's moon Enceladus. They appeared intermittently, visible during some observations but absent during others. More recent observations haven't confirmed the plume detections. James Webb Space Telescope looked for plumes in 2023 and found nothing. That doesn't mean the earlier detections were wrong. It means plumes, if they exist, are sporadic and localized. This uncertainty shaped Clipper's design. The spacecraft carries instruments specifically built to detect and analyze plume material. But it doesn't depend on plumes existing. If Europa is actively venting ocean water into space, Clipper will sample it. If plumes are rare or absent, the mission can still accomplish its goals through remote sensing. That flexibility is critical because nobody knows what Clipper will actually encounter. Models predict certain features. Observations suggest others. But Europa has surprised scientists before. Every time new data arrives, it reveals something unexpected. Take chaos terrain. These are regions where the surface appears to have broken apart and were frozen in a jumbled mess. The first chaos terrain identified decades ago looked like enormous ice floes had drifted apart, rotated, and then frozen back together. Scientists proposed that liquid water or warm ice had risen from below, disrupting the solid surface. Higher resolution images complicated that picture. Some chaos regions show features that don't match simple flooding models. Others have characteristics suggesting multiple episodes of disruption. The process creating chaos terrain isn't straightforward melting and refreezing. Something more complex is happening. Carbon dioxide detections added another layer. Terra Regio, one of the largest chaos regions, shows concentrated carbon dioxide deposits. The carbon appears recently placed, geologically speaking. It hasn't been sitting on the surface for millions of years getting degraded by radiation. Something delivered it relatively recently. If that carbon came from the ocean, it means chaos terrain represents active exchange zones. These find ancient scars from billions of years ago. They're places where the ocean still communicates with the surface. That makes them prime targets for Clipper. But here's the challenge. Terra Regio covers an area larger than California. Concentrated carbon dioxide means higher levels than surrounding terrain, not a single rich deposit. The spacecraft will fly over this region multiple times, but each pass covers only a narrow swath. Finding the exact spots with the strongest signals requires careful targeting. Clipper's cameras can image at resolutions down to 50 centimeters per pixel during the closest approaches. That's detailed enough to see individual ice blocks and small-scale surface textures. But at that resolution, each image covers only a tiny fraction of Europa's surface. Taking pictures of everything at maximum resolution would require thousands of years. The mission strategy involves multiple resolution tiers. Wide area imaging identifies interesting regions. Moderate resolution imaging characterizes those regions in more detail. High resolution imaging targets the most promising specific features. This hierarchical approach maximizes the science return from limited flyby time. Similar logic applies to spectroscopy. Clipper carries two spectrometers, one working in visible and near-infrared wavelengths, another in thermal infrared. These instruments can identify surface composition, but they need time to gather enough light for clear signatures. The spacecraft can't point both spectrometers at every interesting feature during every flyby. Prioritization becomes necessary. Mission planners have already identified dozens of high-priority targets based on existing data. As Clipper begins returning its own observations, that target list will evolve. Early flybys will reveal new features that demand closer inspection during later passes. This iterative process mirrors how Galileo explored the Jupiter system in the 1990s. That mission's early observations raised questions that later observations addressed. Unexpected findings forced mission planners to revise strategies mid-mission. Clipper will likely follow a similar pattern. One advantage Clipper has is processing power. Galileo's computers had less capability than a modern smartphone. Data had to be compressed heavily before transmission to Earth, losing detail. Clipper's systems can do more onboard processing, making smarter decisions about what data to prioritize for transmission. That matters because communication bandwidth is limited. Europa sits over 600 million kilometers from Earth at Jupiter's closest approach. Radio signals take 33 to 52 minutes to travel one way, depending on planetary positions. The spacecraft can transmit data at rates up to 14 kilobits per second under optimal conditions, far slower than your internet connection. A single high-resolution image from Clipper's cameras might contain hundreds of megabits of data. Transmitting one image could take hours. The spacecraft will generate far more data during each flyby than it can possibly send home in the weeks between encounters. Onboard systems must decide what to transmit first. Engineers program priorities into Clipper's software. Certain measurements take precedence. Data from instruments that can't repeat an observation get transmitted before data from instruments that will have another chance. But the system also allows ground controllers to request specific data sets when something particularly interesting appears. This semi-autonomous approach represents decades of lessons learned from planetary missions. Early spacecraft were essentially remote-controlled robots. Every command came from Earth. Later missions gained more autonomy, able to execute pre-planned sequences without constant ground contact. Clipper sits somewhere between, capable of independent operation but still taking direction from mission control. That balance will be tested during the mission's most critical moments. When Clipper makes its closest approaches to Europa, sometimes skimming just 25 kilometers above the surface, communication delays mean ground controllers can't respond to unexpected situations in real time. The spacecraft must handle problems itself. Radiation poses the biggest threat during these close passes. Europa orbits within Jupiter's intense radiation belts. The spacecraft's electronics sit inside a vault with thick aluminum walls, but radiation still penetrates. Over time, cumulative exposure will degrade systems. Some components will fail eventually. The question is whether they'll last long enough to complete the mission. Engineers designed Clipper's radiation vault using techniques borrowed from nuclear reactor shielding. The walls use interlocking aluminum plates that scatter incoming particles, reducing their energy before they reach sensitive electronics. But aluminum alone can't stop everything. High-energy protons still penetrate. Some will strike memory chips, flipping bits from 0 to 1 or back again. Most bit flips won't matter. They'll occur in unused memory locations or get corrected by error-checking systems. Others will cause software glitches that the spacecraft can recover from by rebooting. A few might prove catastrophic. Mission planners accept this risk because there's no alternative. Clipper must operate in Jupiter's radiation environment to study Europa. The spacecraft carries redundant systems for critical functions. If one computer fails, another takes over. If a sensor stops working, others can partially compensate. This redundancy adds weight and complexity, but it's necessary insurance. The most vulnerable moment comes during each close flyby. Radiation intensity increases dramatically as Clipper drops toward Europa's surface. The spacecraft spends only minutes in the most intense zones, but those minutes accumulate. After 49 flybys, cumulative radiation exposure will reach levels that would kill a human in hours. Some spacecraft systems will certainly fail before the mission ends. The question is which ones and when. What happens if a critical system fails during flyby number 20? Mission planners have contingency protocols. If the main computer crashes, the backup takes control and executes pre-programmed safe mode procedures. The spacecraft points its antenna toward Earth and waits for instructions. Ground controllers assess the situation and upload new commands. This recovery process takes days. The spacecraft misses its next flyby opportunity, but the mission continues. Total mission failure becomes likely only if multiple redundant systems fail simultaneously. Probability calculations suggest this scenario is unlikely but not impossible. Radiation damage is partly random. A particularly energetic particle might strike a critical component in just the wrong way, causing cascading failures. Or gradual degradation might weaken multiple systems until a minor problem triggers total collapse. NASA accepted a calculated risk by approving this mission. Previous Jupiter orbiters, like Juno, stay farther from the planet and experience less radiation. Clipper ventures closer because Europa's science value justifies the danger. But there's no guarantee the spacecraft will complete all 49 planned flybys. Mission success is measured in data returned, not flybys completed. Assuming Clipper survives long enough to complete its primary mission, what comes next? The spacecraft carries enough fuel for potential mission extensions. If key systems remain functional after the planned flybys, NASA might approve additional observations. But Clipper can't stay at Jupiter indefinitely. Eventually, radiation damage will accumulate beyond recovery. When that happens, the spacecraft has one final task. Planetary protection protocols require that Clipper not contaminate Europa with Earth microbes. The spacecraft was assembled in clean rooms, but complete sterilization is impossible. Some hardy bacteria almost certainly survived the construction process, hiding in cracks and crevices. If Clipper crashed into Europa, those microbes might contaminate the subsurface ocean, compromising future searches for indigenous life. To prevent this, mission planners will deliberately crash Clipper into Jupiter or one of the other Galilean moons when the mission ends. The intense heat of atmospheric entry will vaporize any remaining biological contamination. This controlled destruction ensures Europa remains pristine for future missions. It also means Clipper is a one-way mission. The spacecraft will never return to Earth. Understanding what Clipper might find requires understanding what scientists already know about Europa's ocean. Galileo provided the first strong evidence for liquid water beneath the ice. Magnetic field measurements showed that something electrically conductive exists below the surface. In Europa's case, that something is almost certainly a global ocean of salty water. How salty? Estimates suggest Europa's ocean contains dissolved salts at concentrations similar to Earth's oceans, roughly 35 grams per liter. Magnesium sulfate appears particularly abundant based on spectroscopic observations of surface ice. That composition matters because it affects the ocean's chemistry and potential habitability. Recent analysis of old Galileo data revealed ammonia-bearing compounds on Europa's surface, concentrated near fractures where subsurface material might have emerged. Ammonia is chemically interesting for several reasons. It contains nitrogen, an essential element for life as we know it. Ammonia also lowers water's freezing point, potentially allowing liquid to exist at temperatures where pure water would freeze. Where did Europa's ammonia come from? Two possibilities exist. It might have been present in the original material that formed Europa billions of years ago, trapped in ice and rock. Or it might be produced by chemical reactions in the subsurface ocean today. Distinguishing between these scenarios requires understanding Europa's internal chemistry. The ocean's temperature provides another clue about habitability. Tidal heating from Jupiter should keep the ocean slightly above freezing, perhaps near 0 degrees Celsius. But the ocean isn't uniformly cold. Heat flows from Europa's rocky interior toward the ice shell. Temperature gradients create circulation patterns, potentially mixing nutrients throughout the water column. Does Europa's seafloor host hydrothermal vents like those found in Earth's oceans? This question sparked intense debate in early 2026 when researchers published calculations suggesting Europa's tidal heating might be insufficient to drive seafloor volcanism. Their models indicated that Europa's rocky core cooled long ago, leaving the seafloor geologically quiet. On Earth, hydrothermal vents support rich ecosystems independent of sunlight. Microbes harvest chemical energy from compounds dissolved in hot vent fluids. These ecosystems demonstrate that life doesn't require photosynthesis. Chemical energy alone can sustain biological communities. If Europa lacks hydrothermal activity, one potential energy source for life disappears. But the debate isn't settled. Other researchers proposed alternative mechanisms that might support habitability without requiring active volcanism. Radiation from Jupiter bombards Europa's surface, breaking chemical bonds in ice and creating reactive compounds. These radiation-produced chemicals might work their way down into the ocean through a process called crustal delamination. Here's how that might work. Dense, chemically altered ice on Europa's surface becomes heavier than the ice below it. Gravity pulls the dense material downward while lighter ice rises, similar to how Earth's tectonic plates move. This overturning process could transport surface chemicals into the ocean over millions of years, providing nutrients that life might use. Another possibility involves serpentinization, a chemical reaction between water and certain types of rock. When water percolates through olivine-rich rock, it triggers reactions that produce hydrogen gas and other compounds useful to microbes. This process occurs on Earth's seafloor even without volcanic activity. If Europa's rocky interior contains the right minerals, serpentinization might generate chemical energy regardless of whether the seafloor is geologically active. These competing models highlight how much remains unknown about Europa's interior. Clipper's measurements will constrain the possibilities. Magnetic field observations can reveal how thick the ocean is and how conductive it is, providing clues about salt concentration and temperature. Gravity measurements during flybys will reveal density variations in Europa's interior, indicating how the moon's mass is distributed between ice, water, and rock. The ice shell's thickness matters tremendously for future exploration. If the ice is only a few kilometers thick, a future lander mission might drill through it to reach the ocean directly. If the ice extends 15 or 20 kilometers deep, drilling becomes far more challenging. Clipper's ice-penetrating radar will measure thickness by timing how long radio pulses take to bounce off the ice-ocean boundary. Surface features provide additional clues about ice thickness. Chaos terrain, regions where the surface appears jumbled and disrupted, might form when warm ice rises from below, partially melting the overlying crust. The size and distribution of chaos terrain features can constrain thermal models of the ice shell. One particularly intriguing feature is Terra Regio, a region where recent observations detected carbon dioxide concentrated on the surface. Spectroscopic analysis suggests this carbon dioxide came from the subsurface ocean, not from asteroid impacts. That finding implies relatively recent exchange between the ocean and surface, possibly within the last few million years. If material from the ocean does reach the surface, it might carry chemical signatures of whatever exists in the water below. Organic molecules, if present, would be broken down by radiation quickly. But inorganic compounds would persist longer. Clipper's spectrometers will search for these chemical fingerprints, mapping their distribution across Europa's surface. The mission's most ambitious goal involves detecting life directly, though few scientists expect this outcome. One of Clipper's instruments, SUDA, will analyze tiny ice grains and dust particles as the spacecraft flies through the tenuous cloud of material surrounding Europa. Laboratory tests showed that SUDA can detect bacterial cell material in ice grains even when only 1% of the grain consists of biological matter. If Europa has plumes that occasionally erupt from the surface, SUDA might sample them. Previous observations from Hubble suggested plumes might exist, rising as high as 200 kilometers above the surface. But more recent observations with the James Webb Space Telescope found no evidence of active plumes during the periods observed. This doesn't mean plumes don't exist. It means if they do exist, they're sporadic, weak, or happening in places we haven't looked at the right times. Europa might be venting material only occasionally, perhaps when tidal stresses reach certain thresholds during specific points in its orbit. The Moon experiences maximum tidal flexing when it's farthest from Jupiter, and that's when plumes would most likely occur. Think about trying to photograph lightning. You might point your camera at the sky for hours and see nothing, but that doesn't prove lightning never happens. You need to be looking at the right place at the right time. Europa might work the same way. The surface could be quiet for months or years, then suddenly release a burst of water vapor that lasts only hours before subsiding. Clipper's trajectory was designed with this uncertainty in mind. The spacecraft won't orbit Europa directly. Instead, it will orbit Jupiter and make close flybys of Europa every few weeks. Each flyby will take the spacecraft through different regions above Europa's surface at different times in the Moon's orbital cycle. This approach maximizes the chances of intercepting a plume if one happens to erupt during the mission. The spacecraft's path will carry it as low as 25 kilometers above Europa's surface during some passes. That's remarkably close for a spacecraft traveling at several kilometers per second. At that altitude, SUDA will be positioned to capture ice grains ejected from any active plumes. Even if no dramatic eruptions occur, the instrument should still detect particles knocked off the surface by micrometeorite impacts or sputtered away by Jupiter's intense radiation. Radiation poses both a challenge and an opportunity. Jupiter's magnetic field traps charged particles, creating radiation belts far more intense than Earth's Van Allen belts. Europa orbits within these belts, and the Moon's surface receives a radiation dose that would be lethal to any exposed organism within hours. This radiation constantly bombards the ice, breaking chemical bonds and creating reactive compounds. On one hand, this makes Europa's surface inhospitable. No life could survive exposed on the surface for any meaningful length of time. But on the other hand, the radiation creates oxidants, molecules with extra oxygen atoms that can participate in chemical reactions. These oxidants might accumulate in the ice and eventually make their way down to the ocean through the processes discussed earlier. If they do, they could provide an energy source for life independent of sunlight. Earth's deep ocean vents support ecosystems using chemical energy rather than photosynthesis. Microbes near these vents metabolize hydrogen sulfide and other chemicals released by geological activity. Europa's ocean might host similar communities, except the energy would come from radiation-produced oxidants rather than volcanic chemistry. Testing this hypothesis requires understanding what chemicals actually exist in Europa's ocean. Clipper's infrared spectrometers will map the composition of surface ice in detail, identifying organic molecules, salts, and other compounds. Different materials absorb infrared light at different wavelengths, creating unique spectral signatures. By analyzing these signatures, scientists can determine what's present and in what concentrations. The mission will pay particular attention to regions where subsurface material might have recently reached the surface. Chaos terrain and the areas around large fractures are prime targets. If ocean water has indeed been exposed at these locations, it might still retain some of its original chemistry before radiation alters everything beyond recognition. Temperature measurements add another layer of information. Europa's surface averages around -160 degrees Celsius at the equator and drops to -220 near the poles. But thermal cameras can detect warm spots where heat from below might be reaching the surface more easily. These thermal anomalies could mark places where the ice is thinner or where liquid water has recently been present near the surface. One instrument, reason, will be especially important for understanding ice thickness. This ice-penetrating radar transmits radio pulses downward and measures how long they take to bounce back. Ice and water reflect radio waves differently, so the radar can distinguish between solid ice and liquid water below. By measuring the time delay and signal strength of return pulses, scientists can map the ice shell's thickness across different regions. If the ice varies in thickness significantly, that tells us something important about Europa's interior dynamics. Uniform thickness would suggest a relatively stable ice shell with consistent heat flow from below. Variable thickness implies more complex processes, perhaps convection cells in the ice or localized heating from tidal friction. These variations would affect how easily material can move between the ocean and surface. The radar will also search for liquid water pockets within the ice itself. Some models suggest the ice shell might not be a solid block but rather a mixture of pure ice, slushy layers, and isolated liquid reservoirs. These subsurface lakes, if they exist, could be important intermediate environments between the ocean and the surface. They might be more accessible than the deep ocean while still being protected from surface radiation. Gravity measurements during each flyby will reveal Europa's internal structure more broadly. As Clipper approaches Europa, the Moon's gravity will pull slightly on the spacecraft, changing its velocity in ways that can be measured precisely using radio signals sent back to Earth. By analyzing these velocity changes during multiple flybys, scientists can construct a gravity map of Europa. This map shows where mass is concentrated within the Moon. A thick ice shell and deep ocean would produce one gravity signature. A thin ice shell and shallow ocean would produce another. The measurements will also reveal whether Europa's rocky interior is differentiated, with heavier elements sinking toward the core, or whether it remains a more uniform mixture. Magnetic field measurements will complement the gravity data. Europa's induced magnetic field arises because Jupiter's powerful magnetic field sweeps past the Moon every 11 hours as Jupiter rotates. This changing magnetic field induces electrical currents in any conductive material inside Europa. Salt water conducts electricity far better than ice or rock, so the strength and behavior of Europa's induced magnetic field provides information about the ocean's thickness, depth, and salinity. The magnetometer aboard Clipper will measure Europa's magnetic field during each flyby, building up a detailed picture of how it varies across the surface and over time. These measurements, combined with the gravity and radar data, will constrain models of Europa's interior structure more tightly than ever before. All of these investigations point toward a single overarching question. Does Europa have the conditions necessary for life? Notice that's different from asking whether life actually exists there. Clipper wasn't designed to search for life directly, though SUDA might accidentally detect it if organisms happen to be present in surface ice grains. The mission's goal is more fundamental, determining whether Europa could support life. That requires three things. Liquid water. Check. Europa almost certainly has a global ocean. Chemical building blocks. Probably. We've detected carbon dioxide, salts, and ammonia on the surface, all of which likely came from the ocean. Energy sources. This is the uncertain part. If the seafloor is geologically active, hydrothermal chemistry could provide energy. If not, radiation-produced oxidants might fill that role, assuming they can reach the ocean in sufficient quantities. Clipper will address each of these requirements. The mission will confirm the ocean's existence beyond any doubt, measure its properties, and determine its composition. It will assess how much exchange occurs between the ocean and surface. It will search for evidence of recent geological activity. And it will evaluate whether the moon's internal heat budget allows for seafloor processes that could generate chemical energy. The spacecraft will also document Europa's geology in unprecedented detail. High-resolution cameras will image the surface at scales of less than 1 meter per pixel in selected areas, revealing small-scale features that might indicate recent activity. Wider area images at lower resolution will provide context, showing how different terrain types relate to one another. Scientists will use these images to construct detailed maps of Europa's surface, identifying regions of interest for potential future missions. If plumes are detected, their source locations will be prime targets. If certain areas show strong evidence for thin ice or recent water exposure, those become candidates for a future lander or even a mission that could penetrate the ice. But all of that comes after Clipper arrives in April 2030. Between now and then, the spacecraft must survive a journey of nearly 3 billion kilometers through deep space. It must execute a precisely timed gravity assist at Earth in December 2026, using our planet's gravity to accelerate toward Jupiter. And it must withstand Jupiter's intense radiation environment once it arrives, a challenge that required extensive shielding and radiation-hardened electronics. The mission engineers designed Clipper's trajectory specifically to minimize radiation exposure. Instead of orbiting Europa directly, which would subject the spacecraft to constant bombardment, Clipper orbits Jupiter in a highly elliptical path. Each orbit brings it close to Europa for a brief flyby, then carries it far away from Jupiter's most intense radiation belts. This approach allows the spacecraft to accumulate the necessary science data while spending minimal time in the harshest environment. Even so, the radiation dose adds up. Jupiter's magnetic field traps charged particles, creating radiation belts far more intense than anything near Earth. By the end of its mission, Clipper will have received a total radiation dose equivalent to several million chest X-rays. That would kill a human instantly, but the spacecraft was built to withstand it. Critical electronics sit inside a thick-walled vault made of titanium and aluminum. Cables are specially shielded. Software can detect and correct errors caused by radiation hitting computer chips. Every component was tested to ensure it could survive. But there's another challenge nobody talks about much. The spacecraft has to work autonomously for long periods. Radio signals take nearly an hour to travel between Jupiter and Earth, so real-time control is impossible. If something goes wrong during a flyby, the spacecraft must recognize the problem and fix it before ground controllers even know there's an issue. That requires sophisticated onboard systems capable of monitoring spacecraft health, diagnosing problems, and executing contingency plans without human intervention. NASA tested these systems extensively before launch. Engineers simulated every failure mode they could imagine, then programmed responses into Clipper's software. The spacecraft knows how to save itself if it detects anomalies. It can switch to backup systems, adjust its orientation, or abort a flyby if necessary. This autonomy is essential because each flyby happens fast. At closest approach, Clipper races past Europa at several kilometers per second. The entire science observation period lasts only a few hours. Miss that window and you have to wait weeks for the next opportunity. The 49 flybys are carefully choreographed. Each one targets a different region of Europa's surface, gradually building up global coverage. Some passes focus on the leading hemisphere, the side that faces forward as Europa orbits Jupiter. Others examine the trailing hemisphere. Several flybys are dedicated to high-priority targets like Terra Regio, where carbon dioxide and salts indicate recent exchange with the subsurface ocean. The lowest altitude passes, skimming just 25 kilometers above the surface, are saved for later in the mission after engineers gain confidence in the spacecraft's performance. What happens after Clipper completes its mission in 2034? The spacecraft won't have enough fuel left to return to Earth, and leaving it in orbit around Jupiter poses a contamination risk. There's a small chance, probably very small, that microbes from Earth could have hitched a ride despite NASA's strict sterilization procedures. If Clipper eventually crashes into Europa, those microbes might contaminate the subsurface ocean. That would be an ethical disaster, potentially compromising one of the solar system's best chances for finding life. So NASA plans to deliberately crash Clipper into Jupiter or one of the other Galilean moons at the end of its mission. This is called planetary protection. The Galileo spacecraft met the same fate in 2003, plunging into Jupiter's atmosphere to prevent any possibility of contaminating Europa. Clipper will likely follow suit. The exact disposal method depends on what orbit the spacecraft is in when it runs out of fuel, but the principle remains the same. We don't contaminate worlds where life might exist. Assuming Clipper succeeds, what comes next? The mission's findings will shape future exploration strategies. If the ocean appears highly promising, with strong evidence for recent geological activity and abundant chemical nutrients, NASA and other space agencies will likely prioritize a Europa lander. Such a mission would face enormous technical challenges. Landing on Europa's icy surface is difficult enough, but the real goal would be to access the subsurface ocean. That means drilling through kilometers of ice, an engineering problem we haven't solved even on Earth in comparable environments. Antarctica's Lake Vostok sits beneath nearly 4 kilometers of ice. After decades of effort, Russian scientists finally reached it in 2012, but the drilling process was slow, difficult, and raised contamination concerns. Europa's ice is colder, harder, and possibly thicker. It exists in a vacuum with no atmosphere to moderate temperature swings. And any mission there must be completely autonomous because of the communication delay. You can't have a human geologist making decisions in real time. Some mission concepts bypass the drilling problem entirely. Instead of landing, they would fly through Europa's plumes, if those plumes actually exist and can be reliably detected. A spacecraft passing through a plume could sample ocean water directly, analyzing it for signs of life without ever touching the surface. But that approach depends on plumes being active when the spacecraft arrives. Current evidence suggests they're intermittent at best, possibly erupting only when Europa is at certain points in its orbit. Timing a mission to coincide with a plume eruption is risky. Another possibility is an ice-penetrating probe. This concept envisions a nuclear-powered device that melts its way down through the ice, trailing a communication cable behind it. Once it reaches the ocean, it could deploy sensors to measure water properties, search for organic molecules, or even look for moving organisms. This sounds like science fiction, but NASA has funded preliminary studies. The technology isn't ready yet, but it might be within a few decades. All of these future missions depend on what Clipper discovers. If the spacecraft finds that Europa's ice is thicker than expected, or that the ocean has less interaction with the surface than hoped, enthusiasm for a follow-up mission might cool. If it finds strong evidence for thin ice, active plumes, and rich chemical exchange, the case for a lander becomes compelling. That's why Clipper's reconnaissance is so crucial. It sets priorities for everything that follows. There's also the broader question of what Europa tells us about life in the universe. If we find even simple microbes in Europa's ocean, that discovery fundamentally changes our understanding of biology's prevalence. Life on Earth might not be a unique miracle but rather an inevitable consequence of liquid water and chemical energy. And if it happened twice in one solar system, it probably happened countless times across the galaxy. On the other hand, if Europa has all the right ingredients but remains lifeless, that suggests life is rarer than we thought. Either answer matters. Europa represents something profound in human exploration. For most of history, we could only wonder about other worlds. Now we build machines capable of traveling billions of kilometers to investigate them. We design instruments sensitive enough to detect molecules in ice grains. We write software that lets spacecraft think for themselves. And we do all of this driven by a single question that humans have asked since we first looked up at the stars. Are we alone? The answer might be waiting beneath Europa's ice. In April 2030, Clipper will begin its search. The spacecraft will spend 4 years mapping an alien ocean world, measuring its properties, testing its chemistry, and evaluating its potential to support life. We won't know what it finds until it looks. But either way, what we learn will reshape how we understand our place in the universe. Because if life can exist in the cold, dark waters of a moon orbiting Jupiter, then the cosmos is far stranger and more alive than we ever imagined. That's worth the journey. The spacecraft carrying humanity's best instruments for detecting alien life is already on its way. By the time you're watching this, Clipper has left Mars behind and is accelerating toward its December 2026 Earth flyby. That gravity assist will slingshot it toward Jupiter at speeds we can barely comprehend. Every second brings us closer to answers we've been seeking for generations. Think about the audacity of this mission. We built a spacecraft the size of a basketball court, packed it with instruments sensitive enough to detect a 1% of bacterial material in a microscopic ice grain, wrapped its electronics in radiation shielding thick enough to survive Jupiter's particle bombardment, and launched it on a 6-year journey to a moon where temperatures would freeze your breath solid in seconds. All to answer one question: could something be alive in Europa's ocean? The weird part is we might already know the answer before Clipper arrives. Not from the spacecraft, but from the data it's designed to collect. If Europa's plumes turn out to be real and active, and if one of them happens to erupt while a ground-based telescope is watching during the 2020s, we might detect organic molecules or chemical signatures that suggest biology. That would fundamentally change Clipper's mission from reconnaissance to confirmation. But here's what makes Europa different from every other place we've explored. Mars might have had life billions of years ago. Venus might have been habitable before its atmosphere went rogue. Europa potentially has life right now, swimming in an ocean that has existed for most of solar system history. If organisms evolved there, they've had 4 billion years to adapt, diversify, and spread through a water volume twice as large as Earth's oceans. That's not a marginal environment clinging to existence. That's a world. The implications split in 2 directions depending on what Clipper finds. Discovery of life, even microbial life, would prove biology isn't unique to Earth. It would suggest that given liquid water, chemical building blocks, and energy, life emerges almost inevitably. That would make the universe less lonely but more mysterious. Because if life is common, why haven't we detected any signs of intelligence? Either technological civilizations are rare, or they don't last long, or they exist but remain invisible to our searches. None of those options is comforting. The alternative might be worse. If Europa has everything life needs but remains sterile, that suggests something is missing from our understanding. Maybe the origin of life requires conditions we haven't identified yet. Maybe the jump from chemistry to biology is so improbable that even 4 billion years in a massive ocean isn't enough time. If Europa is dead, it raises uncomfortable questions about how rare Earth's biosphere might be. Either way, Clipper's data will reshape astrobiology. The mission will establish whether Europa's ocean is habitable in practice, not just in theory. It will measure the ice thickness, map the chemistry, evaluate the energy budget, and determine how much exchange occurs between the ocean and surface. Those measurements will tell us whether a future mission could realistically access the ocean and what it might find there. The engineering challenges facing any follow-up mission are staggering. Drilling through kilometers of ice in a vacuum at -200 degrees with no human supervision isn't something we know how to do yet. But neither was landing on Mars, or flying a helicopter in its thin atmosphere, or catching a rocket booster with mechanical arms. We solve problems like this by trying, failing, learning, and trying again. Europa might require decades of development before we can touch its ocean. But the fact that we're seriously planning for it means we've crossed a threshold as a species. There's something almost absurd about the whole endeavor. Humans, creatures that evolved to survive in Earth's oxygen-rich atmosphere at comfortable temperatures, spending billions of dollars to investigate whether microbes might exist in a freezing ocean beneath 20 kilometers of ice, 390 million miles from home. We can't eat anything we find there. We can't colonize it. We can't extract resources from it. The entire mission serves pure curiosity, our need to know what's out there. That might be the most human thing we do. Every civilization that has ever existed has looked at its boundaries and wondered what lies beyond. We crossed oceans not knowing what was on the other side. We climbed mountains because they were there. We went to the moon partly to prove we could. Now we're sending robots to investigate an alien ocean because we need to know if we're alone. The question drives us in ways that practical concerns never could. The timeline stretches ahead. Clipper arrives at Jupiter in April 2030. First science operations begin shortly after. The 49 flybys will take 4 years to complete, ending in 2034. Data analysis will continue for years beyond that as scientists work through the measurements, compare them to models, and piece together a comprehensive picture of Europa's interior. We might not have definitive answers about habitability until the late 2030s. And if those answers justify a follow-up mission, that spacecraft won't launch until the 2040s at the earliest. Most people reading this will live to see the results. That's remarkable when you think about it. Previous generations could only speculate about other worlds. This generation will know whether at least one of them could support life. Your children might grow up in a world where the existence of extraterrestrial biology is an established fact, not a hypothesis. The implications of that shift are difficult to grasp. But we're not there yet. Right now, Europa remains a mystery. Its ocean stays hidden beneath ice that has never felt sunlight. Whatever exists down there, if anything, has never been observed by human eyes or instruments. Clipper will change that. In April 2030, when the spacecraft makes its first close pass, we'll begin seeing Europa as it actually is, not as we imagine it might be. Some of our assumptions will prove correct. Others won't. The moon will surprise us because nature always does. What we're witnessing is the beginning of a new phase in human exploration. For centuries, we explored Earth's surface, mapping continents and oceans. For decades, we've been exploring space, sending probes to planets and moons. Now we're starting to explore the interiors of those worlds, investigating oceans and atmospheres and geological processes happening beneath surfaces we can barely see. Europa is the first target of this deeper investigation, but it won't be the last. Saturn's moon Enceladus also has a subsurface ocean and active plumes. So does Saturn's largest moon Titan, though its ocean is probably too cold and too far beneath the surface to access easily. Other candidates exist throughout the outer solar system. The search for life is expanding from a question about Earth's uniqueness to a systematic survey of potentially habitable environments across multiple worlds. This is the future of astrobiology, not waiting for signals from distant civilizations, but investigating the places where life might exist right now in our cosmic neighborhood. Europa leads that investigation because we can actually get there with current technology and because the evidence for its ocean is so strong. But it's part of a larger project that will occupy humanity for generations. When Clipper completes its mission in 2034, it will have generated more data about Europa than all previous missions combined. That data will feed into models, simulations, and predictions about what the ocean contains. It will guide the design of future missions. It will answer old questions and raise new ones. And somewhere in those terabytes of measurements might be a signature that changes everything, a chemical anomaly that can't be explained by geology alone, a pattern that suggests something other than sterile water beneath the ice. Or maybe not. Maybe Europa will turn out to be a magnificent but lifeless ocean, a reminder that water and chemistry alone aren't sufficient. We'll learn something profound either way. That's the nature of genuine exploration. You don't know what you'll find until you look, and the act of looking transforms your understanding regardless of the outcome. Europa forces us to confront possibilities we can barely articulate, questions about the nature of life and its distribution in a universe that we're only beginning to learn how to ask properly. The spacecraft flying toward Jupiter right now carries more than instruments and computers. It carries our best attempt to answer whether Earth's biology is an isolated accident or part of a broader pattern. In 4 years, when Clipper begins its flybys, we'll start getting answers. Those answers will shape how we think about our place in the universe for the rest of human history. Because knowing whether we're alone changes everything about how we understand ourselves and our future. Europa might tell us that story. We just have to wait for the spacecraft to arrive and start reading what's written in the ice.